Hey grade 12s and welcome to this video. I want to wish you all a Merry Christmas and a Happy New Year in advance. I hope you guys are doing well and are having a great holiday. As you have probably seen in the title of this video is a compilation of calculus questions from exam papers that I have uploaded so far. It's about 9 hours long and it's meant to assist you when studying for calculus, along with the first calculus compilation video I posted. I plan to also compile other exams based on focused topics like functions and trigonometry, so you guys can recommend the compilations you would like to see in the comments. Okay, get your notebooks out. Make sure to attempt the question first before playing the video for the solution, and let's get into this video. Hey grade 12s and welcome to question 7 of this paper. So 7.1 says, determine f prime of x from first principles if f of x is equal to negative 2x squared plus x. Okay, so we have to determine the derivative of this from first principles. You can start off with finding the equation of f of x plus h. So this just means that wherever you see x, you're going to replace that with x plus h. So this is equal to, we have a negative 2, and then we see x. So we replace that with x plus h, and that will be all squared. Then again, plus x, so we'll say plus x plus h. And then let's just expand and FOIL. So we're going to have first just a negative 2 because this whole bracket is being squared. So then we will have, you can just work with it like this instead. We're going to take x and we're going to square it, and we have x squared. Then we multiply the first and the second term, and that will give us xh. Then you take that and multiply that by 2. So that will give you a positive 2xh. Then we have plus the last term squared, h squared, close bracket, plus x plus h. And then we can go ahead and just multiply the negative 2 into this bracket. So we will have negative 2x squared, and then a negative 4xh, then a negative 2h squared plus x plus h. So just be very careful as you're working with this. You see, it is 5 marks, and this is really where you can score marks. And now to find the derivative. So the derivative is f prime of x is equal to the limit of h tending to 0 or approaching 0. And then we have f of x plus h minus f of x all over h. Okay, remember this is really just the gradient formula. It's y2 minus y1 over x2 minus x1. That's where it comes from. And so we're saying this is equal to the limit as h approaches 0, and then we have the equation of f of x plus h. And the equation of f of x plus h that we have is all of this. So we just rewrite everything very carefully and just make sure that you're not missing anything. So 2h squared plus x plus h. Then we have to minus this by the equation of f of x. And you see that f of x has 2 terms, so you need to include brackets first. And then you put in that equation. So that's negative 2x squared plus x all over our h. Then now this negative is going to multiply into that expression with 2 terms. So rewrite everything again carefully. Don't also forget to keep writing the limit as h approaches 0 up until you substitute h as 0. So when we're multiplying in, this negative multiplies to this negative and becomes a positive. So now we have a positive 2x squared. And then this negative is multiplying to this positive x, making a negative x all over the h that we have. Now the one thing you should notice here is that what you are subtracting by these values, this is usually what's going to cancel across all of this. So because I see a positive 2x squared, I know somewhere there must be a negative 2x squared, and there it is. So negative 2x squared will cancel with a positive 2x squared. And then I have a negative x here, so I know somewhere I must have a positive x. So there's the positive x cancelling with that negative x. And so we are left with, again, we have to say the limit as h approaches 0. Then we have negative 4xh, and then minus 2h squared plus h all over h. Then lastly, we take h out as a common factor because we cannot substitute in h as 0 because that will make this undefined. And so that's the whole point of doing this. So as h approaches 0, we're saying h out as a common factor. And then we will have in here what is left. So take this and divide it by the h. The h's will cancel. You'll be left with negative 4x. Take this as well, the second term, divided by h. The h squared, one of the h's cancel, and you're left with negative 2h. And then this positive h divided by h will be a positive 1 all over the h. Then this 2h's can cancel. Then we have, again, the limit. You can rewrite this, but it's not really necessary. You can just choose to just substitute at this point. So now I'm going to substitute in place of h. So I'm just going to say negative 4x minus 2, and then in place of h, I'm just saying 0 plus 1. And so f prime of x is equal to negative 4x. That becomes a 0, and then that becomes plus 1, as we just have it like that. And so that is that. So just be very careful with this. Remember, it is 5 marks, so it's really a place that you can score marks. So moving on to 7.2. 7.2.1 says that we have to determine the derivative of this function. So this is also a thing where you have to remember the way the notation of these things work. First of all, let's look at the function and see, is this ready to be derived? Well, we have a surd with x on the denominator. You see, a surd is not the problem. It's only a problem where there is an x in that surd. Then it needs to be changed in a way that it's not a surd, but instead its exponent is a rational number. So we're going to have to change that first and then still move it to the numerator because we shouldn't have any x in the denominator. So right now that seems like the only problem. Okay, so what I'm going to do is we're going to keep writing this as is equal to dx, and we're going to just simplify. So as long as you're not deriving yet, you're going to keep writing is equal to dx. And so we have the negative 5x on top, which is fine. And we're going to change the surd. And so you're going to have the base of x. And now you have to just think about the exponent on top of the x is an invisible 1. And the exponent behind this radical, the square root, is actually an invisible 2 because it's a square root. That's why with the cube root, you have a 3 here instead. And so to make this exponent a rational number, you keep the base and you say the inside exponent over the outside exponent. So that's 1 over 2. And then we have the minus x squared over 5. And then we can go ahead and take this to the numerator because it shouldn't be on the denominator. When you take this to the numerator because it has an x in it, the exponent is going to become negative. So again, we're still writing dx because we are not deriving yet. So we have negative 5x. And then that x is going to come to the numerator and it's being multiplied now by the x. And the exponent now becomes negative. So negative 1 over 2. I'd like to also add that instead of taking that x to the numerator, what we could have done is just divided the x's. So we see that we have an x here, and it's actually raised to the power of an invisible 1. And we have an x to the power of a half. So if the bases are the same and you're dividing, you would just subtract the exponents. So it's like saying the 1 minus the half. So we have x to the power of a half instead. So that's something else you could have done. And then there's also a way you can rewrite this just in a way that it will be easier for you to derive it. In front of the x squared, there is an invisible 1. So I'm going to write that invisible 1. And so this is really what I can write this as. I can write this as minus 1 over 5 x to the power of 2. Because that x is on the numerator, and this x is also on the numerator, I can choose to write it with the 1 or away from the 1 because it's really like multiplied by x over 1. So if we had to put it back, it's the 1 or the negative 1 times the x squared, which will give you the negative 1x squared over the 5 times the 1, which gives you the 5. So I can write it just like that. We can go ahead and simplify this part. So we have is equal to, again, I still have to say dx because I'm not deriving yet. Then we're saying the negative 5, and now the x and the x. When the bases are the same and we are multiplying, you need to add the exponents. The the exponent on top of this x is an invisible 1. And so when you're adding the exponents, it's like saying 1 plus negative a half. And if you say 1 plus negative a half, you see that that positive and that negative will just multiply, giving you 1 minus a half. So here we're just going to have x to the power of that 1 minus a half. And of course, that is going to give you a half, so we don't have to rewrite another line again. So that gives you just a half. And then we can continue, and we're going to have minus 1 over 5x squared. And now this is ready to be derived. So we're going to take the coefficient and multiply to the exponent. So that is a negative 5 times a half. And you see the numerator times the numerator, that is going to be a negative 5. And then the denominator, which is really just a 1, multiplied by 2 will give you a 2. So we have negative 5 over 2 there. We have negative 5 over 2, and then we have x, and then we have to say a half minus 1. So if you take a half minus 1, you're going to get negative a half. And then we have, again, we're taking the coefficient and multiplying it by the exponent. Negative 1 over 5 times 2 will give you negative 2 over 5. And we have x, and then that 2 minus 1 just gives you 1. But we don't have to write the 1 here because there's an invisible 1. That is the one that is left. And now we are done with this. So now you can just rewrite this in a way that this negative a half is positive. So this exponent of x. So we can write this like this. The 5 is on the top. This is also on the numerator. So we can take it to the denominator so that its exponent can become positive. So we're going to have the negative 5 all over 2, and now we have x to the power of positive a half minus 2 over 5x. Or if you like, you can write this as 2x over 5. It's still going to be correct. So there we go. That's the derived form of that. Moving on to 7.2.2. And now 7.2.2, we have to determine the derivative of this function. Okay, so there's something I want you to notice about this function. Look at the first term in this first bracket. We have x, and then we also have x here. And then we have a 2 over x, and we also have a 2 over x here. So notice that first and the second term are both the same. The only difference is that we have a plus here and a minus here. Okay, so that should remind you of difference of two squares. Because difference of two squares would work like this. If you have x minus 2, and then an x plus 2, or let me put it in the same order. So if you have an x plus 2 and an x minus 2, if you want to simplify this, instead of foiling out, there's no use of doing that. It is difference of two squares. You have to just identify that it is. Then all you're going to have to do is multiply the first two terms, and that will become x squared, and multiply the last two terms, and that will be negative 4. So that it's going to simplify like that, even if you had foiled out. So that's what we're going to do to these ones as well. So we're saying it's equal to d over dx, because we have not derived yet. We're not deriving yet. And we open a bracket, and now we are saying the x multiplied by the x, and that will give you an x squared. And then the positive 2 over x multiplied by the negative 2 over x. So the numerators and the numerators would multiply. Remember, it's a positive times negative, which gives you a minus. And then we have 2 times 2 giving you a 4 over the x times the x giving you an x squared. So this is what we have so long. And then look at this and ask yourself, is this ready to be derived? Well, no, it's not ready to be derived because we still have an x on the denominator. So we need to take it to the numerator. But when you take it to the numerator, it will cause that exponent to become negative. So what we're going to have is we still have the d over dx because we're not deriving it. And then we have the x squared, which is okay. Then minus 4. And now that comes to the numerator and becomes x to the power of a negative 2. And now this is ready to be derived. So deriving this, now I'm just going to say is equal to, I'm not going to rewrite that. So the x squared, the coefficient of x is an invisible 1 multiplied by the exponent will give you 2. Then we have x, and we have to say 2 minus 1, which is 1. And so it's an invisible 1. I don't have to write the 1. Then the coefficient of x to the power of negative 2 is negative 4, multiplied by the exponent of negative 2 is positive 8, and we have x to the power of negative 2 minus 1 is negative 3. So you can just rewrite this in a way that the exponent is positive. So this will just be, we have the 2x plus, we have just the 8. The 8, it doesn't have a problem. The exponent is not negative. It's the x that needs to go to the denominator. So over x to the power of a positive 3. And so that would be your derived function. Okay, now we move on to question 8. So question 8 says, the sketch below represents the function f of x is equal to x cubed plus bx squared plus cx plus d, and g of x is equal to ax squared plus q. The points A, which is over here, B, which is to a negative 16 over there, and C are points where the two graphs intersect, so those 3 points. Then C, 6 and 0, is an intercept of f, while L and M are turning points of f. Okay, so we have that point over there. The first question is to show that B is equal to negative 5, C equals negative 8, and D equals 12, if it is given that f prime of x is equal to this. Okay, so they want us to determine the values of B, C, and D if they're giving us the derivative of this function. So remember, they gave us the original of this function as this. So let me just rewrite that. So they gave us the original of this function, but then they're also telling us that it is given that f prime of x is equal to this. So if they're giving us the derivative of this function, how about we derive this one as well? And that way we'll be able to match the coefficient of x squared with the coefficient of x squared, the coefficient of x with that one's as well, and the constant with this one. So if we derive this, f prime of x is equal to, so we're going to have the coefficient of 1, the invisible 1 here, times the 3, which gives you 3x. And then 3 minus 1 is 2, so squared. Then we have this coefficient of x, which is positive b times 2, and that gives us a positive 2b. Then we have x to the power of 2 minus 1, and 2 minus 1 is 1. We don't have to write that 1. And then we have positive c times the invisible exponent of 1 on top of that x. And that will just give us a positive c. Then, of course, the x also has an exponent of 1, an invisible exponent of 1. And we have to take out a 1 from that minus 1. And that is now going to become 0. And anything to the power of 0 gives you 1. So that became a 1. And so the c multiplied by the 1 will just give you the c. Then d is a constant because it doesn't have an x in it. It's the only value here without a variable. So that becomes 0 when it's derived. Okay, so when we derive this, this is what we get. So if you compare this with this, notice that the coefficient of x squared over here and x squared over here, they're exactly the same. It's 3 and 3, which is fine. And so since these two equations are really the same thing, they're both the derived versions of the f equation of this. So we're going to equate this, the coefficient of x, which is negative 10, we're going to equate it with the coefficient of x here, which is positive 2b. So we're saying we have 2b, and we're going to equate that with the negative 10. And we're also going to take the constant here of the f prime of x and the constant of the f prime of x, and we're going to equate those. So c is equal to the negative 8. Okay, so let's go ahead and solve for b here. We'll divide both sides by 2, and so b is equal to negative 5. So this is the value of b, and that's the value of c. So we have b and c. We just have to find d. D was in the original equation. So let's put these back into the original equation so that we can find d. So we're going to have f of x is equal to x cubed. Then we have plus bx squared, but it's a negative 5, so we say minus 5x squared plus c, but we have negative 8, so negative 8x, and then plus d. So because d is the only thing missing, if we just have a point that we substitute in place of x and y, we can find d. So let's go ahead and see what point do we have on this graph. As you can see, we have a point b, 2 and negative 16. You also have this 6 and 0. Well, I'll just go with this one. So 2 and negative 16. I'm going to substitute this into this equation, 2 and negative 16. So I'm saying f of 2, because this is an x value I'm substituting, is equal to 2 all cubed minus 5 times 2 all squared minus 8 times 2 plus d. And so if 2 is the x value, we know that negative 16 is the y value. So in place of f of 2, I'm saying negative 16 as the y value is equal to. Now you would notice that all of these are numbers. Everything over here is a number. So you could just put everything here onto the calculator, then we have the plus d. And when I put everything onto the calculator, I get a negative 28, so negative 28. And then I have the plus d. So you see, this is just an equation. We have to solve for d. So I'm going to take negative 28 over, and it becomes a positive 28. And we still have the minus 16. Minus 16 is equal to d. So what's positive 28 minus 16? And so that gives us 12. So d is equal to 12. And there we have found everything. We found the value of b, c, and d. Okay, moving on to the next question. The next question, 8.2, says, determine the coordinates of the turning points L and M of f. And remember, this is for 5 marks. So this is really a place that you can score marks. So these are turning points. It's the points L and M. When you're thinking about the turning point of a function, this is the point where the gradient, the gradient of this function is equal to 0. And that's why they're called stationary points. At this point, they're neither increasing nor decreasing. They're just stationary. So they're where this function has a gradient equal to 0. So how do we find the gradient of the function? You find the gradient of the function by deriving the function. When we derive the function, that is finding the gradient at any point. So we're going to derive this function, and we know this stands for the gradient, so we're going to make this gradient equal to 0. Okay, now the good thing about this is that we already have the derivative of f. They told us the derivative of f when they told us it was given that f prime of x was equal to this. So we can just rewrite this equation and set it equal to 0. So here's the function, and so this is the gradient itself, the gradient function. So we set it equal to 0, and we have 3x squared minus 10x minus 8. So now we have to factorize this. Now you could use the quadratic formula, but you will lose 1 mark for not including your factors. So I'm going to actually just factorize this like the way it should be factorized. We have 3x squared minus 10x minus 8. Notice there is no common factor here. So we have to just factorize this. So there's a method I use, it's called the cross method. So I'm going to take the factors of the first term. The first term is 3x squared. So what times what gives you 3x squared? And that would just be 3x multiplied by x. And then you look at the last term, and we're going to ask what times what will give us this last term. So the factors of the last term, and that can be 4 and 2, it can be 8 and 1, but you have to really think about it like this. If you used 8 and 1, is that really going to help you to get the middle term? Even if you said 3 times 1, that would just give you a 3x, the 3x, and 8x times 8, that would just give you an 8x. And you can see, even if you added these together, they would give you an 11x. It's not 10x in any way. So I know those factors aren't going to work. So I'm going to try 4 and 2, but you now need to put them in a way that it will work. Also remember, 8 is negative, meaning one of the factors have to be negative, the other has to be positive, because that's the only way you can get a negative 8. So I could put a 4, I could put a 2 here, but I would just have to test and see if it's going to work. So if I say 3x multiplied by 2, that's going to give you a 6x, and x multiplied by 4, that's going to give you a 4x. And these two, remember, one of it has to have a minus. This is definitely not going to give you 10. So instead of putting it as 4 and 2, I'm going to put it as 2 and 4. So look at what we get. 3x times 4, that is 12x. And then x times 2, that is 2x. Now think about it. You have 12x and you have 2x. But in the middle, we need to have a negative 10x. So how can we form negative 10x knowing that one of this has to be negative, one has to be positive? Well, if you said negative 12x plus 2x, then that would give you a negative 10x, and that is the middle term. So how you know what signs your factors should get? Because the negative is in front of the 12x, how did we form 12x? We formed it by saying 3x times 4x. So for this to be negative, the negative must have been by the 4. So that is 3x times negative 4, which gives you negative 12x. And then the positive would be here. And so these would be your factors. So if you want to learn how to use this method to factorize trinomials, you can check out this video on my channel. So if you don't want to use the quadratic and you feel that it is worth losing 1 mark, then it's okay. You would still get, it will just be 1 mark lost there. So your factors are, you take the factors like this. These are your 2 factors. So the factors are 3x plus 2 and x minus 4, and that is equal to 0. And now we just have to solve for x. So solving for x, we're just going to say 3x plus 2 is equal to 0, or x minus 4 is equal to 0. 3x is equal to, take the 2 over, it becomes a negative 2. Divide both sides of the equation by 3. X is equal to negative 2 over 3. Or we have x is equal to, take the negative 4 over 4. Okay, so remember, we're just trying to find the turning points of L and M. Right now, we have the x values of their turning points. We need the full coordinates, so we need to get the y values as well. So to get the y value of this x value, you will not substitute it into this formula. This formula is for your gradient. This is the gradient of that cubic function. You're going to take this and substitute it into the original formula so you can get the y value belonging to this x value. So just substitute negative 2 into this. So I'm just going to say f of negative 2, and I'm not going to write it down. I'm just going to substitute it on the calculator. And I'm not really going to write down how I substituted, because if I got the y value, it must mean that I did substitute. So I don't think you need to really show that. Okay, so we get 400 over 27. It's best to leave it as a fraction rather than a decimal, because if you leave it as a decimal, it's going to be rounded off. So 400 over 27, that's the first one. Then you have to get the y value of this 4. So f of 4 in place of x, also just substitute 4. And when we substitute 4, we get negative 36. So negative 36. Okay, so let's just see which one belongs to which one, because we have the coordinates now. We have the coordinate negative 2 over 3 and 400 over 27. And we also have the other one, which is 4 and negative 36 now. Okay, so we have the x and the y coordinates. But let's just see what they belong to. So because we had negative 2 over 3, negative 2 over 3 must be the L, because these are stationary points we're referring to. This must be the one for the L, and then that must be the M. So this one takes L and that one takes M. Okay, so there we go. Okay, so that is a total of 5 marks. But if you do, of course, skip the factorizing of that, you would get 4 marks there. Okay, now moving on to 8.3. So 8.3, we have to determine the equation of G. Okay, so let's go back to the graph and see what we have from the graph of G. So as you can see, the graph of G, we have this point A, we have the point B. If you keep moving, you see we have the point C. So since we have 2 points on this graph, we can determine its equation. So we have B as 2 and negative 16, C as 6 and 0. So let's put down those points. Okay, and I like to put the points under each other because it's easier to just find the gradient like this. So we first have to find the gradient so that we can find the C as well. So M is equal to y2 minus y1 over x2 minus x1. And so this will be equal to our y2. We can just go ahead and say, even if you said the top minus the bottom, it will still work out. You just have to be consistent as well with the x. You must also say top minus bottom. So I'm just going to say negative 16 minus 0 and then 2 minus 6. So over 2 minus 6. And we're going to get a negative 16 over a negative 4. So the gradient is positive 4. Okay, so now we have the gradient. We just have to find the equation of the line. There are 2 equations you can use. You can use the y is equal to mx plus c, but I like to use this equation, y minus y1 is equal to m bracket x minus x1, because I feel like it's quicker. I don't have to first find c, then substitute c back in. So it still works like this one. You just have to find the gradient, put the gradient in, and you need to substitute 1 point. So I'm going to choose the point C, and if we substitute this, we're going to have, but you just need to know that we are substituting it like this. Your x1, that's going to be your 6, and your y1, that's going to be your 0. Okay, the y and the x, those ones are just going to be like your y and your x here. So we're going to have y minus our y1 is the 0 is equal to our gradient is 4, and then open bracket x minus our x1 is 6. And even if you use this, you would still get the same thing. So this is just y, because y minus 0 is still y, is equal to, and we multiply in, that's 4x, and then 4 times negative 6 is negative 24. So this is the equation of g. So I can write it as g of x is equal to, because they didn't really say write it in any way, they just want the equation of g. So it's equal to 4x minus 24. Okay, moving on to the next question. Okay, now we are on 8.4, and 8.4 says, if it is given that the coordinates of A are x and negative 36, determine the length of AM. Okay, so let's go ahead and see that A. So the coordinates of A, they're saying that is x and negative 36. We have to determine the length of A till M. Okay, what were the coordinates of M? We found that already. The coordinates of M was 4 and negative 36. So 4 and negative 36. So if you look at that coordinate and we look at the fact that this one is x and negative 36, notice that they have the same y value. So this y value of here, negative 36, they have the exact same y value. Think about it like this. Look at your x-axis. Your x-axis, every point that lies on the x-axis is an x-intercept. And so they all have the same y value but different x values, meaning they all lie on a perfectly horizontal line. So I'm just saying, if this point over here was something like 2 or 1, and I know that this one is 6, to calculate the distance from here to here, I will just have to calculate and say 6 minus 1, because it's like going from 1 and going 2, 3, 4, 5, 6. I'm counting all the way to 6, and I'll find out, okay, from here to here is actually 5 units. That's how we'll calculate the length of a horizontal line. This line is a horizontal line because they have the same y value. So to calculate its length, we just need to know what is the x value belonging to A, and if we also know, we know this one, the x value belonging to M, and if we take this, it's always the bigger one minus the smaller one, like x2 minus x1. So if we take this and we subtract it by the x value over here, we will find the distance of that line. Again, it's just like saying I have this x value over here, and I also have this x value over here. If I want to find out what the length of that is, we're really just calculating, like counting on all the way to that point over there. So we just have to say this x value minus that x value. But the thing is that we do not have this x value of A. So we need to find that x value of A. Luckily, the A is on the cubic function, but it's also on the straight line. It's a point of intersection, one of the points of intersection of the cubic function and the straight line. So if we substitute, we know the y value of it. If we substitute that y value into the straight line's equation, we will find its x value, and then we'll be able to find the distance of the line. So let's go ahead and do that. We have the equation of g of x, and we're going to substitute that into the y value. Okay, so that's why the thing with functions and in maths in general, the previous question usually has a lot to do with the next question. So this is the g of x, but in place of g of x, in place of y, I'm going to say negative 36. And that is equal to, and we'll say 4x minus 24. So because the 4x is positive, I'm just going to take the negative 24 over, and that becomes positive now. So it's positive 24 minus the 36 is equal to 4x. Okay, so if you say 24 minus 36, we get negative 12. Negative 12 is equal to 4x. Divide both sides by 4, therefore x would be equal to negative 3. Okay, so we have the x value now. Okay, now that we have the x value, let's go ahead and put it in here. So a is actually negative 3 and negative 36. And to find the distance of this horizontal line, we know this is 4. That's the x value belonging to M. And we know the x value belonging to A is negative 3. So we can just say the 4 minus the negative 3. You could have also just calculated it like this. You could have said, if you're looking at the distance from the origin to negative 3, that's just 3 units. And if you're looking at the distance from the origin to the 4, that's just 4 units. So 3 units plus 4 units is 7 units. Okay, so that's how we find AM. So we can go ahead and say that AM is equal to the 4 minus negative 3, which is really just 4, plus 3, which is equal to 7 units. So that is the answer of the length of AM, because it's a horizontal line. Okay, moving on to the next question. And then 8.5.1, we have for which value or values of x is the graph of f increasing. So when you want to check if something is increasing or decreasing, you have to read it from left to right. For example, if we have this line, to determine whether it's increasing or decreasing, if you look at it from the left-hand side to the right-hand side, what is it doing? Notice that moving from left to right, it is moving up. So this line is increasing. And if you looked at this line, you also have to read it from the left to right, like you read a book. So you're going to look at it and see from left to right, it is decreasing. Now, this works the same with curves. If we looked at a cubic function and we're trying to see what is it doing at certain points, notice what is happening over here. Let's actually talk about first where it is not increasing or decreasing. This happens at the stationary points. At this point, the function is neither increasing nor decreasing. That's why the gradient at this point is 0. So let's read this from left to right. Over here in this part, and let me highlight this part of the graph, what is this part of the graph doing? Reading from left to right, this part is increasing. And then here, it stops increasing or decreasing. It just stays still. It stays stationary. Then we see that over here, it starts to decrease. And then here, it stops increasing or decreasing. It just stays stationary. Then lastly, here, it starts to increase. Okay, and remember, we just have to determine the values of x for which it does this. So let's look at our graph that we have, the cubic function, and see how we can find this. But also just take note that the stationary points are a very important point to determine where it's increasing and decreasing. So we'll put that down as well. So this is our graph. This is one of the stationary points we have. And we also have the stationary point of L. And let me just put that point down. That was the negative 2 over 3 and the 400 over 27. I think that was it. Okay, so yes, those are the stationary points. So they want to know where this graph is increasing. This graph is going to be increasing when we look at it from left to right. Over here, it is increasing. Then it stops increasing or decreasing. Then over here, it's decreasing. And then here, we have it increasing again. So now we just have to determine the values of x for which these that belong to these parts of the graph. And this is why I say the stationary points are going to be very important here. So if we're looking at this, let's look at what the x value of the stationary point is over here. The x value belonging to this stationary point is the negative 2 over 3. You see that the graph is increasing all the way here on these highlighted in blue parts. So look at the x values that belong to it. Its values here and here and here. And you have to compare that. You have to compare these values with this negative 2 over 3. So these are values that are what than negative 2 over 3. These are values that are less than negative 2 over 3. So one of the places where it's increasing is where x is less than negative 2 over 3. Remember, you cannot say or equal to negative 2 over 3, because at negative 2 over 3 is a stationary point. There it is neither increasing nor decreasing. So that's the first one. Then we can also look at the other part of the graph. So first mark the stationary point. The stationary point is at 4, that is the x value. Then we're going to mark all the places that are highlighted. We're going to line those places up to the x-axis. So that is over here and here, and it keeps going. And now compare these x values that we have over here to 4. These are values that are what than 4? These are values that are greater than 4. So this is where x is greater than 4. So those will be the two solutions for this question where it's increasing. So we're going to say where x is less than negative 2 over 3, and it also happens where x is greater than 4. Okay, so this can be where x is less than negative 2 over 3, or where x is greater than 4. And then the last question. In question 8 is, for which value or values of x is the graph of f concave down? Okay, so when we talk about concavity or concavity, this is just basically how curved the graph is. When we have a parabola that looks like this, we call this a concave up parabola. We say it's concave up. When you have a parabola that looks like that, you say that that is concave down. So we also have the same type of patterns in the cubic function as well. If your cubic function looks like this, so look at the part that is concave down. It would be here. That part is curved down. And then the part that is concave up would be here. But now we need to know, how do we actually answer them in terms of x? To answer them in terms of x, you need the point of inflection, because the point of inflection is where this cubic function will change its concavity. So that's where it changes from concave down to concave up. So first thing you need to do, you need to find that point of inflection, so we can actually tell them, okay, we have to answer them in terms of x. So we need to know what the x value of the point of inflection is. So to find the x value of the point of inflection, you have to get the second derivative of the function and make it equal to 0. So the good thing is we have the first derivative. So let's take the first derivative. So we have the first derivative as this, and we can now derive it again to get the second derivative. So f double prime of x is equal to 3 times 2, which is 6, and we have x. 2 minus 1 is just 1. We can leave it like that. Then minus 10. Okay, then we have is equal to 0. So we're equating the second derivative with 0, and we have 6x minus 10. Because the 10 is negative, I'll take it over. So 10 is equal to 6x. And then we can divide both sides of the equation by 6. And therefore, x is equal to, notice 2 is common in both. So 10 divided by 2 is 5. 6 divided by 2 is 3. So your x value of the point of inflection is 5 over 3. Okay, now that we know that, we can go back and look at the graph so that we can find this. So let me get rid of all of this. Okay, so wherever the point of inflection is, the x value is 5 over 3. So let's say it was here. I know the x value is 5 over 3. They want to know where it is concave down. It's curved down here. So let's highlight that. It's curved down all the way here. And now let's mark these coordinates. Let's group these coordinates to the x-axis and see the relationship between those coordinates, those x values, and this 5 over 3. So since the graph is marked over here, I'm saying that I have a point here. If I line it up to the x-axis, I have this. If I line this point to the x-axis, it's over here. Look at the x value here. Keep lining it down. And now we have to see what is the relationship between these x values that we keep getting for the highlighted parts of the graph and 5 over 3. These are values that are what than 5 over 3? These are values that are smaller than 5 over 3. They're moving to the left. So this is where x is less than 5 over 3. That would be your answer, where x is less than 5 over 3. That would be the values of x for which your graph will be concave down. So we just conclude this is where x is less than 5 over 3. And that's the end of question 8. So now we move on to the last question in this video, question 9. Okay, so question 9 says, in the figure below, triangle ABE, so this triangle ABE has a base of x meters. The base and the perpendicular height of the triangle add up to 10 meters. Okay, that is a very important point. So the base, which they called x, and the height add up to 10 meters. Okay, then they say the triangle is mounted on a rectangle BCDE, which has a perimeter of 32 meters. Okay, so we have two shapes here. 9.1, show that the area of the figure ABCDE, so the entire figure, is equal to all of this, and it's in meters squared because it's area. Okay, so with this, we have to construct some equations first of all. Let's deal with the shapes separately. Since they spoke about, we can see that there's two shapes here, a triangle and a rectangle. So I'm going to make two columns for the triangle and the rectangle. Let's figure out what's going on here. Okay, so let's see what they say about each of these shapes. So first of all, we're actually told something about the triangle. The base is x meters. And then they say that the base and the perpendicular height, so x and h, they add up to 10 meters. So that means x plus h is equal to 10 meters. That's the equation that we have here. So remember, we have to find the area of this whole shape. So to find the area of the triangle, the area of a triangle is equal to a half times the base times the height. So we're going to use this formula. So a half times the base times the height, and we know, okay, so we have a half times, we know the base is x and the height is h, so times x times h. Now the thing about this is, if you look at the final answer we should have, notice that it does not have any h in it. So it means we need to create an equation for h using the information they gave us about the triangle. So you need to make h the subject here. So making h the subject, we leave h on this side. We're going to take the x over. So this is equal to, we still have the 10, then minus x. So a new equation of h is 10 minus x. So we'll put this in place of h. But because we have a half times x, I'm just going to multiply those. A half times x is like saying it's the numerator of 1 times the x, which is x over 2. Then multiply by h. Because this is two terms, I'm just going to put it in brackets and say 10 minus x in place of h. Then we can multiply this in. So multiplying the x over 2 in, we're going to get 10x over 2. And then the x over 2 multiplied by negative x is going to give us a negative x squared over 2. And this can be simplified further. So we can leave it as 10 divided by 2 is 5. So that's 5x. And then this, we can write it as, just so that we have a number. In front of the x squared is an invisible 1. So you can write this as minus a half x squared. Okay, so that is the area of the triangle. Okay, now let's go ahead and find the area of the rectangle. So the rectangle, let's see what they told us about it. First of all, because this triangle is being mounted onto this rectangle, notice that the base of the triangle and the length of the rectangle are exactly the same. They're both x. But also remember, because this is a rectangle, it means the opposite sides are equal. So if this is x, we can also call the opposite side x. Now, to make this easy, we can also just call this something else. So I can call BC, you can call it y. So we can say we're going to let BC, but I'm also just going to state that I made CD equal to x. So CD is also equal to x. And now I'm going to also just say, I'm going to let this BC be equal to y. Okay, so if this is y, because it's a rectangle, it would mean that ED is also y. Then there was something else they told us about the perimeter of the rectangle. They said that BCD is a rectangle which has a perimeter of 32 meters. They told us the perimeter of this rectangle. To find the perimeter of a rectangle or any shape, you really just add all the sides together. So if we added all these sides together, that means we're just saying it's the side BE, which is x. So I'm saying that x, and then it's the side that, which is plus y, then again plus another x, plus the y. That is the perimeter, and we're going to make that equal to 32, since that is the perimeter. Okay, so again, you don't have any y in this equation. We just called one of the sides y. So we're going to just make y the subject. So if we have x plus x, that gives you 2x. Y plus y, that gives you positive 2y, is equal to 32. And this is all in meters. So we can make the 2y the subject by making this 32, and then we take the 2x over and becomes the negative 2x. And then to make y the subject, we can divide both sides of the equation by 2. And then we have that y is equal to 32 divided by 2, 16. Negative 2x divided by 2 is negative x. Okay, so that's what we have as y. That's what we have as this over here. That is the 16 minus x now. Okay, so to find the area of this shape, it's a rectangle. So to find the area of a rectangle, it is just the length multiplied by the breadth. So the length of this is x. The breadth of this is y, which is really just 16 minus x. So we're going to say the area of BCDE, that is equal to our length multiplied by our breadth, so which is just x multiplied by 16 minus x. So you can write it like this: x multiplied by 16 minus x, since 16 minus x has two terms. Then if we expand this, we're going to get a 16x and then a negative x squared as the area of the shape. Okay, so now we have the areas of these two shapes separately. So to find the area of the entire shape, we would just add the areas of the two shapes together. So the area of ABCDE is going to be the area of the triangle, which is this. So that is the 5x minus a half x squared plus this one, which is 16x minus x squared. And of course, I don't need brackets because we're adding, not subtracting. If you're subtracting, you put brackets because it will definitely change the signs. Okay, so let's put our like terms together. The x and the x are like terms. So positive 5 plus 16x, that is a 21x. And then we have the negative a half x minus x. So you can put that on the calculator as negative a half minus 1, which will give you a negative 3 over 2x squared. Okay, and that's what we have as the area of this. And if you compare to their answer, they clearly just put this one first, the one with the x squared first. So we can also just write it in that form. We can go ahead and say this is therefore equal to negative 3 over 2x squared, and the 21x is positive, so plus 21x. And of course it's area, so it is in meters squared. All of this is in meters squared. Okay, so that's the first question, 9.1, and it was for 5 marks. The next question, we move on to 9.2. So the next question, 9.2, they say determine the value of x for which A, B, C, D, E has a maximum area. So they only want the value of x. Okay, so just the value of x, not the actual maximum area. The value of x for which it has a maximum area. Remember, if you look at the equation for the area of A, B, C, D, E, just look at the kind of graph it forms. It has an x squared and an x. So it's going to form a parabola. But notice the coefficient of x squared is negative. So it's going to form a concave down parabola. And what they want you to do is to find the x value belonging to this maximum value. Notice the maximum value of this parabola. It will always be the turning point because that is the highest value that this parabola is going to reach. That is your turning point. And so to find that, they don't want you to actually find the maximum value. They just want the x value that belongs to that maximum value. So I don't know what it is yet, but if we were finding it and let's say it was here, this is your x-axis. This would be the x value belonging to it. then we would still be able to find the y value, but we only have to concentrate on the x value right now. Okay, because this is speaking about a maximum, a turning point. At the turning point, your gradient is equal to 0 because it's a stationary point. It's neither increasing nor decreasing. So we're going to take the equation of this, the area of this, and we're going to find the gradient by deriving this and then setting it equal to 0, because that way you're making the gradient equal to 0. So because it's the area, I'm just going to call the equation a of x is equal to, and let me just rewrite the equation. And now we're going to derive this. So a prime of x is equal to, and we're saying it's the negative 3 over 2 multiplied by 2. So negative 3 over 2 multiplied by 2, the 2's would cancel and you're left with negative 3x, and then 2 minus 1 is 1. Of course, you can do this on the calculator as well. And then we have plus 21, and that x would fall away. Okay, so this is the derivative. This is the gradient of this function at any point. But we specifically want where the gradient is equal to 0, because the gradient is only equal to 0 at the turning point, which is the maximum value. 0 is equal to negative 3x plus 21. Then we can take the negative 3x over, and that becomes a 3x is equal to 21. Divide both sides by 3. X is equal to 21 divided by 3 is 7. So remember, they only asked for you to determine the x value for which that will have a maximum area. That is the x value for which it will have a maximum area, because this graph was concave down. Okay, and then moving on to the last question in question 9. And now 9.3, they say, hence determine the maximum area of that shape A, B, C, D, E. So here we only found the x value belonging to that maximum area. The maximum area itself is the y value, okay, belonging to this x value. So we can take this x value and substitute it into the original function, because we just want the y value. The y value will tell you the area, okay, belonging to that x value. So we're going to take this and substitute it into the original, not the derived equation. So here is the equation, and we're going to substitute in place of x, we're substituting 7. Okay, and we get, so a of 7 is equal to 147 over 2, but because it's area, you can go ahead and just put it in decimal. So in decimal form, it is just 73.3, and it is area, so you can say meters squared. Okay, likewise, the 7 is actually 7 meters. That's the x value, because x actually was speaking about one of the dimensions, which was the base of the triangle and also the length of the rectangle. So that is, okay, so we're on question 8 now, and question 8 says, determine f prime of x from first principles if it is given that f of x is equal to negative x squared. Okay, so from first principles, you know that the formula for first principles is f prime of x is equal to, when we're deriving, it is the limit as h approaches 0, and then we have f of x plus h minus f of x over h. And so because this is the formula, the best thing to do is to start with this f of x plus h. Since we already have f of x, we already have this. Let's start with the f of x plus h and find out what that is going to be equal to. Since we already have f of x, let's just start with the f of x plus h and find out what that is going to be equal to. Okay, so I'm moving this to the side, and we're just going to find the f of x plus h. So when we see this, it just really means that because we are now saying f of x plus h, wherever we see x, let's just replace that with x plus h. So first we have a negative, and then we have x. In place of x, we're going to put x plus h, but like this, x plus h. And then we have a squared, so we put squared there. And so this is equal to, we still have the minus behind, but we need to multiply this. We need to square this, basically, what is inside the bracket. So you can do this basically by squaring the first term. That will be x squared. Then you're going to multiply the first term with the second term, which will give you xh. Then you take that and multiply that by 2. So that gives you positive 2xh. Then to get the last term, you just square the last term. So h squared will just give you positive h squared. So this is what we have. Then we just multiply this negative into this bracket. So we're going to have negative x squared minus 2xh and then minus h squared. And that's what f of x plus h gives us. Okay, now we can actually find the derivative of this using this formula that we have. Remember, all the formulas are in the formula sheet. So this is that f prime of x is equal to the limit as h approaches 0, and f of x plus h is this negative x squared minus 2xh minus h squared minus, and then we have to minus that by f of x. Now f of x is this negative x squared. So we're saying minus a negative x squared. No? So we're saying minus negative x squared. So as you see, we need brackets here because this is negative. So we need brackets. We can't just leave two signs there like that. And so this is now over h. Then it's equal to the limit as h approaches 0, and we have negative x squared minus 2xh. So you will see that from this, every time when we're subtracting by f of x, this negative is going to multiply to whatever f of x is. So it's always going to be, you always have to take what f of x is and multiply by negative. So in that case, that will now become positive x squared. So this is something that you can just be doing so that you can avoid taking long steps. Because if you take long steps, it really sometimes increases your chances of making mistakes here and there. So we'll say over h, and now this is equal to the limit as h approaches 0. And now a second thing you should also realize is because we're saying minus f of x, the only thing that will cancel across is whatever has the inverse sign, okay, the inverse operation of whatever f of x was. So we have positive x squared, it will cancel with a negative x squared in this. So there it is. That will cancel with that. I'm only saying this so that you don't go ahead and start searching what's going to cancel. Whatever will cancel would be whatever f of x was. And so we're just going to have negative 2xh minus h squared over h. Then, in order to get rid of this denominator of h, we're going to take out a common factor of h on the numerator. So this is still equal to the limit as h approaches 0. And then we have h out as a common factor. So we're looking at h and we're saying what do we multiply to h to get back to this? Or you could say this divided by h. So the h's would be gone and you'll be left with negative 2x. Again, negative h squared divided by h. One of the h will be gone here. This h is gone. You're left with negative h only over h. And then they cancel. So now we have this is equal to the, I don't really want to write the limit as h approaches 0. So what I'm going to do is substitute in place of h 0. So we say negative 2x minus h is now 0. This is f prime of x. And f prime of x finally is just equal to negative 2x. And if we scroll up, just also notice what you can do to make sure that this answer is right. Derive this from the rule of derivatives. So if it was f prime of x, you would just say the negative times the 2, which is negative 2. And then we have x, 2 minus 1 is 1, but we don't have to write that 1. So you see that that works out. You can always just do that to make sure that you did get the correct answer. Okay, moving on to the next question. 8.2 we have, so determine 8.2.1 f prime of x if it is given that f of x is equal to this. So it's only for 2 marks, so we need to do this using the rule of differentiation. Okay, so using the rules of differentiation, we're saying we have to check if it's ready to be derived. So everything looks fine here, nothing, no x's on the denominator, everything is fine. So we can just go ahead and start by saying f prime of x is equal to, so coefficient times exponents, 4 times 3 is 12. Then we have x to the power of 3, and we have to subtract 1 from that, which will give you 2. Then we have the negative 5 times 2, which is negative 10. And we have x to the power of 2, and we need to subtract 1 from that again, and that will just give you 1. But remember, you don't have to write that 1. There's an invisible 1 there. So that is what we have done, and you see that is 2 marks. So that is a nice 2 marks that you can get there. Moving on to the next question. Okay, the next and the last question in question 8 is 8.2.2. We have to determine dx, and we have negative 6 cube root of x plus 2 over x to the power of 4. So let's spot the problems here. First of all, we have a surd. We need to change that so that the exponent can be a rational exponent. And then we also have a case that the denominator is x. So the denominator should not be x. So let's start off with working with that top. Because we're not deriving yet, we're just preparing this to be derived. We have to keep writing dx. And now we're going to have negative 6. And let's solve that x. You have a cube root of x. Now, on top of the x, there's a natural exponent of 1. If you want to write this so that it's not a surd anymore, we're going to keep the base, and you're going to say the inside exponent over the outside exponent. So the inside exponent is the 1, the outside exponent is the 3. And that's how it can be written. So that is just x to the power of 1 over 3. Okay, so that's fine now. Then plus 2. And then, of course, over the x to the power of 4. So this is our next problem now. So how do we resolve that? Well, in this case, this is not a case where we can nicely just take that to the numerator. We can't really do that right now. It won't really work so well because we have 2 terms on the numerator. So what we can do is split this fraction. So if I had a fraction x plus 1 all over 2, if I wanted to split this fraction, I could split it like this. It would be x over 2 plus 1 over 2. Because when the denominators are the same and you're adding or subtracting, you need to just add the numerators and keep the denominator the same, like that. So that's how we'll split that. We can just go ahead and say this is equal to dx. And we open this and we have negative 6x to the power of 1 over 3 over x to the power of 4. And then we have a plus here. So this is being added by 2 over x to the power of 4. Okay, now that we have that, we can simplify. So you see this 2, they can actually simplify. We have the bases being the same and they're dividing. So we need to subtract the exponents. So we have dx, and then we have negative 6. And when the exponents are subtracted, we're going to have x is going to stay on top to the power of 1 over 3 minus 4. So what's 1 over 3 minus 4? And that gives us negative 11 over 3. And then we're going to say plus, and now in this case, you see you have a denominator which has an x. That should not be. This needs to go to the top. So since we're taking this and we're putting it on top, the consequence for that is that the exponent is going to become negative. So we're just going to have the plus 2, and now we have x, but to the power of a negative 4. Okay, and now everything seems fine. Everything can actually be derived in this form. So now that we're deriving, we're not going to write dx anymore. It's going to be equal to, we're going to say the negative 6 multiplied by negative 11 over 3. So what's negative 6 times negative 11 over 3? And that is equal to 22. So you can't just use a calculator. And we have x to the power of negative 11 over 3. And you have to say minus 1. So what's negative 11 over 3 minus 1? And that is equal to negative 14 over 3. Then we're going to say the coefficient times the exponent. So 2 times negative 4 is negative 8. We have x to the power of the negative 4. Again, you must say minus 1 from the exponent. And that will give us a negative 5. Okay, so this is it derived. The last thing you need to do is write this expression or this function in a way that the exponents are positive. So currently the exponents are negative, but these x's, the base carrying the exponents, they are on the numerator. It's kind of like this 22 x to the power of this exponent over 1. So what we're going to do is drag this to the denominator. And so we're going to have 22 over x, and now it is going to be positive to the power of 14 over 3. And then we have a minus do the same thing here. We have 8, and we're going to drag that to the denominator over x to the power of, it becomes a positive 5. And that is our derived form. Okay, so that is the last question for question 8. And now we move on to question 9. And now on question 9. And question 9 says, sketch below is the graph of f of x, which is equal to x cubed plus ax squared plus bx plus c. The x-intercepts of f are at 3 and 0 and m. Okay, so these are the x-intercepts of this. And then they also say where m lies on the negative x-axis. Okay, so they must be saying that for an important reason. Then they say that k, which is 0 and negative 3, that is the y-intercept of f. And then they say that m and n are the turning points of f. Okay, so this is one of those graphs that is sharing an x-intercept and a turning point. So they want us to show that the equation of f is given by this. Okay, now looking at this, for us to be able to, let's just see what we have. First of all, we have a y-intercept, 0 and negative 3, and that is the value of c. So we know that c is actually equal to negative 3, that y value, because it's the y-intercept, negative 3. So if we fill in what we have so long, we would just have f of x is equal to the x cubed, then we have plus ax squared plus bx, ax squared plus bx, and then we'll just have minus 3. Okay, now the problem with this equation is there are two things missing. We have a and we have b missing. In order to be able to find the equation of this, just using this, they would have to give us 2 more pieces of information. They only gave us this extra. They told us that this is 3 and 0. That's all. If you just substitute this 1 point in this, it's not going to help you to find the 2 missing things. You need 2 pieces of information, or 2 points at least. If it was the case that they gave us maybe this point, then it would be more than enough to find it. Because this point is special. It's a turning point. You can use it as a point. We would be able to actually substitute it as a point. That's the first way you could use it. The second way we could have used it is as the derivative. We could have derived this function and said that at this point the gradient is equal to 0. So we derive it and set that derivative equal to 0. But notice they didn't give us that. They only gave us this point. So I'm saying that this is not enough this is not enough to find this. So we need another method to find that. So let's look at the fact that they gave us a cubic function with 2 x-intercepts. One being a turning point and an x-intercept, the other is just a turning point. So the formula of this graph can be written as y is equal to x minus x1. And because this one, the one on the left is the smaller one, I'm going to use it as this one. Okay, so this x value is this x value here. Now, because it is a turning point and an x-intercept, on top of this we would say squared. Then multiply by x minus x2. Okay, and that would be the x2. So x1 is whatever the x-coordinate of m is. And let's just call that something. Let's call it p. So I'm saying x1 is p. I'm going to call it p. And x2 would be the x-coordinate of this x-intercept, which is 3. Okay, so we can substitute that. So x2 is 3. Let's go ahead and substitute it into this. So we have so long, because it's f of x, I'll just call it f of x is equal to x minus p all squared. And then we have x minus 3. Okay, so here we can just go ahead and try and find the value of p. So if we find the value of p, we'll be able to put it back into this formula and just simplify this, and it will basically be simplified to get to this form. So how do we find p? All we need is at least 1 point. So let's just substitute 1 point into this equation and we'll be able to find p. The point that we can substitute is k, because this is a point we have not even used yet. We have 0 and negative 3. So k, which is 0 and negative 3. So I'm going to put this in as my x value and this as my y value. Okay, so the y is f of x. That is the negative 3. It is equal to, so we're going to have, in place of x, we're just going to put in the 0, okay, because that's the x value. So 0 minus p, we don't know what p is yet, p all squared, then multiply by, again we have an x, so in place of that we put 0 minus 3. Okay, so you see only numbers and p will be able to solve for p here. We have negative 3 is equal to 0 minus p is really just negative p all squared, and 0 minus 3 is negative 3. So now I have negative 3 is equal to p all squared is p squared being multiplied by negative 3. So here we'll just have negative 3 p squared and negative 3 on this side. We have to solve for p, so divide both sides by negative 3, and so it means that p squared so long is equal to 1. Then we're going to have to solve for p. You see, this is an equation. To solve for p, we need to get rid of the square, so we'll square root both sides. But you need to remember this. This is an equation, so we're going to have to say plus minus here. The reason why is because not only the positive would work, the negative would work as well. We're saying something squared is equal to 1. Well, 1 squared gives you 1, but negative 1 squared also gives you 1. So always remember you need to add that plus minus. So p is either equal to positive or negative 1. And that's probably why, because remember p is this, that's probably why they mentioned this. They mentioned that m lies on the negative x-axis. So because it lies on the negative x-axis, it's not going to be the positive 1, it's the negative 1. So it means that p is equal to negative 1. Okay, now that we have the value of p, we can go ahead and substitute it into our equation. And our equation is this f of x. I'm just going to copy and paste this. And then we have f of x is equal to, we have x minus, and p is now negative 1. So we say negative 1. You can put that in bracket. All squared, and then bracket x minus 3. Okay, so this is really square brackets, but it doesn't really matter. Then we have f of x is equal to, we have the x, and then the negative multiplies with that negative 1. We're giving it a positive 1, all squared, bracket x minus 3. So you see, our equation is complete. All we have to do is actually simplify it so that it can be in this form. Okay, so we're just going to say f of x is equal to, let's work with this. So because of that, I'll just put this in front, this x minus 3. And now we're going to work on this x plus 1 all squared. Because it's being squared, you can simplify it the quick way. Instead of writing x plus 1, bracket x plus 1, that takes long. All you can do is, you're going to take the first term and square it. That will be x squared. Then you're going to say, to get the middle term, we'll say the first term times the second term. So x times 1 is just x. Then you're going to take that and times it by 2. Okay, and that will be positive 2x. Then lastly, you take the last term and you square it, and that will still give you a positive 1. So you can do it the normal way. It will take longer. I try to take shorter routes because as a human being, you will make mistakes here and there. You're capable of making little mistakes. So I try to avoid those little mistakes by using quicker steps. Okay, so now we can go ahead and just simplify this. We're going to multiply this binomial by this trinomial, and we'll basically do that like this. So we're going to take the first term, x, and multiply it by x squared, and that is equal to x to the power of 3. Then again, the x will multiply to the positive 2x, and that will give you a positive 2x squared. Then the x will multiply to the positive 1 and give you a positive x. So we're done with the x now. You see, each term just needs to multiply by every term here. Then we're going to have the negative 3 being multiplied by the x squared, and that will give you a negative 3x squared. Then the negative 3 multiplied by the positive 2x, and that will give you a negative 6x. And the negative 3 lastly multiplied by the 1 will just give you a negative 3. So finally, f of x is equal to x cubed. And then we have this positive 2x minus 3x squared, so they both x squared, so it's going to be a negative x squared. Then we have the positive x minus 6x, which is a negative 5x, and the constant negative 3. There we go. Okay, so that's what we would need to do in that case. So now you see how the thought process goes. You see why the other method would not have worked and when you should think about using this method. Okay, so that is 9.1. Moving on to the next question. Then 9.2 says calculate the coordinates of n. So to find the coordinates of n is the other turning point. Okay, so to find that, we already know this one. This one, we got m, which was the -1 and 0, because it's an x-intercept. And so we just need to find n. So finding the turning point, you would just need the function. You need this f of x, and we're going to derive this because we're trying to really just find the gradient of this function. So when we derive this, this is the gradient of the function. We're going to say the invisible 1 times the 3, and then we have x to the power of 3 minus 1, which is 2. And then the invisible -1 times the 2, that is going to be a -2. Then we have x, 2 minus 1, which is 1. And we don't have to write the 1. Then minus 5, and of course the x falls away because x to the power of 1 minus 1 is x to the power of 0, which anything to the power of 0 is 1. And so -5 times 1 is just -5. So this is what we have. This equation defines the gradient, okay, of this graph. So we're trying to look for a turning point. At the turning point, the gradient of your curve is equal to 0. So we're going to make the gradient equal to 0. And we're saying it's equal to 3x squared minus 2x minus 5. And this will give us the x coordinates where our gradients are equal to 0, which will really be the x coordinates of our turning points. Okay, so this is something where you can go ahead and use the quadratic formula if you want to. I can't promise that you won't lose 1 mark. You probably will for your factors. You're going to lose 1 mark for your factors. So I'm going to factorize it manually. So I'm going to look at 3x squared and say, what times what gives you 3x squared? That is 3x multiplied by x. And then what times what will give you -5? So that will be 5 and a 1, but one of it needs to be negative. So I think it's in the right position right now so that we can get a -2 in the middle. But when we multiply across, that becomes a 3x. And when we multiply like that, that becomes a 5x. So if you have 3x and you have 5x, which one should be negative for you to get a -2x in the middle? We would make that negative, the 5x, and then this one stays positive. So that would give us a -2x in the middle. That means, how did we create the 5x? We created it by saying x multiplied by 5. So that should get the negative, so that we have, that's how we multiply this, and it became a -5x. Then, of course, the 3 times the 1 will make that positive. So these are our factors. This and that is our factors. So 0 is equal to, we have 3x minus 5, and we have x plus 1. So 3x minus 5 is either equal to 0 or x plus 1 is equal to 0. 3x is equal to 5. Divide both sides by 3. X is equal to 5 over 3. Or it's a case where x is equal to -1 when we take that over. So let's decide which one belongs to n. Remember, this belongs to both stationary points of n and m. We already know m is -1. So this one is the 5 over 3. So that is 5 over 3. Okay, so we have the x value now. Let's find the y value. It is still a point on the graph. So all you're going to have to do, not on this graph, this is the derivative, it's still a point on f. So just take this x value and substitute it into the original equation of f. So we'll say f of 5 over 3, and you're just going to plug that in. And when I plug all of this in, I get f of 5 over 3 being equal to -256 over 27. So just make sure you check carefully that everything was put in properly. So it means that the coordinates of n are 5 over 3 and -256 over 27. Okay, so that is for 5 marks. Moving on to the next question. The next question says, 9.3, for which values of x will f of x be less than 0? So f of x. F of x would stand for the y values of the graph of f. Where will they be less than 0? In other words, where will they be negative? So we're going to use the graph to do that, to find out where they're going to be negative. Okay, remember this is 5 over 3 and, well, that other number. Okay, and that. So where is this graph going to be Negative. Where does it have negative y values? So looking at the y values, these y values here, those are positive. We're looking for where it has negative y values. So where it has negative y values, you see that this would be everywhere down here. We're looking for parts of the graphs that lie down here, so below the x-axis. And the parts of the graph that lie below the x-axis would be all of this over here, this, all the way to here. Not beyond this, because beyond this, these y values are positive. So we just have to now find out what the x values for these points are. And also please note that they said where f of x would just be less than 0, not equal to 0. So why I'm saying that is because of this point of m. At exactly the point of m, the y value of f is equal to 0. So I'm going to try and not include negative 1 itself as a point. Okay, so when we're actually saying what the x values are, let's map this to the x-axis. You see these coordinates? Look at the values that we have. First of all, it's values that are what than, we have this here, negative 1, right? These are values that are what than negative 1. These are values that are less than negative 1. So I can say that x here is less than negative 1, not equal to, just less than it. Then these ones over here, I can also map them out. Map it to the x-axis and you see that these are values that are greater than negative 1. But then look at them here as well. These are values that are less than 3. So this is where x is greater than negative 1, but less than 3. Those would be all these parts of the graph. So that's really our solution. It's that and that. So I'm going to put that down. So this is where x is less than negative 1, or where x is greater than negative 1, but less than 3. And that will be our final answer. This can be simplified further, but I'm sure they will accept this. So if you said something like, if you looked at that and said, okay, that actually basically means that the numbers are, as you can see, if we just look at these numbers, it's actually everything that is less than 3. Because you see, if we keep going, all those x values, they all have, the graph all has y values that would be negative. So it's everything that is less than 3, but you need to say excluding negative 1. So in that case, you could round up everything we said here by saying that x is just less than 3, but, or you don't have to say but, you can put semicolon, x is not equal to negative 1. Because we're saying at negative 1, we cannot include this point, because at this point, f of x is not smaller than 0, f of x is equal to 0. See, it has a y value of 0. So that's another way you could have also concluded that it will still be correct. Okay, so that is just an alternative way of putting that. Then we have 3.1.1 done. Moving on to the next question. Then the next question, 9.3.2, says we have to determine the values of x for which f will be increasing. Okay, let's speak about increasing and decreasing. If we have a line like this, okay, what is this line doing? You have to read graphs moving from the left-hand side to the right-hand side. And if you read it moving from left to right, what is it doing? It is increasing. And when a graph is increasing, it really just means that its gradient is positive or greater than 0. So we want to look for, on this graph, where is this graph increasing? So we can look at this in a cubic function as well. In a cubic function, we have a cubic function like that. And we're looking for places where it's going to increase. Again, we will read the graph from the left to the right. And where it is increasing, if you look at it from left to right, all the way here, it's increasing. Then it does something at the turning point. At the turning point, remember we say that this is the point where the gradient is equal to 0. At the turning point, the graph is neither increasing nor decreasing. It is stationary. So it's standing still. So that's why that's a stationary point. Then when you go past this, the graph starts to decrease. And then it reaches another stationary point. So it doesn't increase or decrease. It just stays still, stays stationary. Then after that, it starts to increase again. So you can see now that two important points would be the x coordinates of your stationary points, and we'll be able to mark where it is increasing, because that's what we need to find. Okay, so let's look at the graph. The graph is going to be increasing here, all the way here it's increasing. Then it decreases here. We don't have to mark that part. We're only looking for increasing. Then it stays stationary, and then it starts to increase again. So what are the x values belonging to this point? So the x values of your turning point is going to be very important here. These values, if you map them up to the x-axis, look at them. Look at that value. Look at that value. Look at what they are. These are values that are less than what number is here. -1 is here. That's the x value here. These are values that are less than -1. So for this part, we can say x is less than -1. Not equal to -1, because at -1, the graph is neither increasing nor decreasing. Then we can do the same thing to this part. We're going to map these to the x-axis. So first of all, the stationary point, the x value of the stationary point is the 5/3. And look at the other parts of the graph that are highlighted. It's these ones, this, and it keeps going. It even goes past 3. So you can't use 3 as a reference. You have to use this stationary point as a reference, because this is where it's neither increasing nor decreasing. What are these x values? They're x values that are what than 5/3. They are x values that are greater than 5/3. And that will be our solution. Now, when we conclude, we're not going to put it as one inequality, because you will notice that they're actually pointing in two complete opposite directions. This one is pointing towards that way, and these ones are pointing towards that way. Okay, they're not related values. So we're just saying that x is less than -1 or x is greater than 5/3. And there we go. So that is just for 2 marks. You don't have to draw this graph. This was just a means of explaining. That would give you your 2 marks. Okay, moving on to the next question. Then we have 9.3.3, which says we have to determine the values of x again, for which f will be concave up. So when we speak about how a graph is concave, when we have a parabola, a smiley face parabola, this is a concave up parabola. This is a concave down parabola. So in a cubic function, we also have 2 different concavity that is also going on there, or concavity. So we have this. That's how a graph looks. The shape is like that. Where it will be concave up would be on this part over here. It's concave up. And where it's concave down would be this part over here. So we have to find out now, if this is the part that is concave up, where exactly does this start? It will start, so where does it change really? It changes after the point of inflection. So in this question, we first have to find that x value. What is the x value of our point of inflection? And so we can say, okay, it is concave up for values that are, as we can see, these values move towards this side. So it's values that will be greater than whatever that x value is. So that's the first thing we need to do. Let's find out the x value of the point of inflection. Now, with what we have on this graph, there's actually 2 ways. You can use the equation of the function, the completed one, and you can get the second derivative of that function and make it equal to 0. Or if you wanted to just get straight to the point, you could just say the second derivative. Where is the second derivative going to be greater than 0? This would be concave up. If you wanted concave down, you just say the second derivative needs to be less than 0. So another way you could have found this is using the x values of your turning points. You see, in between them, exactly halfway between them, that would be the x value of your point of inflection. So if you could find the midpoint of this, okay, really just by saying x1 plus x2 divided by 2 of these x values. So you take the -1 plus 5/3 and divided by 2, and you would find the middle. That would be the x value of the point of inflection. But you can also just do this the easy way by actually just finding this inequality, solving for x in this inequality. Okay, so I'm going to just use the inequality because I feel like it's going to be simpler since we already have the first derivative of this. So we're going to make f prime double prime of x be greater than 0. This would be the values of x for which it would be concave up. Okay, and the derivative of this is this. So when we derive it, it's going to be 6x and then minus 2. That's all we're going to have there. So we're going to have 6x minus 2 is greater than 0. And you just need to solve for x now. So 6x is greater than, and we're taking this negative 2 over. So this is not a quadratic inequality, so there's nothing special here. We just have to solve for x. We need to solve for x by dividing both sides of the equation by 6. And so it means that x just needs to be greater than 2 over 6 is just 1 over 3. That would be the values of x, for which is going to be concave up. And it is for 3 marks, so definitely this method would give you those 3 marks. The other method is quicker, so maybe if it was just like 2 marks or 1 mark, you could have just used the other method instead. Just in the other method, you have to just think a bit. Okay, moving on to the last question in question 9. Okay, so 9.4, the last question in question 9 says, determine the maximum vertical distance. Okay, so maximum vertical distance between the graphs of f and f prime in the interval where x is greater than -1 but less than 0. So we're using two graphs here. We are working with f and f prime. Okay, so a representation of what they're asking for is we have the graph of f. When you derive, okay, this graph, we're going to have f prime. And f prime is going to be from the cubic function. When you derive that, you will get a parabola, just like we have here. You see f prime of x is a parabola. And notice that this parabola is concave up, okay, because the a value is greater than 0. It's positive. So this is a concave up parabola. It will look like this. So this part doesn't really matter. I'm just trying to show you what it looks like. And what they're asking for is the maximum vertical distance between -1 and 0. So they say where x is greater than -1 but less than 0. So we're looking for the maximum vertical distance between here and here. All that just means is we're going to look between these 2 points, right? Looking at what we have in between them, notice that it's the cubic function that is above this graph, the parabola. So actually you would have needed to sketch the parabola a bit just so that you would know what's going on. The cubic function is above the parabola. So when you're calculating the vertical distance, it's really the distance. So we need the y values of it. We don't really have the y values exactly, but what we're going to say is we're saying the graph of f, the cubic function, and we're going to take the graph of f prime, which is this one over here. It's below the graph of f. And we're going to subtract them like that. Because only between not only, but between -1 and 0, you see that the graph of f is above the graph of f prime. So in order to get that distance, okay, that distance between them, you're going to have to say f of x minus f prime of x. And that will give you a general equation for the distance between those two graphs. So that was the whole point of them telling you -1 to 1. It was so that you know which one is above which one. So we have to say this minus that one. So the distance itself, the vertical distance, would be found by saying f of x minus f prime of x. Then after, when we simplify this, we'll find the maximum vertical distance. Okay, so f of x is, of course, the cubic function, which we already have. The cubic function is this. And we're going to subtract this by f prime of x. And the f prime of x is what we have here. F prime of x is this. But remember, in this, we have more than one term. So if we're subtracting by this, we need to put brackets around that. Okay, so let's simplify what we have here. We have x cubed minus x squared minus 5x minus 3. And then this multiplies it. Minus 3x squared plus 2x and then plus 5. Okay, so like terms together, we only have one x cubed, so that is still x cubed. Then we have a negative x squared and a minus 3x squared, which will give you -4x squared. Then we have this minus 5x plus 2x, which will give you a negative 3x. And lastly, negative 3 plus 5, which is like saying 5 minus 3, which is positive 2. Okay, so this is the distance, not the maximum distance yet. Now, using this distance, we can find the maximum vertical distance. And so we're taking this graph and we're going to find out where is it a maximum. We're going to find its maximum value. This graph actually creates a cubic function where the value of a, okay, the coefficient of x cubed is positive. So it looks like this. It looks like a capital letter N basically, just more curved. But if it was a case where a was less than 0, where that coefficient was negative, it would look like a backwards N, just more curved, like that, something like that. Okay. So we're working with this, and this is what we're going to find. We're actually just trying to find the local maximum. So here we have a local minimum, and here we have a local maximum. So however this graph looks, we just want to find the actual maximum vertical distance. We want to find that y value. But in order to find that y value, that maximum, we need to find the x value first, belonging to this. And so you see at this point, we have a turning point. So we're really just trying to find out, you see the distance between those two graphs, they create a new cubic function. And we're just going to find out what exactly the maximum value of that turning point is. Because it's a turning point, you're going to have to derive this, okay? And you have to remember that at the turning point, your gradient is equal to 0. To find the gradient of this distance, this curve, you derive this curve. And so we're going to say d prime is equal to, and I'm deriving it, so it's invisible 1 times 3, which is 3x, and then to the power of 3 minus 1, which gives you just a 2. Then the negative 4 times 2, negative 8x, 2 minus 1, which is 1. We can leave it like that. And minus 3. And of course, that x falls away because of the exponent of 0. And that also just falls away because it's a constant. So this is the gradient of this curve. But now we want specifically where the gradient is equal to 0. So we're making the gradient equal to 0. And this is now 3x squared minus 8x minus 3. So we have to simplify this, factorize this. So I'm going to say 3x multiplied by x is what gives me 3x squared. And what times what gives me 3? That will be a 3 times 1. But remember, this is a negative 3, so one of it needs to be negative. Okay, if I put it like this, it will not give me an 8 because one of it needs to be negative already. This is going to be 3, that's going to be a 3. There's no way 8 is going to come out of that. So I'm going to put it as 1 and 3 instead. And because the 8 is negative in the middle, the one that becomes the bigger number, that should take the negative. So if you say 3 times 3, that will become 9. So this should take the negative. So we can have a negative 9x. And then x times 1, that should be positive. So we can have a positive x, and that will give us negative 8x. So these are our factors. I have a video on factorizing trinomials like this, so you can actually just go ahead and check that out on my channel. You can go to the videos and you will see, well, I will paste a picture of that here so that you'll be able to find that video on my channel. Okay, so we just have 3x plus 1 and we have x minus 3 is equal to 0. So let's solve for x. 3x plus 1 is equal to 0, or x minus 3 equals to 0. 3x is equal to negative 1. Divide both sides by 3. X is equal to negative 1 over 3. Or we have the case where x is equal to, we're taking that over positive 3. Okay, so this is where we have to decide which one is our x value. You see that here we have a maximum, okay, at this x value. And then here we'll have a minimum. So at this x value, notice that this x value is more to the right than this one. So this x value, okay, whatever this is, let's say x2, it's going to be bigger than this x value. So we're going to take the smaller one. The smaller x value would give us the maximum value. Okay, so between these two, which one is the smaller one? It will be this one. Okay, so this is the smaller one, and so I'm taking that. So in actual fact, this y-axis is actually supposed to be like in between these two lines, these two x values. So we have this as our coordinate that we're going to use, the x value. But then we need to find its y value. The only way to find its y value is to take that x value and substitute it into the equation of the cubic function that we have. And that will give you the y value. And this is this equation here. That is the equation for the distance of those two graphs. So I'm saying that the distance, I'm just finding the distance of the maximum. Okay, I can say d maximum, or even if I said d sub negative 1 over 3, because I'm substituting this into this equation, it's going to be the negative 1 over 3 or cubed, and then minus 4x squared, so minus 4 bracket negative 1 over 3 all squared, and then minus 3 bracket negative 1 over 3, and lastly the plus 2. So you can put this onto the calculator, and that would give you the maximum value of that cubic function. And we get 68 over 27 on the calculator. So you can put it as decimals, as a decimal rounded off to 2 decimals will be 2.52 units. Okay, that would be the maximum distance between those two graphs when they're in between these x values. And we have 8.1 saying, determine f prime of x from first principles if f of x is equal to 3x squared plus 2x. Okay, so this is the part of the paper that you can really just score marks. It's 4 marks. So first of all, before even writing that formula down, it's best to start with that f of x plus h so that you already know what that is. So remember, this just means wherever you see x plus h, wherever you see x, sorry, replace that with x plus h. So over here we have 3x squared, so we're going to say 3, and then in place of x is x plus h all squared, then plus 2, in place of x, x plus h. And this will give us 3, and then we still have inside this bracket. Remember how to work this out. Instead of writing the bracket twice, you square the first term, that's x squared, then you take the first term, multiply by the second term, that's xh, and you times that by 2, so that's positive 2xh. Then we have plus h squared, because we squared the last term. Close bracket, we can multiply this in already, so we have plus 2x plus 2h is equal to, then we're also going to FOIL this in as well, so we have 3x squared and plus 6xh, and lastly plus 3h squared, and all of this just follows. Okay, now that we have the f of x plus h, we can go ahead and write the formula. The formula is just that f prime of x is equal to the limit as h tends towards 0, and we have f of x plus h minus f of x all over h. Okay, keep writing that limit of h tending to 0. Then we have the f of x plus h, because that was the f of x plus h. Put all of that in. So we have 3x squared plus 6xh plus 3h squared plus 2x plus 2h. So just be very careful in this one and just try to avoid making mistakes. Then we're going to subtract it by f of x. Now the thing about subtracting it by f of x, and something you can do just so that you don't have to keep rewriting things, instead of just saying minus, then you put brackets and then 3x squared plus 2x, because then you're still going to have to FOIL this in and rewrite all of this again. Something you could have already done is known that this is going to have a minus and then open brackets, meaning this negative is going to multiply to whatever that was and whatever that was, meaning now you just have a negative 3x squared, and again multiply that by a negative, that same negative, negative 2x. So just always multiply those by a negative if you want to avoid putting brackets and foiling in. Okay, then we have over, we have h. And then another thing that you will also notice if you've been working with these the whole time is that these ones, the ones that you're subtracting by, they're the only things that will cancel over here. So that's what you have to search for. I see minus 3x squared, I'm going to cancel 3x squared with that. Then I just have to search for a minus for 2x. It's going to cancel with that one. So there's 2x, it cancels with that. And then everything else is just left. We have is equal to the limit as h approaches 0, and we have 6xh plus 3h squared, then we have plus 2h all over h. And then this is equal to the limit as h approaches 0, and we're going to now have to get rid of or take out a common factor of h so that it can cancel with this h and we do not have this becoming undefined. So we're taking out the h as a common factor and we're opening a bracket. Then we're just going to have, remember, just saying this divided by this, the h's will be gone and you'll just be left with a 6x. And then this second term plus 3h squared divided by h, one of the h's would cancel and you're left with positive 3h. And then the positive 2h divided by the h is gone and you just have a positive 2 all over an h. Then your h's cancel and you are left with this. Now, you don't have to rewrite this lim if you're going to substitute h already. So I'm just going to do that. I'm not going to rewrite this because I'm going to substitute in place of h. So I just have 6x plus 3, and in place of h, we'll put in 0. Then we have plus 2 is equal to 6x, and we have that becoming 0, and we just have a plus 2. So that is the derivative of that function. That is the gradient of that function at any point. Okay, so we have that. Something you can also do just to check that it is correct, you can derive that from the rule. So the rule would say 3 times the 2 would give you 6, and then you have your x. Subtract 1 from your exponent, it would give you a 1. You don't have to write that one. Then you're going to say the positive 2 times the invisible exponent of 1. That gives you a positive 2. Then that invisible exponent of 1 minus 1 just gives you 0. X to the power of 0 is 1. So 1 times the 2 just stays the 2. And that's why it just stays positive 2. So that's another thing you can do just to check that your answer is correct. So we do get the same thing, and so that's fine. Okay, next question. Okay, so 8.2 says determine dy over dx if y is equal to 4 square root of x minus 8 over square root of x plus pi x cubed. Okay, another thing to just look at here, and I think if students looked at this question at first, they would have gotten afraid of the pi. Pi is just a number. That's just something you should remember. Treat it as the number that it is. Okay, so when deriving, before even deriving, you need to prepare your function to be derived. First of all, we know that if you are deriving, you shouldn't have square roots. Okay, so we should not have any square roots. We should also not have anything on the denominator. Move anything that is an x, a variable, to the numerator. So that also needs to go on top. So first, let's work on getting those square roots not to be a square root anymore, but instead we will have it raised to an exponent. So this is what we can do. So we're still saying y is equal to, and so I have the 4. So instead of saying square root of x, you're going to just say put down x. And when we're looking at a square root, there's actually an invisible 2 here, but we don't really say that. So we have square root of x, and on top of the x, there's a natural exponent of 1. You always leave the x like that, and you say it's the inside exponent over the outside exponent. Okay, so it's in over out. And that's how we'll put it as not a third anymore. So x to the power of 1 over 2. So as a rational exponent. Then we have the 8. We can also just do that to that square root over there first. So we have minus 8 over, that is also square root x. So it will become x to the power of 1 over 2. And then we have, of course, the plus pi and x to the power of 3. Okay. Now the next problem that we have is this. That should not be on the denominator because it's an x. It needs to go to the numerator. When you're taking this and putting it on the numerator, the consequence is that your exponent will become negative. So that's what we need to remember there. So y is equal to, we just have the 4x to the power of 1 over 2 minus, now we have 8, and then we're going to put the x on top, but the exponent now becomes negative 1 over 2. Then we have plus pi x cubed. Okay, so now our function is ready to be derived. So when we're deriving, we're saying dy over dx is equal to, you're going to take coefficient times exponent. So 4 times a half, that's like saying a half of 4. That is just going to be 2. We have x to the power of a half. Then you have to say minus 1. So a half minus 1 will be a negative half. So negative a half. Then we have negative 8. Always take the sign in front of it. It's a negative 8 multiplied by a negative a half. Negative times negative is positive. And 8 times a half, it's like saying a half of 8. That is 4. Then we have x to the power of negative a half minus 1. Same thing as saying minus 2 over 2. And that's going to give you a negative 1 minus 2, negative 3 over 2. Because the denominators stay the same. And then we have a positive pi. It's a number. We're saying positive pi multiplied by 3. And that would just give you a positive 3 pi. And then we have our x to the power of 3 minus 1 would give you 2. So there we go. That's it derived. Okay, then when we have it in this form, now we have to just put it in a way that the exponents are positive. So remember, you only move what has a negative exponent. So we're saying just dy over dx is equal to, the 2 has a natural exponent of 1. So there's nothing wrong with it. So we leave 2 where it was. And the x to the power of negative 1, that will go to the denominator. It's currently on the numerator because everything that is just written like this is naturally already put over 1. So we need to put that on the denominator. It's x now to the power of positive a half. And then with the 4, the positive 4 is fine. It has a natural exponent of 1. We only take that to the denominator. So x to the power of positive 3 over 2. And then lastly, this one, the exponents are not negative, so it's fine. Positive 3 pi x squared. Okay, so that is your final answer. You can put this back as surds, but that's really unnecessary. They would still accept this answer. Okay, so question 8.3, it says the graph of g of x is equal to ax squared plus b over x is equal to 96. Has a minimum value at x is equal to 4. And you have to calculate the values of a and b. Okay, so with this question, I feel like there is a problem with the way they wrote this, because they're saying g of x is equal to ax squared plus b over x. Then they're saying it's equal to 96. So I think they mean that this is the function's equation, but they're also saying that g of x is equal to 96, which probably means the y value is 96. Okay, so they're saying that the y value of this function is 96, but this function also has a minimum value at x is equal to 4. So when we have a minimum value, that's a stationary point that we have. So if we have a stationary point at x is equal to 4, then that just means that at that point, the gradient is going to be 0. Okay, so this is how I would go about working out this question. Because we have g of x, first of all, let's start with, it's going to be a simultaneous equation because we need to solve for a and b. So we're going to have g of x is equal to ax squared plus b over x. Because they gave a minimum value at x is equal to 4, I'm going to find the gradient of this function at x is equal to 4. Okay, because it's a minimum value, I know the gradient already. So to find the gradient, we're going to derive this function. But it's not ready to be derived because we have an x on the denominator. So we need to get that x on the numerator. So I'm rewriting it as g of x is equal to ax squared. And then we have plus b. The x is going to the top. And because it's going to the top, remember, its natural exponent, the natural exponent of x is already 1. So when it goes to the top, you're going to have a negative 1. So you have x to the power of negative 1. Okay, now it's ready to be derived. And when we derive it, we're finding the gradient. So I'm saying g prime of x is equal to, so I'm saying a times 2, which is 2a. And we have x to the power of 2 minus 1, which is just 1. I don't have to write the 1. Then we have a positive b times negative 1, and that will give us a negative b. And we have x to the power of negative 1 minus 1. So if you say negative 1 minus 1, you're going to get negative 2. Okay, so this is the gradient. This is the equation for the gradient of this function at any point. But because x is equal to 4, that is a minimum value. A minimum value is a turning point or stationary point. And at the stationary point, the gradient of a function is equal to 0. And remember, gradient in this case is that g prime of x. We know that this should be 0 where x is equal to 4. So that's what I'm going to say. First of all, let's substitute where x is equal to 4. So I'm saying g prime of, and in place of x, 4 is equal to 2a bracket 4 minus b bracket 4 to the power of negative 2. And this will give us, so now I also know that g prime of 4, okay, the gradient at that point where x is equal to 4, that gradient is 0 because it's a minimum value, a stationary point. The gradient at all stationary points is 0. So 0 is equal to, and so 2a times 4, that's 8a, and then we have negative b, but let's just calculate that part first. So 2 to the power of negative 2 is 1 over 16. So that's negative b, and I'm going to put that as, that's 1 over 16. If you're saying negative b times 1 over 16, then negative b times the 1 will multiply, and then this is put over 1. 1 times 16 is 16. So I can just rewrite that as negative b over 16. Okay, so this is what we have so long. Then I'm just going to take the b over, that over, since it's negative. So we have now positive b over 16 is equal to 8a. Then the b looks much more easier to make a subject. So if we need to get rid of the 16 so that b can be left alone here, we would have to multiply both sides by 16. And now we will just get a b is equal to 8a times 16. 8 times 16, that's 128. So 128. Okay, and we have a, of course, 128a. So I'm saying that this is my first equation. That's the first equation I formed using the information that they have given. The second information we can form is probably because of this 96 now. Remember they said g of x is equal to this function, then is equal to 96. So I'm assuming they mean g of x is equal to 96. And if they're saying g of x is equal to 96, g of x stands for a y value. So that is the y value. That's 96. And they told us it has a minimum value at where x is equal to 4. So it must mean the x value is equal to 4. So I can substitute this as a point into this equation of g of x. Okay, so now that we know the x and the y value, we're going to substitute it into our g of x equation. But let's go ahead and just update the equation because we know what b is now. It's 128a. Okay. G of x, the equation of g of x is equal to, it's just the ax squared. And then we have this plus, the b is now 128a. So 128a over the x. Okay. So in place of x now, I'm going to substitute 4. And so I'm saying we're having g of 4 is equal to, then we have a bracket 4 all squared plus 128a over 4. So we've substituted a into this. Okay, then we just have g of 4. G of 4 is actually 96. Since that's the y value, it seems like that's what they're saying is the y value. So g of 4 is 96 is equal to a, and then that gives you 16. So 16a. Then we have plus 128 divided by 4. So if you say 128 divided by 4, we get 32. So plus 32a. And so these a's can go together. If you say 16 plus 32, that just gives you 48. So 96 is equal to 48a. And if we divide both sides of the equation by 48 to solve for a, we're going to get that a is equal to 96 divided by 48 is 2. So a is equal to 2. So now we know the value of a. Okay. To find the value of b, we can just substitute a into that. So b would be equal to 128 multiplied by 2. So in place of a, I'm putting the 2 that we found. So b is equal to, what is 128 multiplied by 2? And that gives you 256. Okay, so that is the value of A and B, it seems like. Okay, so that concludes it for 8.3. Then we can move on to the next question, question 9. So now we're on question 9, and question 9 says, the graph of h of x is equal to negative x cubed. So notice there actually is a number in front of x cubed. It's negative 1. Plus ax squared plus bx plus c is sketched below. So they give you A and B, and they say that they are turning points of h. So they give us that as 6 and 0. Then they also tell us that t is a point on h. We have been given the x value of t, and the graph of h passes through the origin. So the origin is also another point that we have there. As you can see, it is an x-intercept. It's also a y-intercept as well. So that tells us a lot. The first question, 9.1, we need to show that a is equal to 12 and b is equal to negative 36. So for this question, I'm just going to fill in b. B was, so we don't forget, that was 6 and 0. And that origin, you know, it's 0 and 0. So to find a and b, let's see what we can use. From the graph, we know what the coefficient in front of x cubed is. But also remember, because we know what this is, we know that the graph passes the origin. It means that its y-intercept is 0. This is also an x-intercept, but we know definitely the y-intercept is 0. So this already tells us the value of c. We know that c is equal to 0. Okay, so c is equal to 0. Okay, so that is the value of c. But now, based on the way this graph looks, there is another easier way to actually solve for this. Remember that this is a graph that has an x-intercept that is also a turning point. The equation of this graph in the x-intercept format would look like this. So whenever you have x-intercepts, we have two x-intercepts here. We have one here and we have one here. You can use the x-intercept formula of this, so the format of a cubic function. And that is y is equal to, we have the a first, open bracket x minus x1, and then x minus x2, and that one is squared. The one that is squared belongs to your stationary point that is also an x-intercept. So that one. Okay, so what we can do is we know what a is in this form. It's not this a, okay? This a is a different, this a is referring to the one in front of x squared, okay? That number in front of x squared. This a that I'm referring to here, that refers to whatever is here in the cubic function. So your cubic function, the general equation looks like this. Y is equal to ax cubed plus bx squared plus cx plus d. This is the a I'm referring to over here. Okay, and I'm saying that the value of that a, as we can see over here, there it is. It's negative 1 because we have negative x cubed. So that a is negative 1. So I can fill that in there. So I'm saying y is equal to the negative 1, and then we have x minus our first x-intercept. So this is the normal intercept that is not also a turning point. And that intercept would be here. The x value, okay, that is a 0. So I'm going to say x minus 0, and then open another bracket, x minus the x2, that would be the turning point that is also an x-intercept. And that one, the x value of that is 6. So minus 6, close bracket, all squared. Okay, so let's just solve for what we can here. Here we have y is equal to negative, and we have x minus 0, which is just going to give you x. So it's negative when we times in by x. And then this. So I'm going to open up a bigger bracket so we can just simplify this. Remember with this, all you have to do is square the first term. That's x squared. Then first term times second term. That's negative 6x. Then times that negative 6x by 2. That's negative 12x. Then square the last term. Negative 6 all squared. That's positive 36. Okay. Then over here, I can just go ahead and say negative x multiplied by the x. That's going to give you, so y is equal to, you just have a negative x being multiplied by all of this. X squared minus 12x plus 36. Then I'm going to just FOIL in. So I have this times that, which gives me y is equal to negative x cubed. And then again, multiplied by the second term, that is positive 12x squared. And then by the last term, which would be negative 36x. And then now if you compare this to the equation we had above, you would see that, so I'm just going to rewrite this equation so we can just see what a, b, and c are. Okay, this was what h of x was. So as you can see now, look at the order it's in. We have our negative x cubed. Then you can see now that positive 12, that is your a value. And negative 36, that is your b value. And c really is equal to 0. Okay, so remember they only asked you to find a and b, but we do know c is equal to 0 because that was a y-intercept as well as an x-intercept. So it means that, therefore, a is just equal to 12 and b is equal to negative 36. Okay, so that's how to find a and b. Then moving on to the next question, 9.2. So the next question, 9.2, they want you to calculate the coordinates of a. So a is a turning point. So you just have to find the coordinates of a turning point. To find the turning point, you're going to have to take the original equation and derive it. So we have, it was h of x. We have h of x is equal to negative x cubed, and our a is now positive 12x squared, and then our b is negative 36x, and our c is 0, so you don't even have to write it. So we have this, and we have to find a, which is a turning point. To find the turning point, just derive this. So to derive it, you're getting the gradient. So remember, we're deriving it just so that we can find the gradient of this function. So h prime of x is equal to, and so we're saying this negative 1 times 3 is negative 3x minus a 1 that is squared. Then we have positive 12 times 2, which is positive 24. X to the power of 2 minus 1, which is just 1. We don't have to write that one. And then negative 36 times 1 on the numerator, on the exponent here. So that's negative 36. And we just have, of course, that will fall away because x to the power of 1 minus 1, that's just x to the power of 0. Anything to the power of 0 is 1. This 1 is just multiplying by that and staying the same. Okay, so now that we have this, this is the gradient of this function of h. Since we want the turning point, we are finding the gradient, okay? But we know what the gradient is at the turning point. At every turning point, the gradient is always going to be 0. So we're going to make h prime of x equal to 0, since this is the equation of the gradient. So we have negative 3x squared plus 24x minus 36. As you can see, this is something we have to factorize, but also notice there is a common factor of, I would say, negative 3 all through. So we're going to divide both sides by negative 3 just so that that can be positive. And we're going to get 0 is equal to that. That's going to give you x squared. 24 divided by 3, that's going to give you a negative 8x. And negative 36 divided by negative 3 is a positive 12. Okay, so now that we have this, we can say 0 is equal to, open up two brackets, and we're saying x and x, factors of 12 that can give us a negative 8. Because the 8 is the only negative one, the middle is the only negative and everything else is positive, both these brackets are going to get a negative. So looking for factors of 12, then when you add them, you're going to get 8. So that can be 6 and 2, because if I say negative 6 minus 2, I get negative 8. And if I say negative 6 times negative 2, I get positive 12 at the end there. So that worked out fine, and now we can just solve for x. So it means that x is either equal to 6 or x is equal to 2. So these are our two solutions, but remember, we want b. We already know one turning point. That's the 6. So we're only going to accept the 2. Let's work with the 2. So we want the coordinates of a, so we need to get the y coordinate as well. We have the x coordinate. To find the y coordinate, you take 2 and substitute it into the original equation, not the gradient. The gradient one only tells you the gradient, doesn't tell you a y coordinate. So we're saying h of 2 is equal to negative, open bracket 2 to the power of 3 plus 12 times 2 power of 2 minus 36 times 2. And let's see what this will give us. And when we put that into the calculator, just make sure you put everything in properly. Just be very careful when you do this. You get negative 32. And that makes perfect sense. It's negative because you see the y value is negative. So we know this one now is 2 and negative 32. Okay, so that is the value of a. Make sure you always conclude because they ask you for the coordinates. So conclude a is 2 and negative 32. Okay, so that is 9.2 done. And then we move on to 9.3. So 9.3 says calculate the value of y. So we have to find y. Okay, so y was the y coordinates of t. Okay, so we have 3 and y. So we just have to substitute the x coordinates into the original equation of h and we'll find y, the y coordinate. So since h of x was equal to, I don't actually have to rewrite that. See, here's the equation of h of x in the previous question. So instead, I'm just going to substitute 3 because t was just 3 and y. So h of 3 is equal to negative, open bracket, 3 all cubed plus 12 times 3 all squared minus 36 times 3, and then we close the bracket. And let's see what that gives us. And as you can see here, h of 3 is negative 27. So that is our y value. So it means that y is just equal to negative 27. Okay, so I always just try to answer exactly what they ask for. They ask for y, tell them what y is. Okay, and that's just for 1 mark. Moving on to 9.4. 9.4 says, is the graph of h concave up or concave down? So concave up or concave down at the point T. So show all your calculations. When we're speaking about concavity, let's look at what we have to look for when you're finding things about how the graph is concaved at specific points. So if you have a cubic function, something like that, for example, when you're looking for how it is concaved, it's just speaking about how it's curved. So like a parabola, you have 2 types of parabola, one concave up and one concave down. It's the same thing here. So if you can look at it, you see that this part here, that's the concave down part. And then this part over here is concave up. But then we would need to know where exactly does this start. So, okay, cool. I know that this part is concave up, but like where does that start? Now that starts at the point of inflection, So if the graph looked like this, whatever the x value of your point of inflection is, this part of the graph is concave up. It would mean that whatever the x value is, let's say it was 2, right? You would be able to say, okay, it's concave up at the point where x is greater than 2. So we can see over here, it's all concave up because these are all values that are greater than 2. That's if x was 2. And it would be concave down for where x would be less than 2. That's where it would be concave down. So if they're asking for a specific point, let's say they were asking for 5 and 5 is over here, and you're asking, is it concave up or concave down? Well, this falls in the region of where it is concave up. So at where x is equal to 5, it will be concave up. So let's answer that question for what they actually asked us for in the graph. So at the point of t, let's see if it's concave up. We know what t is. We know the x value of t is 3. So is it concave up here? Now, you cannot just assume that it's concave down just because it looks like that. You can't just assume that. So it means that you actually have to find that point of inflection because you don't know where it changes concavity. You don't know where it changed from concave up to concave down. So let's find that first, that point of inflection. Then we'll be able to judge whether it is concave up at t. So to find that point of inflection, or really just the x value of the point of inflection, we're going to take the equation of h. Let me just write that down. Then we're going to derive it. Okay, so derive it the first time. So we derive it twice. First time we get negative 3x squared plus 24x minus 36. To get the point of inflection, you derive it twice. So second derivative, then we have negative 6x plus 24 when we derive it twice. Then you're going to set that second derivative and make it equal to 0. So 0 is equal to negative 6x plus 24. Because the 6 is negative, I'm just going to go ahead and take it over so it can become positive. So we have 6x is equal to 24. Then we divide both sides by 6 to solve for x, and we find out that x is actually equal to 24 divided by 6. I think that is 4. Okay, so yes, it is 4. So x is equal to 4. So now we know where the concavity changes. Let's mark that place on the graph. So on the graph, the concavity changes at the point where x is equal to 4. And that already doesn't look right. 4 can't be here. So looking at this, I'm just trying to pinpoint where 4 is. I'm just going to assume this one, this t is this over here. So let's say this one was 3. Then after it is 4. So here is our 4. Let's say this is where it changes concavity. 4. The graphs are never really drawn perfectly and to scale and stuff like that. So if it changes concavity here, this is what this means. It means that all through here, you see it's curved up. All the way from here to where the x value is 4. That is concave up. And all the way from here, after the 4, all the way down, that's concave down. So it means that 3 would not fall within the concave down region. It's in the concave up because it's not even past 4. We have 3 here. The point of inflection is at 4. So where t is, where the x value is 3, your graph is still concave up. So that's a way that you can answer that. The graph is concave up. So it just means that the graph is concave up at the point t because x is equal to 4 is your x value of the point of inflection. And you can see it did not go past that x value. Okay, and then 9.5 is determine the coordinates of the point of inflection. Okay, now about this, because it's 2 marks, I feel like they might not have wanted you to find this about the concavity this method, because you see, using this method, you found the x value. We will find the x value because you see, using this method, we would already find the x value of the point of inflection. So if they only gave 1 mark, if we know what the x value is, to find the y value, we would just have to substitute this into that equation. So I find it weird that if they only gave us 1 mark here for doing that, because we knew what 3 was and we just put it into this, then I feel as if this one might only give you 1 mark. So something you can do is show how you found the x value of the point of inflection. That would also mean that there's also another way of doing this. And there's another way of actually finding out whether something is concave up or concave down. And so let me put the second way of doing this. So for this one, we will just need the equation of the second derivative. So of course, we will find the second derivative just like we did here. So I'm not going to rewrite that. I'm just going to put that down, only the equation of it. So I also like to add, this is why it's also very important to look at the next question before actually doing the question you're doing, just to check if there are alternative methods of working through this question. Okay, so this is how to see how it is being concave. We can just go ahead and substitute. We knew that t was 3 and y, but we found out what y is, but we only need the x value. If you want to find out whether it's concave up or down at this point, just substitute 3 into this equation, the second derivative's equation. So if you say f double prime of 3 and we have is equal to negative 6 bracket 3 plus 24, let's see what we get. And you see, we get a positive 6. So we get h prime double prime of 3 is equal to positive 6. If your second derivative is positive here, it's greater than 0, it means that the graph is concave up at this point. If it gave you a negative value, to be concave down. Now, please also take note, this is not the same thing as finding out whether there is a local minimum or local maximum. That is a different situation. In that case, local minimum and local maximums are turning points. The higher one is the maximum. The lower one is the minimum. In that case, I know there's also a second derivative test that we use to test whether it's going to be a local minimum or maximum. This is a different test entirely. In this test, you would have to put in the x value of that turning point. That is a different case to this. This 3 is not a turning point. It doesn't belong to a turning point. So when you substitute any other x value on the graph into the second derivative's equation, it will tell you the concavity at that x value. But when you are speaking about specifically the turning points, it will tell you whether it's going to be a maximum or minimum. And this is how this one works. Let's say this over here is x1, right? And this one is x2. If you wanted to find out, is there a maximum at this point, you would substitute like this. We would say h double prime of, let's say we substitute x1. Now, this one, if it was a maximum, it will give you a value that is smaller than 0. That would mean you have a local maximum. If it was a minimum, when you substitute x2, you would get something greater than 0. That means you have a local minimum. This is different because we are specifically using the x values of the turning points. Okay. But in this one, 3 is not a turning point. It doesn't belong to a turning point. It's just a random point. So that will tell you how it is concave. If it's greater than 0, it's concave up. Smaller than 0, it's concave down. So it just means that the graph is concave up at the point T. So for 5.9, where we have to determine the coordinates of the point of inflection, we're just going to take the original equation and derive that to find the point of the x value of the point of inflection. So if you derive that h prime of x, then derive it again to get the second derivative, that's negative 6x plus 24. Then equate that second derivative to 0. So 0 is equal to negative 6x plus 24. And then take that over. So 6x is now equal to 24. You need to solve for x, divide both sides by 6, and x is equal to 4. So we have the x value of the point of inflection. We just have to find the y value because we need to get the full coordinates. Okay, so to get the y value, substitute 4 into the original equation. So h of 4 so that we can find the y value. Negative 4 all cubed plus 12 times 4 squared minus 3 times 4. And for h of 4, we get negative 16. So it just means that your point of inflection is just 4 and negative 16. And that is the last question in 9.5. Okay, so now we are on question 10, and question 10 says, a hotel has 72 rooms to let to clients. The daily rent per room is 500 Rand. If the rent is increased by 100 Rand per day, 2 rooms can be left vacant daily. The rent is X Rand per room per day, where X is greater than 500. So 10.1 says, show that the total daily income I is given by I is equal to 2x minus x squared over 50. Okay, so let's just read into what is being said here. So this hotel has 72 rooms to let to clients, and the daily rent is 500 Rand. And this rent is going to keep being increased by 100 Rand every day. And while the rent is being increased, 2 rooms are left vacant daily. Okay, and now they are saying that the rent is X Rand per room per day, where X is greater than 500 Rand. And we basically have to find the total daily income. So you have to look at this as if you own a hotel. If you owned a hotel and you wanted to calculate your total daily income, you find your income by basically saying, what is my rent? How much am I charging per room? Multiplied by the amount of rooms that have been rented. So these are the two factors we're going to look at. We're going to have to look at the rent per room versus the rooms that have been rented out. So let's look at the rent per room. Remember that they said that the daily rent per room is 500 Rand. And then, so it's basically starting at 500 Rand. And if the rent is 500 Rand, they also tell us that a hotel has 72 rooms. So this is where it has not been increased by 100 Rand yet. So where the rent is 500 Rand, the rooms available is 72. Then they tell us if the rent is increased by 100 Rand per day, 2 rooms can be left vacant. So 2 rooms will be left open or empty, meaning a total of 70 rooms have been rented. So it looks like this. We have 500. Now it's been increased by 100. And so what happens here is you have your 72 rooms minus 2. So 70 rooms are now going to be rented. So from this, it's kind of like saying, if I wanted to calculate the total income, if the rooms were 500 Rand, then I'll just say 500 times 72, and that would be the price. If I wanted to calculate the rooms, if the rent was this 600 Rand, then I'll just say this 600 Rand multiplied by the 70 rooms available, and I would find that. But the thing here is that they're not saying that the rent is actually a specific price. They say the rent is X Rand per room per day. But before actually looking at that, let's just see the pattern that this keeps creating. Since this part keeps increasing by 100 Rand, the next time that we increase the price again, so when we're increasing the price for the second time, or let's just look at it as the third day after the price has been increased, it would be plus 100 Rand plus 100 Rand. So the previous price plus another 100 Rand. And the rooms rented would look like this. It's the 72 rooms minus 2 of the previous day, then minus an extra 2. So if you look at the rent per room, you see that it's creating a pattern. It's creating a pattern that we can actually sum up like this. We're saying this is 500 and then 500 plus 100. And I'm actually going to say times 1 instead. And then instead of saying plus 100 here, I'll just say plus 100 times 2. So you can see these numbers now are going to start representing the day after the increase. So this is the first day after the price has been increased, the second day after the price has been increased, and this affects the rent, the price of the rent per room. Likewise, I can also do the same to this part. Instead, I can say 72 minus 2 times 1. That was the first day after the increase. And then instead of saying 72 minus 2 minus 2, I can just say 72 minus 2 times 2 instead. This is the way the pattern looks because 2 rooms keep being deducted. So looking at this, we can actually just create a formula because you can see it's a pattern. It's a pattern that is increasing constantly by 100 Rand. We can actually create a formula for this rent per room. So what is actually going on is that we have 500 Rand plus 100 Rand, and then you see that these keep increasing. This is the day of the increase. I'll see it as 1 here stands for the first day of the increase. Then 2 would be the second day of the increase because then we're increasing it by second 100 Rand. So I'm saying 500 plus 100 multiplied by the specific day of the increase. And likewise, the rooms rented can also have a formula. It can also just be, as you can see, it's also doing the exact same thing. This formula or this pattern keeps decreasing by 2. So we can say that it's actually 72 minus 2 multiplied as well by the specific day of the increase. But now if we read into this question, they are giving us a specific rent. We don't have to now guess of which one we're going to take, which particular rent. They said the rent is X Rand per room per day, where X is greater than 500. So when they're saying X is greater than 500, that is really kind of their hint of telling you that it is definitely not this day. We cannot calculate the total rent by saying 500 times 72 because X is greater than 500. So definitely there's been an increase in the day that they are referring to. So the rent on that day is X Rand. And of course the rooms will be calculated still by saying 72 minus 2 multiplied by that specific day of the increase, whether it's the first, second, third, fourth. So looking back at our whole goal of this, finding the income, the total daily income, this really just means that the total daily income is going to be found by saying, again, it's still the rent per room, but in this case, we know that the rent they're speaking about is X Rand. So that would be the X multiplied by the rooms rented out. And that would be this formula, 72. So multiplied by the 72 minus 2 times, I'm just going to use big brackets here, times whatever day of the increase that they are referring to. So that being whether it's the first day of the increase or the second day of the increase or the third and so on. But the reason we cannot calculate, we cannot just give this as the formula is because, as you can see, the formula looks nothing like that. So we actually have to find, it has X, it has numbers in it, but it doesn't have this day of increase. So we actually have to find the formula for the day of the increase. So notice that this day of increase is included in the rooms rented formula, and it's also in the rent per room formula. But let's look in the information and see how we can actually create a formula from this. Remember that they said that the rent is X rand per room per day. If this is the formula for you to get the rent per room per day, and they're telling us that the rent itself is X rand, we can equate this formula with X in order to find the day of increase and put that as a subject. So we're simply just going to say the 500 plus 100 times the day of increase, that being the formula for your rent per day. We're saying that that is actually equal to X because that's what they told us. They told us that X was the rent per room per day. So we're going to equate that with X. And now all we have to do is make this the subject. So to make this the subject, notice the 100 is being multiplied by this. So we need to get rid of the 500 first. So we can take the 500 over, and what we're going to have here is 100 multiplied by the day of increase. And that will be equal to, we still have the X here, then minus 500. Then to make this the subject, that day of increase, we can divide both sides by 100. So divide by 100 and divide by 100. And what we're going to get is that the day of increase will be equal to, so we have, I'm going to split this formula by saying X divided by 100. That's just X over 100. And then negative 500 divided by 100, and that will be negative 5. So that would be the formula for the day of increase. And now we can go ahead and use our total daily income formula and just substitute in place of day of increase. We can substitute this because this will tell us whether it's the first day of increase or the second day of increase and so on. So here again is our formula for the total daily income, and in place of day of increase, I'm just going to substitute this X over 100 minus 5. Okay, so let's go ahead and simplify this. So it just means now that our income is going to be equal to, we still have the X, and then it's being multiplied by, let's sort out what's inside here first. So we just have 72 first, then the negative 2 is going to multiply by the X, and remember the negative 2 is really on the numerator, so it's like negative 2 times X, which is negative 2X over 100. And then we have negative 2 multiplied by negative 5, which will give you a positive 10. Okay, then we can go ahead and just put the 72 and the positive 10 together since they're both numbers. So we have that our income is equal to X multiplied by 82 instead, minus 2X over 100, but that can be simplified as well. So if you say 2 is common in 2 and 100. So if I scratch out 2 here, 2 divided by 2 is 1, but there's an X, I can just leave that as X. And then 100 divided by 2 is going to be 50. So we just have over here an X over 50. Then lastly, this X is going to multiply into these two numbers. So we have X multiplied by 82. So our income is equal to 82X, and X multiplied by negative X over 50, which will be negative X squared over 50. And that's how we get the income. And remember, that is the answer for 10.1. Okay, so that's our answer. And now moving on to 10.2. Okay, so 10.2 says calculate the maximum daily income per room. So the maximum income per room. We already know what the daily income is. This is the daily income per room. So we just have to find what is the maximum value of this. To find the maximum or minimum value, you have to derive this equation and then set it equal to 0. And of course, you can think about it as if it is a curve, right? This case, this is clearly a parabola because it has x squared, the highest exponent is x squared, and then we have an x over here. And you see that in front of the x squared, we have a negative, okay? So it's definitely a concave down parabola, and we're just trying to find that's the turning point. So you're finding the turning point, and we can see this is a maximum turning point. Okay, so we're finding this maximum. So it's also, just remember, it's also, we're just finding the gradient. When you derive anything, you're finding the gradient of that function at any point, but we're trying to look for where exactly is the gradient equal to 0, because only at the turning point your gradients would be 0. So we're deriving this. So I'm just going to say I prime is equal to, and if you derive, now there's a way you can just, before actually doing that, there's a way you can rewrite this so that it doesn't look as confusing as it is. So we have 82x, that one is fine. But this one, we have a minus. Think about the number you have in front of x squared. There's actually an invisible 1. So you could have written this as minus 1 over 50 x squared, because the x squared is on the numerator. So if you look at it like this, it's really like x squared over 1 being multiplied by this. So when we multiply it, it would have been negative 1 times the x squared to give you the negative 1x squared, and the 50 times the 1 to give you the 50. So you can separate it like this. Okay, so there's your fraction and there's your exponent. So now we can derive. So I prime is equal to, I'm saying the 82 times the exponent of 1. So it's 82. And then, of course, the x to the power of 1 minus 1 just gives you x to the power of 0, which gives you 1. So 1 times 82 stays 82. Then we have the negative 1 over 50. So negative 1 over 50 being multiplied by the exponent of 2, so times 2, and that gives you a negative 1 over 25, and then x to the power of 2 minus 1, which is 1. We don't have to write that. Now that we have derived it, this is the gradient of this parabola. We want to find the turning point, or the maximum turning point. So this is going to be 0. We have to make the gradient equal to 0 and say 82, then minus 1 over 25x. In this case, I would rather just put the x on top. It's just easier to solve like this. Since this is negative, I'll take it over. So this is x over 25 is equal to 82. Then we just need to solve for x by multiplying both sides of the equation by 25. And so x is going to be equal to, what is 82 multiplied by 25? It's 2050. So it means that x is just equal to 2050. That would be the x value of the maximum daily income of this. Okay, so that's just the x value. If you're looking at it as a graph, the x value was that 2050. They didn't really ask you for, oh, they did. Okay, they asked you for, calculate the maximum daily income per room. So they are actually asking for the maximum daily income. So they want the y value. This is just the x value belonging to this maximum turning point. We want the y value as well. Okay, so we need to find what that y value is. Simply just take the x value that you found here, substitute it into your original incomes formula, and you'll be able to find the y value. So remember, the income formula looks like this. And so now we're just going to find out what exactly is that maximum amount. So I is equal to, in place of x, because this is just the x value belonging to the maximum value. Okay, so we're putting 82, and then in place of x, 2050 minus, and then that's going to be 2050 all squared, then over 50. And let's see what that gives. Okay, so remember they said that x was really just the rent. That's what they called x. They said it's the rent per day. But the total income is not the rent per day. That's how much you have made in total based on what the rent for that day was. So that the total income would be 82,050 Rand. That would be the total income. So in this case, that's what they're asking for, the maximum daily income. So that is the maximum daily income. The maximum daily income is that. So that's the maximum daily income. Okay, so that's just something that you need to be careful about. Remember, this formula only gives you the total daily income. The X is the rent on that specific day. So we know this was the rent, okay? And then the total or the maximum daily income would have been this amount because you have to take it and put it back into the equation. It's like finding the y value. That was the x value, but 84,050, that was the y value. I said 82,000, 84,050. So that is the final amount. Okay, so now we're on question 7, and 7.1 says, determine f prime of x from first principles if f of x is equal to x squared plus x. So remember, this is 5 marks. This is really a place that you can score marks. In order to find the derivative of this function from first principles, what we can first do is find out what f of x plus h is going to be. So how we find f of x plus h? This is saying f of x plus h, meaning this x plus h is now being placed in place of x. Okay, it's been put here in place of x. So wherever you see an x, replace it with x plus h. So I see x squared, so I'm going to change that to x plus h. And because this is now replacing the x, you have to square that, so all squared. Then we have plus x, so you're going to say x plus h, okay, because we're replacing it. And now we're just going to simplify this. So if we're foiling this one out, you can create 2 brackets, but that does take long. So you can deal with this the quicker method, which is really just to take this and you're going to say the x and we're going to square that, and that gives us x squared. Then we multiply the x and the h, which gives you xh. Then you times that by 2, which gives you positive 2xh. And then lastly, that h, you're going to square that, which will give you a positive h squared. Then plus x plus h. So that's the f of x plus h. So to find the derivative, you're going to use the formula that f prime of x is equal to the limit as h tends towards 0. And then you're going to say f of x plus h minus f of x all over h. Okay, so this is the derivative. It is from the gradient formula. So that's y2 minus y1 over x2 minus x1, which has been simplified to h. So this is equal to the limit as h tends towards 0. And then in place of f of x plus h, we're substituting what it is equal to. Then you have a minus, and then we have to minus this by f of x. So f of x is equal to x squared plus h. So we need to subtract this. But remember, this has more than one term, so you need to protect it with brackets so that that minus can have an effect on both terms. So x squared plus h all over h. And this is equal to the limit as h tends towards 0. We have to keep writing that until we substitute, and we're going to multiply that in. Okay, so everything here is going to stay exactly the same. And then when this one multiplies in, we just get negative x squared minus x. And all of this is over h. Now remember, you don't have to start searching for what's going to cancel. Whatever you are subtracting by is going to be what cancels. So I have a negative x squared, so there must be a positive x squared that cancels with that. And then I have a negative x, so there must be a positive x that cancels with that. And then I'm just going to rewrite what we have right now. That is 2xh plus h squared plus h all over h. Now, the whole point is to get h out of the denominator. So we're going to do this by taking out a common factor of h. So we're saying the limit as h tends towards 0. Take out h as a common factor, and we will be left with the first term, you'll be left with 2x. In the second term, you're going to be left with a positive h. And then you're left with a positive 1. It's really just asking yourself, what do I multiply to h to get back to 2xh? That will be 2x, and so on, all over h. And so like this, the h and the h would cancel. And now we have this. The limit, well, I'm not going to write the limit. I'm just going to substitute. So we only have this, and we can just go ahead and substitute. In place of h, we can substitute 0. So now I don't have to write that anymore. So this is 2x plus 0 plus 1, which of course, that means that f prime of x is really just equal to 2x plus 1. Okay, so another thing that you can also do from the beginning is take this, and derive it from the rule of differentiation. If you do that, you already know what your answer is, and if it's wrong, you'll be able to check where you made a mistake. So if we use the rule, obviously, to derive this one, you'll say the coefficient times the exponent, which will give you 2, then x, then subtract 1 from that, which is 1. You don't have to write that. Then this x just becomes a positive 1, of course, because it has a 1 in front. And when you say the exponent of 1 minus 1, it gives you 0. Anything to the power of 0 gives you 1. And so 1 times 1 is just 1. Okay, so do that just to make sure that you have everything and it is correct. Okay, moving on to the next question. Okay, 7.2, we have to determine f prime of x if we have this expression as f of x. So this is for 3 marks. We have to use the rule of differentiation. So f prime of x, this is already ready to be differentiated. There is no x on the denominator. We don't have any x in a third. So this is fine. So we're going to first of all take the coefficient of this and we're going to multiply that by the exponent, and that will give us 10. Then we have x. Then you have to subtract 1 from that exponent, and that gives you 4. Same thing over here. We're taking the negative 3, that coefficient, times the 4, which gives us a negative 12. Then we leave the x and we subtract 1 from that, and that gives us 3. And then with the 8, we have a positive 8 as the coefficient and an invisible exponent of 1. So 8 times 1 is positive 8. We have x. And then we have to say 1 minus 1, which is 0. And anything to the power of 0 becomes 1. And 8 times 1 just stays 8. So that just stays like that. Okay, so this is what we have, and that is f prime. And it's for 3 marks. So this is a really good 3 marks that you can get. It's a very simple one to derive. Okay, question 7.3 says, the tangent to g of x is equal to ax cubed plus 3x squared plus bx plus c has a minimum gradient at the point -1 and -7. For which values of x will g be concave up? Okay, so we're trying to find out the concavity of this function. Okay, so let's look at the information they've given us. Well, they told us that the tangent to a function has a minimum gradient at this point. And in this function that they give us, a, b, and c is missing. That's a lot of things that are missing. Okay, there's a way that you can solve this by actually just using what you know about cubic functions. So they're saying the tangent to this function has a minimum gradient. Let's think about that carefully. You have a cubic function, but the thing right now is we don't really know what this cubic function looks like. We don't know if a is greater than 0, and so therefore it looks like this, which is really the shape of a capital letter N, but just more curved. And we also don't really know if a is less than 0, so if it looks like a backwards N, just more curved. We're not really sure what it looks like yet. Okay, now that we have these two, because they speak about the gradient, they say it has a minimum gradient. Just remember, if you have this type of parabola, something that looks like this where a is greater than 0, if you derive this cubic function, you're going to end up with a parabola that is concave up because the a value was greater than 0. And this one, you end up with a parabola that is concave down. Okay, now the thing about this is that they tell us that the tangent, so there's also a tangent that we have to take into account. The tangent to this has a minimum gradient. So when you're finding the gradient of a cubic function, those are the parabola, because when you derive the cubic function, you get a parabola. So this represents the gradient, but they're saying that it has a minimum gradient, meaning its gradient, okay, has a minimum value. So the only type of gradient of a cubic function, in other words, the only type of parabola of a cubic function that will have a minimum value would be this one, because this has a minimum value. Here's your minimum. That's the lowest point that this parabola can go. This one has a maximum. So now immediately we know what the graph is going to look like. So we know for sure that a is definitely greater than 0. Okay, so that's our a value over there. We know that a is positive. Okay, let's try to see what we can do with this now. Now we know the shape of the cubic function. So let me put down a Cartesian plane and actually draw this down. So the cubic function I know now looks like this. Now, taking into account the information we have, we also know the gradient, okay, of this cubic function creates a concave up parabola. So I'm also going to draw that in. So concave up parabola. But I'm going to try and keep that turning point at this point, this side of the x-axis, because they do tell us that this tangent to this has a minimum gradient at this point. Okay, we'll still draw the tangent in and then put down that point. But I know that it has a minimum gradient at this point. So its x value is -1. So if it's here, something like that, then we know, okay, this is our minimum. So what they're saying is that this cubic function, let me actually correct the way it looks quickly. Okay, so the cubic function, which is of course g, this cubic function has a tangent being drawn to it at this point, okay? That tangent has a minimum gradient. So here, at this point, so we know that since the tangent has a minimum gradient, where we have this minimum value of this parabola, which represents the gradient, that's that minimum gradient, okay? This tangent is going to be perfectly in line with this point so that their gradients are the same. Okay, because when you move along the graph, the gradient changes. So that it has a minimum gradient, it's perfectly in line, vertically in line. So that point could be over here. And so that tangent could look like this. I have to draw it like this. I can't really draw it like this because then it wouldn't be a tangent. It would cut here and here. So that's not a tangent. A tangent must cut a curve only once. So I have to draw it like this. That means this is what the tangent probably looks like, something like this. And this tangent is cutting only once. Just pretend it's cutting once. I'm actually supposed to rotate it a little bit. It would look like that, something like this. Okay, so this is what we have. Now, the points that it's cutting the cubic function itself is at -1 and -7. So that is at -1 and -7. And this is already saying a lot. Because we know now that this has a minimum, okay, gradient, this is really what this means. You need to remember how cubic functions and their derivatives work. When you have a cubic function that looks like this, if you derive it, it will become a positive or concave up parabola. Okay, something you should remember is that the point of inflection of this cubic function, you see that x value, it's going to be the exact same x value as the turning point or that minimum value of your parabola. That's going to be in line with each other. So that, since we have a minimum gradient here, and this is perfectly in line with this point, which is -1 and -7, that means that that point is your point of inflection. So we know the point of inflection now. So I'm going to just say that the point of inflection is -1 and -7. And just like this, we'll be able to solve this question. We need to find out for which values of x it's going to be concave up. Okay, for a graph to be concave up, when you have a function, we already know what it looks like. You have to just find the point of inflection. If you find the point of inflection, all it just means is that wherever it looks curved up, this part over here, that is where the graph is concave up. And then this part over here is where the graph is concave down. So since we know that this one is concave down here, this one is concave up here, we're just looking for the part that is concave up. We already know the x value that belongs to the point of inflection. It's -1. So it's concave up for all these values over here. Everything here, it's curved upwards. See, so that's concave up. So these are, we have to see the x values that belong to these points. Looking at it compared to -1, these are all values that are greater than -1. All of these, they have values greater than -1. So the values of x for which this graph is going to be concave up is where x is greater than -1. Okay, so that's one way of solving that question. But that's actually how I would have done it. I am more of a visual learner, so I would rather do this and just draw out the graphs to try and make sense of it. Okay, so that is it for question 7, and then we move on to question 8. Okay, so question 8, we have this. Okay, so the graph of y is equal to f prime of x is equal to mx squared plus nx plus k is drawn below. Then they tell us that the graph passes the points P, which is negative 1 over 3 and 0, Q 1 and 0, and R 0 and 1. And first of all, we have to determine the values of m, n, and k. So we have to basically find the equation of this parabola. Okay, just pay close attention to what they have given you in the parabola. First of all, they gave you an x-intercept, gave you another x-intercept, and then they give you another point. Whenever they give you two x-intercepts, you can use the x-intercept formula of a parabola, which looks like this. It says y is equal to a bracket x minus x1 multiplied by x minus x2. So these would be your two x-intercepts, those x values. So we can actually use this, okay? But because they strictly did say that we would have to find m, n, and k, I can actually just call a m, okay? Because here it's in the form of ax squared plus bx plus c. So as you can see, because a is in line with m, then that is m. So I'm just going to change that to m. Okay, so now x1 and x2, this is what we have. x1 is the first x-intercept, the x value of it, which is negative 1 over 3. And x2 is 1, and the second x-intercept that we have. So we can just substitute these first into the equation. So we have y is equal to, then we still have the m, open bracket, x minus x1, so that's going to be minus negative 1 over 3. But remember, minus negative 1 over 3 is just going to be plus 1 over 3. So I'm going to change that to plus 1 over 3. Then we have x minus 1. Okay, so that's the x-intercepts in. And now that we have this, as you can see, it's almost complete. The equation is almost complete where you just have y and x's. The only thing that's missing is m. So to find m, you can just take this other points that they gave you and substitute it in. So we can go ahead and just substitute r, which was that 0 and 1. So you're going to substitute this in place of x and y. Okay, so let's go ahead and do that. So we have y, so I'm going to put that as 1. So 1 is equal to, and we have m multiplied by x, and x is 0, so we just have 0 plus 1 over 3, and x again, which is 0 minus 1. Okay, so simplify. Let's just figure out what these ones are going to be. So first of all, 0 plus 1 over 3 is just 1 over 3. 0 minus 1 is negative 1. So that's 1 over 3 times negative 1. What does that give us on the calculator? So 1 over 3 times negative 1, that's of course going to be negative 1 over 3. Okay, so we have m and then negative 1 over 3 and 1. So we just need to solve for m by getting rid of this negative 1 over 3. If you divide both sides by negative 1 over 3, so here we're going to have that m is equal to 1 divided by negative 1 over 3. You can put that on the calculator, but it's just going to become negative 3. So there, we found m. Okay, we found the value of m. Now to find n and k, you can just substitute m back into the equation and simplify, put the equation in standard form, and naturally you'll be able to see the value of n and k. But honestly, k is easy. K is y-intercept, so that's k. But either ways, we can just go ahead and put it in standard form just so that we can find n at least. So this is y is equal to the equation of it, and I can call it y is equal to because they did say y is equal to f prime of x. So y equals, and we have negative 3 multiplied by x plus 1 over 3 multiplied by x minus 1. And now if we go ahead and simplify this, equal to negative 3, and let's just FOIL this out. So that's going to be x squared negative x positive 1 over 3x and negative 1 over 3. Now simplify negative 3, we have x squared. What is negative x plus 1 over 3? That's like saying 1 over 3 minus 1, because that's the coefficient that we have there. Now this is a positive 1 over 3. I'll just change that to a 3 over 3 which is going to be negative 2 over 3. So you can use a calculator as well. Negative 2 over 3x and then minus 1 over 3. Then I'm going to just multiply this in. So y is equal to negative 3x squared positive. So you see the 3, I know that it's negative and negative, so it becomes positive, but the 3 is going to cancel with that 3 on the denominator because this is naturally on the numerator. So we have positive 2x remaining. Then likewise with this, the negative and negative give you a positive, but the 3 ends up cancelling with the 3 on the denominator, which gives you positive 1. That's what's left on the numerator. And that's what we have. So this would mean that now that it's in this format, this would mean that m, and this is n and this is k. So it means that m is equal to negative 3, n is equal to 2, and k is equal to 1, which we could already see from here that k was 1. Okay, so that's how to solve for this. You have to use the x-intercept formula of a parabola. Okay, moving on to the next question. Okay, 8.2 says if it's further given that f of x is equal to negative x cubed plus x squared plus x and then plus 2, we have to determine the coordinate of the turning points of f. So to find the stationary point of a cubic function, what you're going to do is we use this logic. To find the stationary point, at the stationary points, your gradients are standing still. They're not moving. They're neither increasing nor decreasing. And so because of that, the gradients are specifically just equal to 0. So what we're going to do is find the gradient of this function and set it equal to 0. To find the gradient of this function, you just derive it. So we're going to make f prime of x equal to 0. Okay, let's derive the function. So that is negative 1 times 3, which is negative 3. Then we have x. Then minus 1, which is 2. Then that is going to give you a positive 2x. Okay, 2 times 1. Then subtract 1 from that, which is 1. You don't have to write that again. Then we have plus 1, of course, because we have the coefficient times the exponent, which gives you 1. The x, then we have the minus 1 from the exponent, which gives you 0, which anything to the power of 0 is 1, and 1 times 1 stays 1. Then the constant falls away, okay? It really just becomes 0 because you're finding the gradient of each of it. Gradient of a constant is 0. Okay, so this is what we have. We set this equal to 0, and then we just have to solve for x now. So since this is negative, it shouldn't be negative if you want to nicely factorize. I'm going to get rid of that by dividing both hand sides by negative 1. And so we have 3x squared minus 2x minus 1 is equal to 0. Then you would have to factorize this. Now, there is a hack. You can use this hack. Just don't show them that you use the parabola, the quadratic formula. So how you can factorize or pretend to factorize it is by doing this. So on your calculator, you're going to substitute this in as if you're using the quadratic formula. So we can just go ahead and say negative b, so that's negative, and b is negative 2. So negative 2, bracket negative 2, plus minus, I'll start with the plus, square root of b squared, but b is negative 2, so negative 2 all squared, minus 4, and then a is 3, and then c is negative 1, over 2a, and a is 3. Okay, so you see the first solution we get is 1. This is how we're going to look at it. I'm going to open up two brackets as if I am factorizing. And I know that this is equal to 1. So that is the factor that is less complicated. It's a whole number, or an integer rather. So I'll say x is equal to 1. This is the solution for it. But when I am solving here, I'm just going to say, to get the factor, it's like taking 1 over, which is going to give you x minus 1. So the factor is x minus 1, therefore the solution is x is equal to 1. Okay, to find the other factor, I would change the sign now to a negative, so minus now. And then this is what I get, but it should be a fraction. So there, it's negative 1 over 3. And this is how I'm going to put it. I say x is equal to negative 1 over 3. And now I use the same logic here. I'm kind of taking this over, and this is now x plus 1 over 3. But then it's not supposed to just look like that. The thing about this is that whatever is here is actually supposed to be your coefficient of x. So you take this to the coefficient of x, so that's 3x plus 1. That's actually what your factors would have been, 3x plus 1. So you can get rid of that, just write that in pencil. And so there, it looks as if you factorized and you got your solutions. The only reason I do this is just in case they actually do require you to give them factors and they'll give you a mark for the factors. I don't think they do that as much anymore though. Okay, but now that we have these as our factors, all we're going to do is, these are the x values, okay, of the stationary points. To find the y values, you would just take these x values and substitute it into the equation. So I'm saying f of negative 1 over 3, I'm substituting this x value in, is equal to, we have negative x, so negative bracket negative 1 over 3, all cubed, then plus negative 1 over 3 all squared, then we have plus x, but I don't have to say plus negative 1 over 3 because this is going to multiply and become negative. I can just say minus 1 over 3 and then plus 2. So you can go ahead and substitute this into your calculator and see what you get. Okay, so the first solution we get is 49 over 27. So that is for negative 1 over 3. So let's also find the one for 1. So 1 is equal to negative bracket 1 cubed plus 1 squared minus, not minus, plus. Okay, that was a plus x, plus 1, and then plus 2. Okay, so f of 1 is equal to, we substitute 1 into the equation, and then we get 3. So there, our stationary points, or our turning points, is specifically called the turning points. So the turning points are negative 1 over 3 and 49 over 27 and 1 and 3. So those are our coordinates of our turning points, and that is 3 marks. So it's a very simple thing to do for 3 marks. Moving on to the next question. Then 8.2 says, draw the graph of f, indicate on your graph the coordinates of the turning points and the intercepts with the axes. So good thing about this is we already have the turning points and the intercepts with the axes, we can actually find them because of this. So remember how a cubic function, right? When you derive it, it becomes a parabola. Well, this is the derivative of that function that we have. Okay, it's still the same question. So the derivative of this function, since this cubic function is concave down, the type of cubic function that you're going to have is going to be a function where a is less than 0. And this is going to look like a backwards n, just more curved. So we already know what this is going to look like. It's going to look like a curved n, something like this. Okay, now I'm just doing this only so that I can find the things that we need to look for specifically. Okay, so the x-intercept of the parabola is going to be the same x value as the turning points. Those ones, they're not really a problem because we already found the turning points. The things that would need to draw this cubic function is we need to know the y-intercept of the cubic function. We also need to know its x-intercepts. Now, right now, that's what we don't have. So clearly, we have to find those. And now it makes sense why they would give us 5 marks for this. It's clearly because we still need to find those x-intercepts, which we do not know. We do, however, know the equation of the cubic function. So this is this, right? So we have f of x is equal to the negative x cubed plus x squared, and then that was plus x plus 2. Okay, so plus x plus 2. So we have this, and what we're going to do now is we're going to have to factorize this in order to find the x-intercept. Okay, so before finding those x-intercepts, let's just state everything we have. We have the turning points of this, okay? And let's just put them down so that we know that everything is here. We also know the y-intercept. You see, the y-intercept, this is already in standard form. The y-intercept is always going to be that constant, that value without a variable in it. So it's 2. So as a y-intercept, naturally its x value is equal to 0, meaning your y-intercept is just 0 and 2. So we have all of that. The only thing we need to find now is the x-intercept. To find the x-intercept of a function, you need to just make y equal to 0. So we're going to say 0 is equal to negative x cubed plus x squared plus x plus 2. And now we have to factorize this. So this is a step where we have to actually factorize a cubic function. So since we have to factorize this, we have to use one method of factorizing cubic functions to factorize this. I'm personally going to use the synthetic division method because I like that method more. So with the synthetic division method, first of all, you're going to look at the constant and you're going to find factors of that constant. So factors of 2. Now factors of 2, you're going to have to take positive and negative factors as well. The first factor of 2 will be 1, and so the second one will be negative 1, and then 2 and negative 2. And what we're going to do is we're going to substitute these values into the function, and we need to find the one that actually gives us 0. See, we're saying 0 is equal to that. So we need to find the one that actually gives us 0 because that one will be a root or one of the x-intercepts. Okay, so I first of all tried 1, and as you can see, it's not working. It didn't give me 3. Also notice I put brackets just so that it's easier to substitute in case like I'm substituting a negative number. Okay, so I'm going to try negative 1 next. So if I make that negative, let's see what we get. So that gives us 3. That is not 0. Let me try 2 next. Okay, so when I try 2, it works out. It gives us 0. So it means that 2 is a root. Okay, so since 2 worked, then it means that x minus 2 is a factor. Okay, that is a factor because x is equal to 2 is one of your solutions. So it's just like taking that over. So x minus 2 is a factor of this, okay, cubic function. So there may be an easier way of doing this, but I'm just going to try and do this whole synthetic division just for anybody who wanted to maybe learn it. Okay, so here, now that we found out that 2 works, what we're going to do is we're going to draw an L, a letter L, but backwards. So like this, that has a really long tail. Then we're going to put the number that worked here, so 2. And then in here, let me actually just make this straighter. So in here, what we're going to put is the coefficient of all your variables. First of all, the coefficient of x cubed is negative 1. So we're going to put that here, negative 1. Coefficient of x squared is positive 1. So we have a positive 1. And then we have another positive 1. And lastly, the constant, which is a positive 2. And this is how synthetic division works. Step 1, you drag this number down. That negative 1, we just drag it down. Then you say negative 1 multiplied by the 2 here. And that gives you negative 2. And you put that on top of here. Then you say negative 2 plus 1, and that's going to give you negative 1. Then negative 1 multiplied by 2, which gives you again negative 2. Then negative 2 plus 1, which gives you negative 1. Then lastly, negative 1 times 2, which is giving you negative 2 again. And then negative 2 plus 2, which gives you 0. Now this is the thing, you should always end with 0. If you end with 0, then you know that you had multiplied and added properly. So this is our factors. You see these numbers here, they represent the coefficients of your parabola that you're going to have. When you factorize this, it's going to be a quadratic expression. So this is the coefficient of x squared, this is the coefficient of x, and that's your constant. That's how this is going to work. So it means that in our expression, what we had is this, 0 is equal to all of this, right? But now we're going to have 0 is equal to, and the first factor that we already had was this x minus 2. That was a factor. So we have x minus 2. And then in this bracket, we're going to put our other factor, which is these ones with their coefficients, of course. So the coefficient of the x squared is negative 1. So we have negative x squared. And then we have negative x. And then a constant of negative 1. So that would be this factorized. Okay, so now we have to just try and solve for x. So the first one is quite easy. X is just going to be equal to 2 because you're taking negative 2 over. Then we have or, and then this one. Now this one already looks really weird. Definitely cannot. So because even if you decided, okay, let's make the coefficient positive. So we divide both sides by negative 1. Then you're going to get x squared plus x plus 1 is equal to 0. Already looking at this cannot be factorized because if we have x multiplied by x, and now we have to find out what multiplied by what would give us a positive 1. Well, that's 1 times 1. But when you add these two, they should give you the coefficients of the middle. And we can clearly see that's not happening. Now, another way to find out whether this does not have solutions is to actually just use the quadratic formula on it. Then you see that it will not factorize. As you can see on the calculator, it is ending with I. So that is not a real number. So it doesn't have solutions. So here, x has no solution. You can just say x has no solution. And that's okay. So it means that it only has one x-intercept, which is 2. So the x-intercept that we have is 2 and 0. That's the only x-intercept that we have. Okay, let's try and plot this graph now. So you're just going to plot all the points that you do have, and let's see how it works out. Okay, so this is all our points. We have a turning point, we have a y-intercept, and one x-intercept. So just draw down a Cartesian plane. And now I'm going to put down the values because I don't want to start writing numbers. We don't have to do that. So we're going to plot down the values. First of all, on the y-axis, the only value I see that we have is the 2, this one, okay, for the y-intercept. So I'm going to plot that down. I have a 2 over there. You can plot it as 0 and 2, but even if you said 2, that just makes sense. It's fine. It's a y-intercept anyways. It's not a normal point. And then we have an x-intercept of 2 itself. So that's over here, and I'm just going to put that as 2. Okay, then we have turning points. So the turning points we have this and this. 1 and 3 is going to be somewhere here. 1 and 3. So that's 1 and 3. And then we have this negative 1 over 3. So negative 1 over 3 is just a third. And 49 over 27, I'm just putting it down because I just want to see roundabout where it is. 49 over 27 is like almost at 2, almost at positive 2. So negative 1 over 3 and almost at positive 2, we have that. The points, you just have to make sure that you are writing those coordinates down. That's negative 1 over 3 and 49 over 27. Okay, now we can draw down our cubic function. Remember the shape of it, because we had that f of x was equal to this. The a value is negative, so your graph is going to look like a backwards n, just more curved. Okay, so we're going to have to try and draw it like that, noting where the turning points are. In other words, noting where we need to curve. So we need to curve here and here. So it means that our cubic function is going to look like this. It's going to come down like this. And then it's going to go up like this, cross that y-intercept, and it's going to stop here and curve, and then move downwards and pass that x-intercept. So it's going to look something like this. Not the most perfect graph, but that's roughly what it would look like. And then just name it f because it was f of x. So there we go. And they will give you 5 marks for all of that, for basically finding that x value of your x-intercept and sketching the graph down. Okay, so that is our cubic function. Moving on to the next question. Okay, so 8.3, we have points E and W are 2 variable points on f prime. So they're probably speaking about, it's still f prime. It's still this question basically. So on this graph that we have over here, the one that they gave us in the beginning, this graph, I don't need that anymore. Okay, so we have 2 points on this graph. For the sake of understanding, I'm going to copy this graph and then put it there. Okay, and then they say that, so these points E and W are 2 variable points on f prime and are on the same horizontal line. Okay, so there is some sort of horizontal line. Let's just say it's here. And we have these 2 points on the same horizontal line. Okay. And of course, they are on F. They did tell us that there are points on F and they are on the horizontal line. So this is E and this is W. So E and W. Then they tell us that H is a tangent to F prime at E. Well, tangents are straight lines. So we have a straight line that is a tangent to this graph of F at the point E. So since it's at the point E, supposing that E is over here, then this tangent must look like this. Because it's a tangent, it must only cut the graph once. So it's going to look something like this. And it basically just touches the graph once. Okay, so that is our point. That's our H. So I'll label that H. Okay. Then they also tell us now that G is a tangent to F at W. So G is a tangent to F at W. So we have another tangent here. By default, we have to draw it like this. So we have to draw it like this. Something like that. Okay, let me just correct what it looks like. Okay, so that's what that looks like. And that graph is called G. Okay, then they tell us that H and G intersect at D. And this is the coordinates we have, A and B. So these two graphs eventually intersect. So looking at the way it looks, it's clearly going to intersect as they go up like that, then they intersect. So let me just extend them and then show that point of intersection. Okay, so there they intersect at this point. And we're calling that point D, which is A and B. And the question is, we just have to find the value of A, that's all. So that value. Okay, so this doesn't seem that bad given that we already know what the equation of f prime of x is. Okay, so remember that f prime of x is equal to, honestly, I forgot what it was equal to. Let me just see what it is equal to again. Okay, it was equal to this because we found the equation of it. Okay, so let's also look at the other information that they gave us. Well, they told us that these are two variable points. So variables are like letters. We don't really know what the numbers of these points are, but we do know that they lie on the same horizontal line, meaning their y value is going to be exactly the same. So if this was like a half, then this y value is also going to have a half, and that y value will also be a half. Okay, but as for the x values, we don't know what that is. So the x values are different. Because of that, I can call this one P, and then the y value, let's just call that Y. And then with the other point as well, I don't know what its x value is. I'll just call that Q. And the other point, I'm also going to call Y, just to really emphasize that the Y values are going to be exactly the same. Okay, so it's interesting that they don't ask for B. They only ask for A. Okay, so the fact that it lies on a horizontal line, this is actually where we'll be able to solve for this. Okay, let us use the x-axis quickly. You see the x-axis, something that we understand about the x-axis is it is a horizontal line. And the points of intersection of this graph and the x-axis are your x-intercepts. Now, before looking at those x-intercepts, let's just look at something quickly here, right? With this line, because this is a flat horizontal line and it's being drawn from a point with the same y value, okay, as this point. It means that this right here would be an isosceles triangle that we have. From this point to this point of intersection will be the exact same distance as from this point to that point of intersection as well. Because this is a straight line, it is constant, it's consistent, it's not going to change its shape. It's going to keep constantly going in the same direction with the same gradient. So because they are from the same horizontal line, they're going to meet, okay, exactly at the middle of this parabola. So looking at the x-intercepts, if we were trying to find that exact middle point, okay, because this will be the middle point since these two are exactly the same lengths. If we're trying to find the middle point, that will be the midpoint of these 2 points over here. If you find the midpoint of the x-intercepts, you would find exactly what the middle point is. And so that would be the x value you will have and the y value as well. And that x value would belong to the x coordinates of A. They are intersecting at the midpoint of this line, which is also the midpoint of the x-intercepts because of the way a parabola behaves. A parabola is going to always be symmetrical about its turning point. So there's two ways to find this. You can either find the x value of the turning point of this because that will be the midpoint, or you could physically take these 2 points and find the midpoint of it. That midpoint, that x value is going to be the same x value that we have, okay, in between here, and also the same x value where these two graphs intersect. Okay, so I feel like any method you use would still work. You can use the finding the x value of the turning point, which you would just say x is equal to negative b over 2a, and then you find it. Or we could also just use the midpoint formula and say x is equal to x1 plus x2 over 2. And of course, y1 plus y2 over 2. But we don't really have to find the y1 and the y2 because they're both just 0. It's going to stay 0. So we can just focus on the x. So that would be negative 3, 1 over 3, sorry, plus 1 and divided by 2. Okay, so let's see what this gives us. Okay, so as a fraction, that gives us 1 over 3. So it means that x is equal to 1 over 3. And that is the x value of this point, which is a. So it therefore means that a is just equal to 1 over 3. Okay, just remember you can also use this. It will also give you the x value of the turning point, which would be the midpoint of the two x-intercepts and even these 2 points, as long as they have the same y value. When you're trying to find the midpoint of it, okay, it's going to be exactly the same. If I put down a horizontal line like this and I try to find the midpoint of these 2 points, it's still going to be in between here again. Because of the way the parabola behaves, it is symmetrical on the left and the right hand side. Okay, moving on to the next question. And then 8.3.2, we have determined the value or values of B for which H and G will no longer be tangents to F prime. Okay, so looking at this graph, how can we make these two lines to no longer be tangents to this graph? So by definition, a tangent is a line that cuts a graph only once. And that's what these two graphs are doing right now. They're cutting the graph here and here. But we want these two graphs to no longer be a tangent, but they want us to determine the values of B for which this will happen. So we're going to control these two graphs, using the B value, meaning we are still keeping in mind that they are going to still be intersecting. But we're going to have to see what B should be in order for us to do this. Now, honestly speaking, in my head, I can see the way this looks, but I know you may not be able to see it in your head as well, and I can't just say it with words. So I'm going to create an animation for this and then explain this using that animation. Okay, so we're looking at these two tangents, H and G, and we have to manipulate them from the point of D. Okay, so we're manipulating that value of B so that these two tangents are not going to be tangents to this graph of f prime anymore. Okay, so first of all, since we're trying to manipulate the value of B is the y value of this coordinate of D. If you're trying to manipulate a y value, if you change its value, you're either going to move that point up or down because it's a y value. So it's either going to move up or down. X values move left and right, but we're trying to manipulate B, and that is the y value. Okay, so now that we understand that we need to either move that point up or down, okay, and not saying the graph, the points, because they said specifically B, and that is a coordinate, okay, that's the y coordinate of that point of D. Okay, so let's think about that. If we move that point up, so that means we're just taking the value of B and we are increasing it to higher than whatever it was currently. So if we do that, look at what happens. So if B is at a higher place now, then look at what's going to happen to the graphs. You see, these tangents, look at what happens to them. D is still the common point of intersection. We know this because they told us to manipulate B, which is the y value of D, so that these two are not tangents anymore. So we are moving it from this point. And you see what it did to the graphs? Well, doing that doesn't really solve the problem because they're still tangents. And because they're still tangents to this graph, it's not going to work. We need them to not be tangents anymore. Okay, let's try moving it higher than when it currently is right now. So if we move it higher, look at what happens to the graph. See, it still doesn't solve the problem because H and G are still tangents to the graph of f. Now, because of the way the parabola works, and because of the way it is curved, it's still not going to solve the problem. If you keep moving that point up, if you keep manipulating B to be a higher value than what it was. So, how about we try moving this parabola down? But let's just reset it and put it back to what it originally looked like. So this is what it looked like. Now we're going to take that point, or we're really manipulating the value of B, and we're going to manipulate the value of B to make it a lower value than what it currently is right now. Let's look at what happens to the tangents. You see, now the tangents, they are still tangents to this graph. They're still intersecting the parabola at one point. So that doesn't solve the problem, but we're getting somewhere. Let's move it even lower. So when we move it even lower, you see that it's getting closer to the turning points. We're just trying to make these tangents not tangents, meaning they must not touch that parabola once. Okay, so let's see. How about we take that point and we move it right to the turning point, okay? Let's move it right to the turning point of the parabola. And look at what happens when we do that. Let's just monitor the graph of h first. Let's see what happens. If you move that point of D and you make the B value to be exactly the Y value of your turning point of that parabola, look at what's going to happen to that tangent of H. See, it's still a tangent to this graph, but now it is a flat horizontal line, which makes sense because at the turning point, the gradient of the turning point is 0. So it makes sense that it's making a flat horizontal line because horizontal lines have a gradient of 0. That's why they're flat. That is the ground we walk on every day unless you live on the mountains. Okay, and the graph of G does the exact same thing. The gradient is 0. This is a flat ground. Okay, so moving the graph down, it's still a tangent when we move it down until the turning points. The thing about this is, yes, they look different now. They're both in the same position, the exact same place, to a point that they're just literally overlapping each other. But there's still a tangent to the graph of f. They're tangents at the turning point now. So let's take that point D, right? We're manipulating the value of B. Let's make B a lower value than what that Y value of the turning point is. Let's see what happens when we do that. Okay, so if we move that down, let's see what's going to happen. And let's just monitor first of all the graph of G. Okay, so remember they are going to move at the same time, but I'm just moving it one by one so that you can see what's happening. If we move the graph of G, do you see now, is this a tangent now to this graph? No, it's not a tangent anymore. And because it's not a tangent because it's intersecting the parabola at two places, not one place anymore. So it's not a tangent anymore, it's now a secant. Okay, let's take the graph of H and let's do the same thing because they're actually supposed to move at the same time. So there we go. The graph of H is also now a secant. It's intersecting the parabola at two places. So if we take the value of B and we make it lower than whatever the Y value of the turning point is, then it's not going to be a tangent anymore. They're going to be secants. So we're taking it from that point over there. And we have to find out what exactly that point is. If we can find out what that point is, then we'll be able to find out what exactly we need to make the value of B to become less than. Okay, because B must just be less than whatever that value is. Then it's going to be a secant and not a tangent. Okay, so looking at that value of B, what can we do? Well, first of all, since we're trying to find out what exactly that's going to be, we can take the actual formula for the parabola and we can substitute 1 over 3 since it is the x value of the turning point. And to find the y value of the turning point, we can substitute that into the equation. And when we do that, we get 4 over 3. So now we know what's there. That's 4 over 3. That is the y value of the turning point. So if we can just make that b value to be anything lower than 4 over 3, then it's going to make these tangents not to be tangents anymore, but rather to be secants. So b just needs to be less than 4 over 3. Okay, and that's how we solve that problem. Okay, so from the animation, you would have seen that all you really needed to do was find that y value of the turning point and finally tell them that b needs to be less than 4 over 3. Okay, and that's it for question 8, and then we move on to question 9. Okay, so question 9, the last calculus question for this paper, we have given f of x is equal to x squared, we have to determine the minimum distance between the point 10 and 2 and a point on f. Okay, they at least told us what f of x looks like. It is x squared, which is just the mother graph of a parabola. So it basically looks like this. So this is our mother graph of the parabola, that is our graph of f. And we have to determine the minimum distance, okay, between the graph of f and this point, between this and this point. So 10 and 2 is like 10 and 2. So 10 and 2 is over there. And we just have to find the minimum distance, okay. So the reason they say minimum distance is because there's different ways to find the distance of this point and this graph. You could have been looking at it like from a point over here till there. But that's definitely not the smallest distance. That's not the minimum distance. You could have also been looking at it from like here to here, or even here to here. Okay, so we just want to find out the minimum distance. It can be from numerous points, but the lowest one basically. Because you see the word minimum, it's going to have to do with deriving at some points, and then we're going to have to find the minimum value. So let's go ahead and just try to find the distance of this parabola. In order to find the distance of 2 points, naturally you need an x and a y value of both points. Here we have an x and a y value, we have 10 and 2. But the other point, remember, the other place that we are looking for, the other points that we're starting from, is this parabola f of x is equal to x squared. We don't have an x and a y value. So what we can call it is, we're just going to say, let me just get rid of these other lines and just going to say, let's say this is the minimum point. Okay, the x value belonging to this graph, because we don't have an actual number, we will call that x. And so the y value would just be the result of substituting x, which would be x squared, okay? F of x is equal to x squared. So the y value is x squared. So we're trying to find the minimum distance of this line using these 2 points as our 2 points on sort of like a line, okay? So that would make this your x1, and that can be x2, and that can be y1 and y2. What did I just write? Sorry, I meant x1 and x2 and y1 and y2. There we go. So those 2 points, we're just going to try and find the distance of that. Okay, so let's use the distance formula. The distance, I'll just call it d for now, is equal to the square root of x2, so x2 minus x1 all squared, plus y2 minus y1 all squared. So that's how we find that distance. Then we're going to say the distance is equal to, and substitute. So the square root of, and we have x2, which we said is 10. So that's 10 minus x all squared. Honestly, I want the x to be first. I'm going to change that to x1 and that one x2. Okay, so that means this is now x2, which is x minus 10 all squared, plus y2, which is the x squared minus 2 all squared. Okay, so now that we have this down, what we're just trying to find is the minimum distance. So if you want to find the minimum distance, the lowest distance, we can just simplify this as far as possible. And then with that expression, if we can find out where that expression will be a minimum value, we can take that expression and substitute it back into this distance formula. Okay, so let's just simplify this. So we're going to have the square root of, and we have, first of all, this is being squared. So I'm going to take the x and square it. That's x squared. Then x multiplied by negative 10 is negative 10x. Then multiply that by 2, which is negative 20x. And then negative 10 all squared. 10 squared is 100. So that's positive 100. Then here we're going to have the same situation as well, because we have 2 terms and we're squaring it. So we take x squared and we square it, which will give us positive x to the power of 4. And then we're going to take the x squared and multiply it by the negative 2, which is negative 2x squared. Then you take that and multiply it by 2, which is negative 4x squared. Then the last term is a negative 2. You square that and that gives you a positive 4. Okay, so that's just a quick way of simplifying instead of taking two brackets and then distributing it. Okay, so we're going to have the square root of, and let's just put our like terms together. So we have x squared and we have a negative 4x squared. Those can go together. But I'm going to put them in the order of the exponents. So highest exponents to lowest. So the highest exponent is that x to the power of 4. Then we have the x squared. So x squared minus 4x squared is negative 3x squared. And we're done with that. And now that we're done with those ones, I'm just scratching it out. Then we have this. So negative 20x, and there's nothing else with an x. So minus 20x, and then 100 plus 4, which would just give us 104. So positive 104. Okay, so this is what we have. And we have to find the minimum value of this. Okay. So to find this minimum distance, if you take the expression that is under the radical, under that square root, all we're going to have to do is find out at which x value or x coordinate that this will end up being at a minimum. Because if we find out which x coordinate would make this expression a minimum, when we substitute that into this, it's going to give us the minimum value of this entire expression. So I'm going to separate this. I'm only going to use this right now and try to find out what exactly the minimum value of this expression will be. Okay, so to find this minimum value, we're going to derive this expression. So I'm going to take this expression and derive it, and let's see what we get. So let's just say it's y is equal to this. So it's going to be y prime is equal to, and so we have 4x to the power of 3 minus 6x. We're basically deriving just like we have throughout the paper. Then minus 20. Okay, so this is what we get when we derive this. Now, to find the minimum value happens at the turning point. To find the turning point, you're really just going to make your gradient equal to 0, because the gradient of a turning point is always 0. That's why it's stationary. So 0 is equal to 4x cubed minus 6x minus 20. Okay, then we have to factorize this. Okay, so this was for 8 marks. That's probably why. So you see, we have to factorize a cubic function. Again, so this is a cubic function, but we do not have x squared, and that's not a problem. So first of all, to factorize the cubic function, you look at the constant term, and you're going to get factors of that constant term. So factors of negative 20, that would be 1 and negative 1, 2 and negative 2, 4 and negative 4, 5 and negative 5, 10 and negative 10, and 20 and negative 20. And then you're going to have to substitute these values into this and see the one that gives you 0. So 1 does not work. It gives us negative 22. Let's try the next one. Negative 1 gives us negative 18. And then 2 gives us 0. So 2 works. So we're going to use 2. And let's go ahead and we're going to say that now, since 2 worked, it means that, remember, the solution is x is equal to 2. The factor is x minus 2. It's like taking the 2 over. So it means x minus 2 is a factor. Let's just keep that in mind. Okay, then to factorize, we draw a letter L, but backwards. Then the number we put here is the one that worked, which was the 2. And then we're going to put the coefficient of everything we have here. But the thing is, it must be in the order of x cubed, x squared, x, and your constant. Okay, that's the cubic part. So the coefficient of x cubed, we can see that's 4. But then we don't have x squared, so we're going to give it a coefficient. Because it's not there, we're going to say it is 0. So we're going to put 0 as the coefficient of x squared. And then we have the coefficient of x, which is negative 6, and negative 20 as your constant. Okay, now that we have all of this, let's go ahead and start simplifying. So first of all, we drag 4 down, and we're going to say 4 multiplied by this 2 over here. So 4 times 2 is 8. Then 8 plus 0 is 8. Then 8 times 2 is 16. 16 minus 6 is going to be 10. 10 times 2 is 20. 20 minus 20 is 0. We ended with 0, so we know everything is correct. So it means these are our factors. See, when we had this, we're going to now say 0 is equal to, the first factor we had was x minus 2. That's why the 2 worked. So we have x minus 2. Then open a bracket. Now, these are our other factors. Remember, they are in the order of x squared, x, and the constant. So we have 4x squared plus 8x plus 10. Okay, so this is our factors and we can just factorize now. So 0 is equal to x minus 2. Then factorize this. Well, so I can just say that x is either equal to 2 or 4x squared plus 8x plus 10 is equal to 0. Then I see that there's a common factor of 2 all through. So I can divide both sides of the equation by 2. And so we get 2x squared plus 4x plus 5 is equal to 0. Then we can factorize this. Then if you try to factorize this, like normally or using the quadratic formula, you will notice that it does not factorize. So it means that there is no solution for this. And again, we have one solution only. X is equal to 2. Okay, so since x is equal to 2, it's the only solution that we have. We don't even have to test and see whether it is the one that's going to give us a minimum value or not. Okay, so see, it has no solution. It has an I in it. That is an imaginary number. But of course, on your calculator, it would say math error. So this is what we have. We have x is equal to 2. So that just really means that x is our solution. So we know that x is equal to 2. And all we have to do is take that and substitute it into this. If you like, put it into this, but it's not necessary. You can put it straight into the distance formula. So we're taking this distance formula and we're going to put in place of x, we will substitute 2. You can put that on your calculator and see what you get. And we get that distance to be 2 square root 17. So the distance is 2 square root 17, which we can just round off to 2 decimal places, which is going to be 8.25 units. Okay, so that is the minimum distance. And now we're on question 7. And 7.1 says we have to determine f prime of x from first principles if f of x is equal to negative 2x squared minus 1. Okay, so since you have to do it from first principles, you can actually just find the answer first so that you know what your answer needs to look like. If we derive this using the rule of differentiation, we will say f prime of x is equal to the negative 2 times the 2 is negative 4. Then we have x minus 1, which is 1. We don't have to write the 1. And then we have a constant. It falls away. So you know that this should be your answer. Okay, so when deriving this from first principles, you can start with this formula, the f of x plus h. Let's find out what that is equal to. We already know what f of x is. So this just means that whenever you see x, replace it with x plus h. So this is going to be equal to, we have the negative 2, there's an x, so replace it with x plus h. Then we have a squared, so all squared minus 1. Okay, so simplify this further, it's negative 2. Then we have to square this. So it's 2 brackets being multiplied by each other. So square the first term, that's x squared. Then square the last term, that's plus h squared. Then the first term times the second term, that's going to be xh. Then times that by 2. So that is positive 2xh. Okay, then minus 1. So this is what we have. And then remember, it's a closed bracket here because this still needs to FOIL in. Then we're multiplying in the negative 2 into these 3 terms here. And so we will have negative 2x squared minus 4xh minus 2h squared minus 1. And that is your f of x plus h. So the formula to calculate the derivative of this from first principles is f prime of x is equal to the limit as h approaches 0, and then we have f of x plus h minus f of x all over h. So this is equal to the limit, again, as h approaches 0, and we have f of x plus h, which is all of this. So put that in carefully. Remember, this is like 5 marks. That's really a place where you can score marks. So minus 4xh minus 2h squared minus 1. Then we're saying minus. And remember, you're subtracting it by something that has more than one term. So you need to put brackets. So minus, open a bracket, and we're going to say minus negative 2x squared minus 1 all over h. Then we have is equal to the limit as h approaches 0. We'll repeat everything that we have there. Just make sure to be careful as you write everything down. And then this negative is going to multiply into that. And so we have now a positive 2x squared, and we have a positive 1 all over h. Now, the thing about this is things are going to cancel here, and you don't have to really just search. You know that what you subtracted by, that's the only thing that's going to cancel. Okay, so if you have a positive 2x squared here, it will cancel with a negative 2x squared. If you have a positive 1, then there must be a negative 1. So the positive 1 cancels with negative 1. They just become 0. So long we just have, again, the limit as h tends towards 0. We keep writing this until we substitute. So negative 4xh minus 2h squared. That's all we have here, okay? And then all over h. Then we have to take h out as a common factor. So we still have the limit as h approaches towards 0, and you only take it out so that it can cancel and you don't get to substitute 0 into here, because that will make it undefined. So to find out what is here, it's like saying, what do you multiply to h to get back to negative 4xh? Or you could just say this, negative 4xh divided by h. H's will cancel, you're left with negative 4x. Same thing here, this divided by the h. One of the h's would cancel here, and you'll be left with negative 2h all over the h. Okay, so here's your h is cancelled in, and then I'm going to just substitute already. So I don't want to rewrite that again. I'm saying negative 4x minus 2, and in place of h, I'm going to put 0. So f prime of x is going to be equal to, this times 0 just stays 0, so negative 4x. And as you can see, we got the same answer using the rule. Okay, so that is 5 marks. So 7.2, we have to determine 7.2.1 f prime of x if it is given that f of x is equal to this. So we just have to derive this. This is already ready to be derived. So f prime of x is equal to, we're saying the negative 2 times the 3, negative 6, and then x to the power of 3, then you have to take out a 1 from the exponent. So that's going to be squared. And then you have the positive 3 as the coefficient times the exponent of 2. That gives you a positive 6. And then you have x to the power of the 2 minus 1, which of course gives you a 1, but you don't have to write that 1. Okay, so when we derive that, that's all we get. And that is for 2 marks. Okay. So 7.2.2, we have to determine the derivative if y is equal to 2x plus 1 over the square root of 4x. So sometimes you have to make sure that the equation or the function that you're going to derive is ready to be derived. You see, in this one, you have a square root. Now, the square root is not necessarily a problem. If you just had square root of 4, it's not a problem. The problem is the fact that x is in the third. X should not be in the third, and it also shouldn't be on the denominator. Okay, so we're going to have to fix that first. So we just have y is equal to 2x plus the 1 over the square root of 4x. Okay, so the square root of 4 can be square rooted. So we can simplify that. So this is very different from something like this. If you had 4 plus x, you can't square root this because you cannot square root across terms like that. But this 4 and the x are being multiplied, so we can. So we can have y is equal to 2x, then plus 1 over, the square root of 4 is 2. But the square root of x is still the square root of x. So this is what we're going to have, 2 square root x. And then now the new problem is the fact that this is still on the denominator and it's also a third. So let's first change it to not be a third anymore. So we will just say y is equal to 2x plus 1 over, then we have the 2. Now the x, this is what's actually going on here. It's a square root. So here, the exponent that we have here, it's actually a square, just like when you have cube root. Okay, it's a 3 there. So there's an invisible 2 here. And in front of every number and variable, there's a natural exponent of 1. So we can actually rewrite this like this. We can say x, and then we're going to raise it to the power of, you always say the inside exponent over the outside exponent. So that is 1 over the 2. So that's how we can rewrite that. And then now the new problem is that the x is still on the denominator. We need to take it to the numerator. But when you take it to the numerator, it's going to cause its exponent to become negative. Okay, so we have y is equal to 2x plus, and so now I'm moving this x to the numerator. 1 is kind of like standing as a placeholder here. Because there's already going to be an x on the top, I don't have to rewrite the 1. That's like saying 1x. There's no need to say that. So we have x to the power of, that half now becomes negative a half, and we have over 2. Okay, now in this case, I'm actually going to leave this 1 here. The reason why is because we need to have a number here. So that 1 in front of the x, I'm actually going to leave it here. So we have a 1 in front of the x, and this is the reason why. So I'm going to say y is equal to, we have 2x, then plus, and I will rewrite this like this. We say 1 over 2, and then we have x to the power of negative a half. See it like this. The 1 and the x to the power of negative a half are being multiplied. You could move this away and let the 1 carry the denominator of 2. Because this is just a separated form of this. We could have just said, if we said x to the power of negative a half and we put this over 1, you see the fact that these two are next to each other, they're actually being multiplied. So if you wanted to get it back to this point, you multiply the numerator and the numerator, which would give you that, and then the denominator and the denominator, which would give you the 2. Okay, so we can actually just write it like this. And now this is ready to be derived. So we'll say dy over dx is equal to, and so let's derive this. It's the coefficient times the exponent. There is a natural exponent of 1 on top of the x. So it's going to multiply by that. And so you have 2 times 1, which is 2. Then we have x to the power of this 1 already that is already there. But then you have to subtract 1 from the exponent. So minus 1, which would give you a 0. And anything, so it's x to the power of 0. Anything to the power of 0 gives you 1. And 2 multiplied by 1 just gives you the 2. So that just stays 2. Then we come to this part. It's the positive half as the coefficient multiplied by a negative a half. And that will give you negative 1 over 4. Okay, you can be using the calculator for this. Then we have x to the power of, we still have our exponent, and we're going to subtract 1 from it. So 1 can look like, you can also just calculate that on the calculator. So 1 can be written as 2 over 2. I'm just writing it in a way that the denominators are the same. So dy over dx is equal to 2 minus 1 over 4 x to the power of, so I'm saying negative 1 minus 2, which is negative 3. Over, and then the denominators stay the same because we are subtracting. When you're adding or subtracting, your denominators must stay the same. So over 2. Then lastly, you can just write this in a way that the exponent is positive. So this is just dy over dx is equal to 2, then minus. Remember that this x is actually on top. It's on the numerator. So we need to take it to the denominator so that its exponent will be positive. So we have 1 over, the 1 is still there, 4, and then the x comes here now. And then the exponent is now positive 3 over 2. So this is the derived form of that function that we had. Okay, so that is 7.2.2. Then 7.3 says the graph y is equal to f prime of x. Okay, so this is already a derived graph. Has a minimum turning point at 1 and negative 3. Determine the values of x for which f is concave down. Okay, so the fact that they're saying y is equal to f prime of x, that derived graph already, has a minimum turning point. When you're thinking about something that has a minimum turning point, we can imagine a parabola that is concave up. This will have a minimum turning point. So if this is the equation of y, okay, because this is the y is equal to f prime of x, this is the graph that has been derived already. So if this is the derived form of this graph, okay, this is f prime of x, then the original graph must have been a cubic function with the a value being greater than 0. Okay, so you have to think about it like this. The cubic function, the equation of it looks like this. Ax cubed plus bx squared plus cx plus d. If you derive this, okay, so y prime, if you derive this, you're going to get this a, because if a is greater than 0, it's going to look like an n, okay, a capital letter N, looking like this, okay, but just more curved. So that's how it looks. And so if you derive this, you're going to get a parabola. So you have to think about it like this. This 3 is already positive, and you have to multiply it by the coefficient of x. If this is positive and you're multiplying it by a positive, then this 3a, this value, is a positive number. So you have now x squared. Then, of course, the b times the 2 will give you plus 2bx and 2bx. And then you have 2 minus 1, which is, of course, 1. Then you would have plus c, and the d would fall away because it's a constant. It doesn't have x in it. So you see, this would be the equation of a parabola. And you can see that the coefficient of x squared is positive. 3a is positive because a was positive and 3 was a positive number, and they multiplied. So it will create a concave up parabola. So that's what I'm saying. The only way we can have this kind of graph, if this is f prime of x, it must mean that the original graph is a cubic function that has the a value being greater than 0, meaning it looks like this. Okay, just also remember, if a value is less than 0 in a cubic function, the graph will just be like a backwards n, okay, but more curved. Okay, now I don't really need this part. I was just trying to explain that and where that comes from. So they're saying if we have this graph, that f prime of x, that y is equal to that, it has a minimum turning point at 1 and -3. So 1 and -3 is the minimum turning point. This is f prime of x's minimum turning point. Okay, then the question is, you need to determine the values of x for which f is concave up. The blue one would be a graph of f. That's the original one. That's the derived one. So where is it concave up? For you to find out how it's concave, you need to know what the point of inflection is. Okay, just also remember when we're looking for concave down, so here, this part would be concave down. That is curved downwards. And then this part would be concave up. Okay, it's like a parabola. Like we have a concave down parabola and a concave up one. So we're also looking at that here. But we need the point of inflection to be able to find out for which x value this thing would be concave down, because we need to take this blue part. This is concave down. So with this, you have to remember that if we have a cubic function and we derive that cubic function and it gives us the parabola, this turning point, the x value of the turning point, is also going to be the x value of your point of inflection. Okay. So the point of inflection's x value is also 1. So we just have to find out where is it concave down. So the highlighted part in blue, that's where it's concave down. Okay, starting from whatever x value this is, and we know now it's 1. So imagine you had a y-axis. Okay, and for the sake of this, I'm just going to get rid of that. I don't really need that part. So we want to find out where's it concave down. So it's concave down all through here. If this x value, the point of inflection's x value, is 1, and then these are all the places that it's concave down after 1. So here, moving to the left, you see, look at all the points for which this graph is concave down. All of these points are concave down, and look at the x values. They are values that are what than 1. These are values that are less than 1. That would be the value of x for which it's concave down. So you can conclude and say that x needs to be less than 1. Okay, so that is 7.3, and that's the last question in question 7. Okay, so we're on question 8, and question 8 says, given f of x is equal to x cubed plus 4x squared minus 7x minus 10, we have to write down the y-intercept of f. Okay, so when we have to find the y-intercept, just remember that you only have to just make x equal to 0. But there's an easy way to see the y-intercept. So remember that this cubic function is in standard form. And so the y-intercept will be the last number without a variable in it. So that would be d. That is your y-intercept in the cubic function. So the y-intercept is where y is equal to -10. As a coordinate, the x value is 0 and the y value is negative 10. So you can also go ahead and make x equal to 0 and substitute in place of x 0, you will get negative 10. Okay, moving on to the next question. They want you to show that 2 is a root of the equation f of x is equal to 0. Okay, so for 2 to be a root, meaning it is an x-intercept, it really just means that if you take this, you have to take 2 as an x value, and if you substitute it into the equation of f, it should give you 0 as your y value. So that will prove that it is a root. So I'm going to take the function of f of x and I'm going to substitute in place of x. I'm going to substitute 2, and it's equal to 2 all cubed plus 4 multiplied by 2 all squared minus 7 multiplied by 2 minus 10. Okay, and you can go ahead and put that into the calculator and see what you get. And when we put that into the calculator, you see you get 0. So I guess here you're just getting a mark for substitution and for your answer. Okay, then moving on to the next question. 8.3 says, hence factorize f of x completely. Okay, so since we know that 2 is a root, we have to factorize f completely. So the fact that they told us that 2 is a root, it helps us to factorize. Okay, so this is the equation of f of x. So the method we're going to use to factorize this is synthetic division. Now, when using synthetic division to factorize, first you're going to focus on the constant in this function. So we have negative 10 as the constant, being the only number without a variable. So we look at that constant and we take factors of that constant. So the factors of negative 10 would be things like negative 1 and 1, negative 2 and 2, 5 and negative 5 as well, right? But we don't have to do this anymore, because the whole point of doing this is so that you can take these numbers, these factors of negative 10, and substitute it into the equation, okay, into the function, and the one that gives you 0 is your root, and we use that number in our synthetic division. But we don't have to do all of that, because we already know they told us that 2 was a root. So we already know which number here will work. It's 2 that's going to work as one of the factors of negative 10. These aren't all the factors of negative 10, by the way. So since we already know that, it means we can skip that step. We know that 2 is a root. Okay, so this is how we're going to use it. We're going to put 2 on the right hand side, and then we're going to draw a capital letter L, but we're going to draw it backwards. So a backwards L, which would look like that. Okay, and then after we have drawn that, now you're going to look at all the coefficients in f of x, all the coefficients of everything here. So the coefficient of x cubed is a 1. So we're going to put 1 here. Then the coefficient of 4x squared is that positive 4. So we'll put a positive 4 here. And then, of course, the coefficient of x is negative 7. So we have minus 7. And lastly, we have the negative 10. Okay, then the first thing you do is, you see this 1, you drag down the 1. Then we're going to say 1 multiplied by 2, which gives you 2. And we put that answer on top of here. Then 2 plus the 4. Okay, we take whatever sign is here. That is 6. Then again, 6 multiplied by 2, which is 12. Then 12 minus 7, that gives you 5. Then 5 again multiplied by 2 gives you 10. And lastly, 10 minus 10 is 0. And this is one thing, you should always end with 0. If you didn't end with 0, it means you must have miscalculated somewhere. So just always make sure you end with 0. Okay, so this is how it's factorized. Remember that 2 was already a root. So if we're factorizing f of x as it is, if 2 is a root, so it just means that when you were simplifying, when you said f of x is equal to 0, 2 was one of your solutions, meaning x is equal to 2. But now we need to see what the factor was. So to find the factor, it's like taking the 2 over the equal to sign. And so the factor is actually x minus 2. So x minus 2 is a factor, but x is equal to 2 is one of your roots. So we're going to put, this is the first factor we have, x minus 2. And then to find the other factors, we are going to use the coefficients of these numbers that we found here. And how we use them is like this. 1 is the coefficient of x squared. 6 will be the coefficient of x. And 5 will be your constant, the number without a variable in it. So when we write down these factors, it's really 1x squared, but we don't have to write the 1. It's just the x squared. And then we have a 6x, so it's positive. So it's a positive 6x and then a positive 5, so plus 5. And that is our second factors. Okay, so we still have to factorize this part further. So that would be f of x is equal to, then we have x minus 2. And then we factorize this. So open up two brackets and we're going to have x multiplied by x is what gives you x squared. Then we have to ask ourselves, what multiplied by what will give us a positive 5, but that can help to give us a positive 6 in the middle. Also notice everything is positive. So factors of 5 would be positive 1 times positive 5. That would give you the positive 5. And of course, if you see you have positive 1 plus 5, it would give you the 6 in the middle. Okay, so these are our factors and now it is factorized fully. Okay, so that is for 3 marks. That's what you get for 3 marks. Then moving on to the next question, 8.4. If it is further given that the coordinates of the turning points are approximately at 0.7 and negative 12.6, and then this as well, negative 3.4 and 20.8, draw a sketch of the graph of f and label all intercepts and turning points. Okay, so they gave us turning points. They gave us the stationary points or our turning points. So we know what those are. Now we can just go ahead and put down our intercepts. Okay, so we have that f of x being factorized, but we just have to find the x-intercepts of this. So to find the x-intercepts, you're going to make y equal to 0. So make that equal to 0. So really what you have is 0 is equal to, and then you have x minus 2, bracket x plus 1, bracket x plus 5. And it works with the same logic as quadratic equations. You're saying something times something times something gives you 0. So we're going to say either this first bracket is equal to 0. Therefore, we're saying that either x is equal to 2 or x is equal to negative 1 or x is equal to, take the 5 over, negative 5. So those would be our x-intercepts. Okay, then also to find the y-intercept. So you can put it as coordinates as well, just to remind yourself. That's 2 and 0. This one will be negative 1 and 0. This one is negative 5 and 0. Okay, the y-intercept, we already have that. So the y-intercept is this over here, 0 and negative 10. So we can also just put that down. Our y-intercept is 0 and negative 10. And then, of course, they gave us the stationary points. Okay, so one thing about this graph is, apart from the stationary points and all the intercepts, you have to know the shape of the graph. So the shape of this graph, since the equation of it is x cubed plus, and then this keeps going on. But remember, we have x cubed, meaning the coefficient of x cubed is 1. It's a positive 1. So it means that a is greater than 0. And when a is greater than 0, your graph is going to form a capital letter N, but it's just going to be a more curved one. Okay, so to draw this graph, we already know the shape of the graph. So what I'm going to do is I'll just put, I don't know where the x and the y axis is yet. What I would actually do is draw the graph. I know what it looks like. It looks like this. So that's what I'll do first. And then now we can start figuring out where the other things are. Draw the graph first, then you can draw the x-axis. Okay, now that the x-axis is there, let me just make this line straighter. So there's the x-axis. Now we can just put down the x-intercepts, because that will help us to just know where exactly the y-axis should go based on these numbers here. So the x-intercepts we have is, the smallest one first is negative 5, then negative 1, and then 2. Okay, so I'm putting it down like this. I have negative 5 over here, then I have negative 1 over here, and then the 2. So from this, you'll be able to see where the y-axis is going to be. Since this is negative 5, negative 1, then you know after negative 1, you should have 0. And when you have 0, that's where your y-axis is going to be. Then, of course, you have the 2. So that's what I'm going to do. I'm going to draw the y-axis just after that negative 1. So the y-axis can be here. Remember, they don't really care too much about you writing numbers. They just want to see the shape of the graph is right, your intercepts, even the y-intercept as well, and the turning points. Okay, so here's the y-axis, and now I'm going to just go ahead and put down that y-intercept. So the y-intercept was 0 and negative 10. So 0 and negative 10. All I have to do is say that it's intersecting here at 0 and negative 10, or you could even write the negative 10. You can write it as coordinates, it's fine. So negative 5 and 0, and we have negative 1 and 0, we have 2 and 0. Over here we have the 0 and negative 10. And then of course we're going to have the turning points. So the turning points are just going to be the one here and the one there. Also just look at where the numbers are going to be. You see this one, the x value should be smaller than the x value you're going to have for this one, because this one is more further to the right. So let's see which one has a smaller x value. So we have the 0.7 and the negative 3.4. So this one definitely is the one that we have here. Okay, so this one is going to be negative 3.4 and the 20.8. Okay, so 20.8. 20.8. That's that turning point. And then this one over here is going to be this 0.7 and negative 12.6. So 0.7 and negative 12.6. There we go. Okay, so not really perfect, but it's a quicker way to draw the graph because they really just want to see the shape is right and you have all your intercepts and your turning points. Plus in the memo, that's usually how it looks. They don't really have numbers in the memo. And of course, because the name of the graph was, the name of the equation of the graph was f of x, we can go ahead and name this graph f. Okay, so that is a method you can use to draw your graph. First, start off with the shape of the graph. Actually draw the graph. So the shape of the graph, whether it looks like that or like that. You can even use this trick for the parabola as well. Works well with the parabola. Secondly, you put down your x-intercepts. Then you're able to find your y-axis based on that. Okay, so y-axis. Then you put down your y-intercept. And lastly, you're able to find your turning points. Okay, so those 4 steps would really help you with sketching the graphs. Okay, next question. So the next question is 8.5. Use your graph to determine the values of x for which f prime of x is less than 0. So when they're saying f prime of x, what do they mean? So f prime of x, when you derive a function, what you're finding in that function is the gradient of the function at any point. So when you say f prime of x, it's really speaking about gradient. So this question is really saying, where is the gradient less than 0? Okay, so let's try and understand what positive and negative gradients mean. When you have a line that is doing this, okay, you read functions from the left-hand side all the way to the right-hand side. What is this line doing moving from the left to the right? You see that this line is increasing. And so when a line is increasing, it means its gradient is positive. Okay, that's what increasing functions do. They increase moving from left to right. And so it means that if you have a line that looks like this, and you again read it from left to right, it means that this line is decreasing. So we're reading it from left to right and you see it's moving down. So the gradient of this graph is negative. That means it is decreasing. Now we do the same thing with curves as well. So we're only just looking for where is the curve, where is the gradient of the curve negative? In other words, where is the curve decreasing? So if we look at this graph, where is it decreasing? So let's just go ahead and check what it is doing throughout. We're going to start from the left-hand side moving to the right. Over here, reading it from left to right, look at what this part of the graph is doing. It is increasing. Then it reaches the turning point. Now at the turning point, it neither increases nor decreases. And that's why at this point it is stationary. This is a stationary point. And then after the turning point, look at what it starts to do. It starts to decrease. Then it reaches another turning point and it stays stationary and then it starts to increase. Remember, we're looking for where f prime of x is less than 0. In other words, where is the gradient smaller than 0? Where is it decreasing? And this graph is decreasing here. So all the way through here. And it is decreasing. Okay, so let's find out which x values exactly belong to that part of the graph, because we always have to answer them in terms of x. Okay, so the x value that belongs directly to this point is negative 3.4. Okay, so that's the negative 3.4. And also let's just mark the x value that belongs to this endpoint as well, since it only decreases from here to here. So that is the 0.7. So notice what it's doing. If we line these parts of the highlighted graph to the x-axis, you see that these points are points that are what than negative 3.4. They are points that are greater than negative 3.4. You see, because they are on this side, on the right-hand side of negative 3.4. But what than 0.7? You see that these points, look at where they are. They are on the left-hand side of 0.7, so they are less than 0.7. So this is really how we can write this. We can write this as a single inequality. We're saying that x needs to be greater than negative 3.4. So it needs to be greater than negative 3.4, but less than 0.7, but less than 0.7. And that would be the values of x for which this graph has a negative gradient, or where f prime of x is less than 0. Okay, so that is where x is greater than negative 3.4, but less than 0.7. Okay, moving on to the next question. Then the next question, 8.5.2 says, the gradient of a tangent to f will be a minimum. So we have to determine the values of x for which the gradient, okay, of a tangent to f will be a minimum. Okay, so let's break this down. The gradient of a tangent. Let's just understand what that means. They're really just adding too much words. I feel like this word tangent is unnecessary in this. But just think about it like this. The gradient, okay, of a tangent. When you have a curve and you have a tangent to that curve, so no matter what the curve is, whether it's a parabola or a cubic function, let's say you have a tangent drawn to a curve at a specific point, because tangents only ever touch a curve once. So understand that when they're saying the gradient of a tangent to f, this is what they're saying. The gradient of this line to this graph, okay? The gradient of the tangent to f and the gradient of f at this specific point, they're exactly the same, okay? They're equal at this point. So if the gradient of a tangent, of this tangent, let's say it's 2, then it means that the gradient of the graph at this point is also 2. So let's just establish that when they're speaking about the gradient of a tangent to f, let's just understand that part as the gradient of a point on f. So since the gradient of the tangent to f is exactly the same thing as saying the gradient at this specific point on f, if it's exactly the same, let's just skip this word tangent and let's actually speak about the gradient of f at a specific point. So if we rewrite this question, this is really what it's saying. So the question is really just, where will the gradient of f at a point be a minimum? And now we can think about what the gradient of f is actually speaking about. Remember that f is a cubic function, right? If we're trying to find the gradient of f, it means you need to derive the graph of f. And if you derive the graph of f, it's going to form a parabola. If this one is positive, if this one, its a value is positive, when you derive this, it's going to form a concave up parabola. Okay, so this would be the derivative of f. In other words, this function represents the gradient of f. So this is what they're actually speaking about. The gradient of f refers to this parabola. The question is, where will this parabola be at a minimum? Or where will this parabola have a minimum value? So you see now, since it's a concave up parabola, it will definitely have a minimum value and not a maximum value. See this, it comes from infinity going down, and then at this point it turns and starts to increase. This would be the lowest point on this parabola. That is the minimum. So the question is, where will this graph be at a minimum? They want you to answer them in terms of x. You just need to find the x value belonging to this minimum point on this parabola. Okay, because the parabola stands for the gradient of f. That's really what it is. So let's find that minimum value. Okay, let's find the x value belonging to that minimum value. We can first of all start by drawing this derivative of f, that parabola. We can draw that graph. So that graph is going to look like this. So when we're drawing this parabola, the thing about this parabola is that we actually know the x-intercepts of it. You see the x value of your turning point, that negative 3.4, is going to be the same x value of your x-intercept of your parabola. And then the other turning point as well, the 0.7, that is also going to be the x value of your x-intercept of your parabola. And remember, your parabola will be concave up because this one, the a value is also positive. So our graph is basically going to look something like this. The parabola is going to go like that and like that. So something like that. Not really a perfect one, but okay, let me try again. So like this, and then moving up like that. Okay, that looks better. So that will be f prime of x. Okay, this is the derivative of that function, that cubic function. And we just have to find its turning point, but not really the full turning point, just the x value of the turning point, because that will tell us where this graph will be at a minimum. Okay, so to find the x value belonging to that turning point, all you have to do is, you see, this is your x-intercept and this is another x-intercept of this graph. That point that we're looking for is going to be exactly in between, halfway in between these 2 points. So we're really going to find the midpoint of these 2 points. And how we can find that is, first of all, it's already on the x-axis. So we already know that it's going to also be on the x-axis. We just need to find its x value. And you can find its x value by using this part of the midpoint formula. We're just going to say x1 plus x2 and divided by 2. So we're taking x1 of this parabola's x-intercept, okay, because it's halfway between these two x-intercepts of the parabola. So we're taking the negative 3.4 and adding it to the 0.7, and then you're going to divide that by 2. That will be the calculation. And so if we do that, let's see what we get. So if we do that, we get negative 1.3. So that is the amount we get, negative 1.35. Okay, so that point where x is equal to negative 1.35, that will be where this graph will be at a minimum. And therefore, that is where the gradient of a tangent to this graph will be a minimum. That will be your answer. Okay, so we need all these calculations there. Okay, and that's how we find the answer. Okay, so that's a way to really just understand what was actually going on there. Okay, so moving on to the next question, this is what we have. We have f prime of x being multiplied by f double prime of x. Where is it going to be less than or equal to 0? Okay, let's talk about this graph, f double prime of x. Since f prime of x, we already found that it's a parabola. So remember, this is how it works. The cubic function, that was f. If you derive this positive cubic function, it will give you a concave up parabola. Okay, also just remember, if your cubic function, if a was less than 0, it would not look like this. It would be like an n, a capital letter N, written backwards, like that. And if you derive that kind of graph, you would have a concave down parabola. Okay, so in this one, we have a concave up parabola for f prime of x. So f double prime of x will be a straight line, but an increasing straight line. So that is a straight line with a positive gradient. So I'm just showing you what f double prime of x is going to look like. We're going to have to draw this in order to be able to find out what x is going to be for this. Okay, so let's start off with drawing it. Remember, it is an increasing graph like that, but there's also something else we know about it. This graph, so we have the parabola, right? And we know what the x value belonging to the turning point of the parabola is. So the thing about that f double prime of x, this graph, you see its x-intercept. It's going to have the same x value as the x value of your parabola in the f prime of x. Okay, so these are just stuff that would be in textbooks that you have to study first to remember. So we can go ahead and draw this straight line graph. So that graph, the f double prime of x, is going to be a straight line, and its x-intercept is going to be that negative 1.35 that we found. So I'm actually going to put that point down so that we don't forget. That's that negative 1.35. Then the x-intercept is going to just be a line that will pass that point on the x-axis. Okay, so this is what this graph is going to look like. F double prime of x is going to be a straight line that is increasing because the parabola is concave up, and its x-intercept is going to be that negative 1.35, which is also the x value of your parabola's turning point. Okay, so the question there, so now that we have that graph drawn down, let's figure out what they want. They want where f prime of x multiplied by f double prime of x gives us something less than or equal to 0. Okay, so if I'm going to actually put them in their colors, remember that this graph was pink and that one was blue. Okay, so to find this, really what we're looking for is this. So we're saying when we multiply, and just remember when we're saying f prime of x, it refers to the y values of this graph and the y values of this graph. So this is the parabola and this is the straight line. Where do you take the y values of this and you multiply to the y values of that, and it gives you something less than or equal to 0? This is only possible if the y values of this graph is positive, and we multiply it by the y values of this graph, which would be negative. Then you would get something that is less than 0. Okay, so I'm speaking about the less than 0 first. We will also look at the equal to 0. Now, another way this could have happened is if the y values of this graph was negative, and we multiplied it by the y values of this graph, which was positive, then we will also get something that will be less than 0 or negative. That's what less than 0 would refer to. But we also have to watch out for where we will multiply these values and they would give us 0. Okay, this will only be possible if, for example, the y values of that was 0 multiplied by the y values of this one, and let's say that was either positive or negative. It doesn't matter, because if you multiply 0 by either a positive or negative number, you're still going to end up with 0. Okay, so that would be the equal to 0 part. We could also have a situation where this graph could either have positive or negative values and multiply by this graph, which has a value of 0, a y value of 0, then we would also get 0. So this is really what we are looking for on the graph, and you'll see how we're going to try and find it. Okay, so here's the graph. I've decided to put the requirements here on the side. So we are going to concentrate on f prime of x and f double prime of x. So just the pink and the blue graph. And since this is the last graph, I know that you're supposed to still, of course, have that cubic function, but just to avoid any confusions, I'm going to erase the cubic function. And let's just work with it like this, because this will just make more sense. Now we can just focus only on these ones. Okay, so this is what this graph looks like now. So I'm erasing everything about the cubic function because I don't really see a need of leaving this here, since that is the last question. Okay. So that is the last question for this section. Okay, so this is what we can do here. So first we're looking for where are the y values of the pink graph going to be positive. The y values are positive here. So remember, this is the y-axis. This is the positive part of the y-axis. That's the negative part. So notice the negative part is below the x-axis. The positive part is above the x-axis. So you're only going to look for parts of the pink graph that lies above the x-axis, since we're looking for where that is positive. And the parts of the pink graph that lie above the x-axis would be here. So here, that is above the x-axis. But we need to find at the same time, okay, for the same x values, the blue graph needs to also be negative, okay? So it needs to be for the same x values. So I notice that it starts becoming positive here after this point. So when we go like to the left of this point, you see that these have positive y values. Okay, the pink graph has positive y values. If I look at that, the blue graph for this same x values, I will also have to I will look at it in a vertical line like that, because this point on the blue graph, the x value is exactly here, is also negative 3.4. So if these are the points that belong to the highlighted part of the graph, so these x values, let's also see where they belong to on this blue graph. These same x values, if you extend this down, look at where it is. You see this blue graph has a negative y value. And for the same x value, the pink graph has a positive y value. And that's what we want. We want where the pink graphs have positive y values, and at the same time, or for the same x values, the blue graphs have negative y values. And this is happening over here. So you see here, same x value at this point over here, it has a positive y value. And if you look at it for the same x values for the blue graph, it has a negative y value. That's what we're looking for. So you see it happens all the way here. So let's mark this point. Now, the reason I cannot take beyond this is because of this. If you go beyond this, you see the blue graph? Yeah, it's sure it has negative y values. But the pink graph at those specific points, at that same x value, you see it doesn't have a positive y value. The pink graph has a negative y value here. And for the same x value, the blue graph has a negative. That's not what we're looking for. We're not looking for where the pink is negative and the blue is negative. The pink graph needs to have positive y values. So we cannot take anything that goes past this line here. Meaning these x values are only values that are less than negative 3.4, because you see they are moving to the left of negative 3.4. There's nothing on the right. It's not working on the right here. Okay, so that's the first solution we have. We can go ahead and say this one, that part worked where x was less than negative 3.4. Okay, now we cannot just assume that this is the only place that it happened. We also have to check through the rest of the graph. So if we look on this part of the graph, and the reason I'm choosing this wing is because I want where the pink graph has positive y values, meaning it needs to be above the x-axis. Here it has positive y values. Here it does not have positive y values. That is below the x-axis. So I'm taking only this part of this graph. Let me see. Does the blue graph for the same x values also have negative y values? So if you look at that, you see this part of the graph. I'm trying to see, okay, let me line this up vertically to the blue graph as well. If we start moving towards this side where this graph is positive, where it has positive y values, move in the same direction for the blue graph, you see that this blue graph has positive y values as well. So that's not going to work. We cannot have where the pink graph has positive y values and the blue graph has positive, because that's not the requirement. The blue needs to have negative. So it's not working anywhere else here. Okay, so it just means that this first requirement has been met where this is positive and this is negative. That works out. Okay, and it only works here for now. Now, let's also consider the zeros because that's also important. Remember, we are also looking for places where if you take the y value of this one and you multiply to that, it gives you 0. Meaning this graph, if its y value is 0, which is here at the x-axis, okay, at this x-intercept, this pink graph has a y value of 0. If you multiply it to the y value at the same x value, okay, of the blue graph, it should give you a 0, because 0 multiplied by this y value, which is negative, will give you 0. So it means that in this case, negative 3.4 is also an included point. So I can't just say x is just smaller than negative 3.4. It's smaller or equal to negative 3.4. Because of that, equal to 0 as well. Okay, so it's really just multiplying the y values of the graph. The pink graph's y value is 0. If you multiply it by the blue graph's y value at that same x value, the blue graph's y value is negative. So 0 multiplied by whatever negative number that is will give you 0. So that's why I have to say this here. Okay, so that means all through I didn't really find any other place that it worked. Okay, so long we are done with that first requirement. Now let's look for where the y values of this pink graph is going to be negative and the y values of the straight line graph will be positive. Okay. So where are the y values of the pink graph negative? That happens below the x-axis. Now, the thing is, at the same time, the y values of the straight line graph must be positive. So I'm only going to look for those places. So over here, this part, the reason I will not take this is because, yes, this part may have y values that are negative. But you also have to look at the y values of this straight line. So you see over here, like just a point over here, it has a negative y value on the pink graph. But on the blue graph, that same point for the same x value, it has a negative. So I cannot take that, okay, because that's negative and negative. I need to look for negative and positive. So if I keep going on this graph, you see that as you keep going like downwards, moving from left to right, it's still negative all through here. But this graph as well is also still having negative y values. So I keep moving down. I even get to here And I see I still have a negative y value here, but for the same x value, this graph also needs to be positive. Okay, but it's negative, so it's not working until we get here to this point. You see, at this point, this y value of this graph is 0. So the y value of the blue graph is 0. And if you multiply it by the y value of this graph, okay, the pink graph, it's a negative number. And if you multiply those y values, they give you 0. So since this is one of the requirements, I have to take this. So I have to take this point where x is equal to negative 3.5. But before taking it, let me just check if we also meet one of these requirements, this one, the negative and the positive. So over here, you see that this graph has negative y values, negative, negative, and all of that. But for the same x values, this graph needs to have positive y values, which you can see is working here. A negative y value for the pink graph. And if you line it up to the x-axis and past that, you see that this graph has a positive y value. So it starts to happen from this point, negative 3.5, moving towards the right. It keeps working, okay, until this point here. Because now, here we still have the pink graph having a negative y value and the blue graph having a positive y value, which is what we're looking for, until you get to this point over here. So when we reach this point, you see that the pink graph's y value is 0 because this is an x-intercept. And the blue graph's y value is going to be positive. So if you take that 0 multiplied by whatever positive number that is, that will be 0, which is one of the requirements. When we multiply the y values, we should also get 0. So it means that it's working everywhere in between here. So it means that x is either greater than, so it's moving towards this side, or equal to negative 1.35, but less than or equal to, I also have to say equal to 0.7. Okay, so that is what we have there. These would be our two solutions. Okay, so we're saying it's either that x is less than or equal to the negative 3.4, or x is greater than or equal to negative 1.35, but less than or equal to 0.7. Okay, so this is our answer for this. So that is it for question 8, and then we move on to question 9. Okay, question 9. So question 9 says a wire 12 meters long is cut in 2 pieces. One part is bent to form an equilateral triangle and the other a square. Okay, so an equilateral triangle, all the sides are equal. A side of the triangle has a length of 2x meters. And 9.1, they want you to write down the length of a side of the square in terms of x. Okay, so since they say a wire which is 12 meters long, okay, so 12 meters long, we have this wire. And the full length of it is 12 meters. But then they say it's cut into 2 pieces. So not half, just 2 pieces. And one part is bent to form an equilateral triangle. Okay, so since this line is being cut into 2 parts, I'm going to just call it like it's being cut into 2 parts. I'll call this part A and I'll call this part B. So, okay, it's cut into 2 parts and then one part of it is bent to form an equilateral triangle. So let's say that was the part A that was bent to form an equilateral triangle. So out of that, we form an equilateral triangle, just knowing that all the sides in this triangle are equal. And then they say, and the other a square. So the other part is bent to form a square. So that would be the length of B. Okay, so I'm going to go ahead and draw a square, and that is B. And in a square, all the sides are equal. Okay, then they say that a side of the triangle has a length of 2x meters. So one of the sides has 2x meters. So it means everything else is also 2x meters because all the sides of a triangle are equal. So the whole point of this is to write down a side of the square in terms of x. So we need to find one of these sides, but it needs to be in terms of x. Okay, since it needs to be in terms of x and the only thing that has x in it is the triangle, we start from here. So since this entire wire, everything here, right, is made up of this one part, which I've called A. It's made up of that one part. So let's find the formula for A. So we can say that A, the value of A, that length of that wire, can be the entire 12 meters minus the length of B. So that is 12 minus the B. Okay, so that's what A is. So since A is the entire wire, let's put it in terms of X. Since all of these lines are equal, these sides are equal, it means this is 2x and this is also 2x. So if we're calculating the length of the entire wire in terms of x of this triangle, it's going to be the 2x plus the 2x plus the 2x, which will give you a 6x. So that's the length of A. That is that piece of wire, that's A. So I can say that 6x is equal to 12 minus B. So because I want to name this one in terms of x, it would not make sense to try and make x the subject here. Rather, I'm going to make B the subject, and then I'll be able to name that in terms of x, since the entire length of this part is B, and that's what is used to make this square. So we can take B over to the left-hand side and it becomes positive. It's equal to, and we still have the 12 here, and we're taking the 6x over, so minus the 6x. Okay, so B is equal to 12 minus 6x. But B happens to be the entire length of this square. Okay, so I'm saying that B is the entire length of this square. So that is that 12 minus 6x. Okay, that is everything here. And since each side, all the sides in the square are equal, to just find one of the sides, if this is the entire length of it, I just have to divide this entire length by 4, and it will give me the length of one of the sides of this square. In a way, we can look at it like this. Since B is the entire length of this wire and it's the entire length of this square, that's like looking at the perimeter of the square. And the formula for perimeter of a square would be 4 multiplied by S, because whatever the side is, you just multiply that by 4 and that will give you the entire perimeter, since all the sides are equal and there are 4 sides. So if 4s is equal to 12 minus 6x, remember we just want to find the length of a side. We just want to find s, one of the sides of the square. So we can divide both sides of the equation by 4 to find s. And so one of the sides of this square would be this. So I'll just divide. 12 divided by 4 is 3. Negative 6 divided by 4. So if you say negative 6 over 4, it simplifies to, I'll leave it as a fraction, minus 3 over 2. And we have x as well. Okay, so that is one of the sides of this square in terms of x. So it means that one of the side is equal to 3 minus 3 over 2x. Okay, so that's the first question. Moving on to the next question. Then question 9.2 says, if the square is now used as the base of a rectangular prism with a height of 4x meters, determine the maximum volume of the rectangular prism. Okay, so we have to find the maximum volume. Okay, so if this square is going to be used as the base of a rectangular prism. Remember, rectangular prism kind of looks something like this. Okay, so it can be something like this, a rectangular prism. And so they're saying that the square is now being used as the base of the rectangular prism. So the square that we had, one of the sides of it, so each side is equal to 3 minus 3 over 2x. So it means that this as well would also be like that. We have all the sides being equal because the base is a square, and one of the sides is just 3 minus 3 over 2x. Then they also tell us about the height. Okay, they tell us that the height of this rectangular prism is 4x meters. So you can kind of imagine it as if it's standing up. This part over here would be the height of it. That's how high it is. So that is 4x meters. Okay, so we have to determine the maximum volume of the rectangular prism. To find the volume of it, the formula for volume is equal to, of a prism, would be the area of the base multiplied by the height. That's how you'll be able to find out how much space is filled up in this entire object. So the area of the base, remember the base is a square. To find the area of a square, you just say the side multiplied by the side, which is really just side squared. And then we have to say that's the area of the base parts, then multiply by the height. We know that one side is equal to 3 minus 3 over 2x. So we have that 3 minus 3 over 2x, and that side needs to be squared, so all squared. And then we'll multiply that by the height, which is 4x. So multiply by 4x. Okay, so this would be the volume. Then we still have to find the maximum volume after that. So let's go ahead and find just the equation of the volume of this. So to simplify this, remember this is a binomial being squared. Just square the first term. That's going to give you 9. Then you multiply the first term by the second term. So that is 3 multiplied by negative 3 over 2. So negative 3 over 2. Then you see that answer that you get, you're going to take that and multiply it by 2. Okay, you could do it the usual way of creating two brackets and foiling out, but that takes long. So then that will give you a negative 9x. Okay, because when we multiply this times this, that becomes that negative 3 over 2x. Then when you multiply by 2, it becomes a negative 9x. Then lastly, you square the last term. So if you take this and you square it, first of all, it's going to become positive. Then the 3 is going to be squared and give you 9 over the 2 being squared gives you 4. And the x being squared gives you x squared. And all of this is being multiplied. Okay, so multiplied by 4x. We multiply by 4x. Okay, so I'm just going to rewrite it like this instead. So I'm writing the 4x in front because since it's only one term and it's being multiplied by all of this by, let me put it in the order of its exponents. Since this has x squared, I'm going to write it first. So I'm going to say it's a positive 9 over 4x squared. And then we have the negative 9x. And then we have the plus 9. Okay, so this is going to multiply in. So we're multiplying these in. And what we're going to get is, you can use the calculator here just to be careful. So 4 multiplied by the 9 over 4. So 9 over 4x squared, it gives us a 9. So we have 9. And this x times the x gives you x cubed. Then it's the 4x multiplied by the negative 9x. So what is 4x multiplied by negative 9? Okay, negative 36. And so x times x will give you x squared. Then we have again a 4x multiplied by a positive 9. That will be positive 36x. Okay, so this is the formula for the volume of this shape. But now we just have to find out, they ask for the maximum volume itself. So they're not just asking for you to determine the value of x for which is going to be a maximum. They want the maximum volume. So first we're going to find out at which x value will this have a maximum, okay, volume. So let's go ahead and do that. And the way we'll do that is just remember that looking at the way this formula looks, it has 9x cubed. This is going to be a cubic function. And the coefficient of x cubed is 9. So that is a positive number, meaning your graph is going to look like that. Something like that. Okay. And so we can go ahead and find, what we're trying to find is the maximum value itself. So it has a local maximum and a local minimum. We're looking for this one, the local maximum, and specifically its y value. So let's find its x value first. So since this is the formula of it, to find that y maximum, that maximum value, since it's a turning point, we're going to derive this so that we're really finding the gradient, okay? So the gradient of this graph, but specifically where the gradient is equal to 0, because the gradient is always equal to 0 at the turning point. So let's derive this. 9 times 3, so 9 multiplied by 3, that gives you 27. So 27x, and then take out a 1 from the 3 squared. Then negative 36 times 2, that is negative 72x. And so take out a 1 from that, it gives you 1, but we don't have to write that. Then plus 36, and that x falls away because it becomes a 1. So this is the gradient of this function that we had, the volume of that. Now we just have to make that gradient equal to 0 because that will help us to find the turning points. Only at the turning points are the gradients equal to 0. So we have 27x squared minus 72x plus 36. Then, if we look at all these numbers, we have to factorize this. All of these numbers, let's just see what can go into everything here. So 27 divided by 3, okay, is 9. 72 divided by 3 is 24. 9 and 24 already have something in common. They have 3 in common, so it means there's a bigger factor we can divide by. Let's try 27 divided by 9. Okay, it's 3. 72 divided by 9 It's 8. Okay, so I know 3 and 8 have nothing in common. So that means we can divide both sides by 9. 9 can definitely go into all these numbers. So if we have 0 is equal to 27x squared divided by 9, that is 3x squared. 72 divided by 9, that's minus 8x. And then 36 divided by 9, I think that's 4. 36 divided by 9, yeah, okay. So positive 4. Okay, so that's what we have. Okay, then you have to factorize this. So I'm going to use the factorizing method. You can use the quadratic formula if you want to. So we're going to open up 2 brackets, and because there's a coefficient here, you cannot factorize it normally. I'm going to use the cross method. So I'm saying 3x and x, and then I need, so that's the factors of 3x squared. Then I need factors of 4, but once that will help me get an 8 in the middle. The fact that the middle is the only negative one, you should know already that both terms will be negative. Okay, so I have a negative and a negative. I would have tried 4 and 1, but this doesn't seem to help to give an 8 in the middle, because that will give you negative 3, and that's negative 4, and that's negative 7. That doesn't give you negative 8. So I'm going to try 2 and 2. Okay, so 3x multiplied by negative 2, that's negative 6x. And then x multiplied by negative 2, that is negative 2x. Okay, so that gives you negative 6x minus 2x, negative 8x, and that is the middle term. So these are our factors. It's 3x minus 2 and x minus 2. Okay, so that's what we have. So solving for x, we're saying 3x minus 2 is equal to 0, or we have x minus 2 being equal to 0. 3x is equal to, take the negative 2 over, divide both sides by 3, and x is equal to 2 over 3. Or it is where x is equal to taking that over 2. Okay, so we have 2 solutions here, and we have to now decide which one is going to be the one that belongs to the maximum turning point. The way you can decide that is knowing the shape of your graph. Okay, the shape of our graph looks like this because it's a cubic function and a is positive. So since it looks like this, then it means that this here is your maximum. And if you're looking at this on a Cartesian plane, then it would mean that the x value belonging to the maximum is the smaller x value. So we have to take this one, this 2 over 3. That would be the maximum. Then the bigger x value is 2. That would be the minimum, the local minimum. Okay, so we know it's this one. So since x is equal to 2 over 3, to find the actual maximum, okay, that maximum volume, you're going to take this x value belonging to that maximum y value and substitute it into the original equation of this cubic function so that you can find out what that y value is. So the original equation is this volume right here. So we're taking the original equation and we're going to substitute 2 over 3 because it's the x value that belongs to that maximum y value. So v, and we're subbing 2 over 3 in there, is equal to 9 bracket 2 over 3 all cubed minus 36 open bracket 2 over 3 all squared plus 36 open bracket 2 over 3. And you can go ahead and put this onto the calculator and let's see what we get. And the answer we get is that 32 over 3. But because it's volume, I'm not going to really call it just 32 over 3. I'll put it in decimal form and round off to 2 decimals. So it is this 10.66. So we can just round off to 2 decimals. That volume of that is going to be 10.67, and because it's in volume, okay, it's going to be meters cubed. Remember, these dimensions were in meters, so that is 10.67 meters cubed. That is the maximum. So you can conclude and say the maximum volume is that answer, okay, of the rectangular prism. So the maximum volume of the rectangular prism is 10.67 meters cubed. And that is our final answer in question 10. And now we're on question 7. And 7.1 says we have to determine f prime of x from first principles if f of x is equal to negative 2x squared minus 1. Okay, So since you have to do it from first principles, you can actually just find the answer first so that you know what your answer needs to look like. If we derive this using the rule of differentiation, we will say f prime of x is equal to the negative 2 times the 2 is negative 4. Then we have x minus 1, which is 1. We don't have to write the 1. And then we have a constant. It falls away. So you know that this should be your answer. Okay, so when deriving this from first principles, you can start with this formula, the f of x plus h. Let's find out what that is equal to. We already know what f of x is. So this just means that whenever you see x, replace it with x plus h. So this is going to be equal to, we have the negative 2, there's an x, so replace it with x plus h. Then we have a squared, so all squared minus 1. Okay, so simplify this further, it's negative 2. Then we have to square this. So it's two brackets being multiplied by each other. So square the first term, that's x squared. Then square the last term, that's plus h squared. Then the first term times the second term, that's going to be xh. Then times that by 2. So that is positive 2xh. Okay, then minus 1. So this is what we have. And then remember, it's a closed bracket here because this still needs to FOIL in. Then we're multiplying in the negative 2 into these three terms here. And so we will have negative 2x squared minus 4xh minus 2h squared minus 1. And that is your f of x plus h. So the formula to calculate the derivative of this from first principles is f prime of x is equal to the limit as h approaches 0, and then we have f of x plus h minus f of x all over h. So this is equal to the limit, again, as h approaches 0, and we have f of x plus h, which is all of this. So put that in carefully. Remember, this is like 5 marks. That's really a place where you can score marks. So minus 4xh minus 2h squared minus 1. Then we're saying minus, and remember you're subtracting it by something that has more than one term, so you need to put brackets. So minus, open a bracket, and we're going to say minus negative 2x squared minus 1 all over h. Then we have is equal to the limit as h approaches 0. We'll repeat everything that we have there. Just make sure to be careful as you write everything down. And then this negative is going to multiply into that. And so we have now a positive 2x squared, and we have a positive 1 all over h. Now the thing about this is things are going to cancel here, and you don't have to really just search. You know that what you subtracted by, that's the only thing that's going to cancel. Okay, so if you have a positive 2x squared here, it will cancel with a negative 2x squared. If you have a positive 1, then there must be a negative 1. So the positive 1 cancels with negative 1. They just become 0. So long we just have, again, the limit as h tends towards 0. We keep writing this until we substitute. So negative 4xh minus 2h squared. That's all we have here. Okay. And then all over h. Then we have to take h out as a common factor. So we still have the limit as h approaches towards 0, and you only take it out so that it can cancel and you don't get to substitute 0 into here because that will make it undefined. So to find out what is here, it's like saying, what do you multiply to h to get back to negative 4xh? Or you could just say this, negative 4xh divided by h. H's will cancel, you're left with negative 4x. Same thing here, this divided by the h. One of the h's would cancel here and you'll be left with negative 2h all over the h. Okay, so here's your h's cancelled in, and then I'm going to just substitute already. So I don't want to rewrite that again. I'm saying negative 4x minus 2, and in place of h, I'm going to put 0. So f prime of x is going to be equal to, this times 0 just stays 0, so negative 4x. And as you can see, we got the same answer using the rule. Okay, so that is 5 marks. So 7.2, we have to determine 7.2.1 f prime of x if it is given that f of x is equal to this. So we just have to derive this. This is already ready to be derived. So f prime of x is equal to, we're saying the negative 2 times the 3, negative 6, and then x to the power of 3, then you have to take out a 1 from the exponent. So that's going to be squared. And then you have the positive 3 as the coefficient times the exponent of 2. That gives you a positive 6. And then you have x to the power of the 2 minus 1, which of course gives you a 1, but you don't have to write that 1. Okay, so when we derive that, that's all we get. And that is for 2 marks. Okay. So 7.2.2, we have to determine the derivative if y is equal to 2x plus 1 over the square root of 4x. So sometimes you have to make sure that the equation or the function that you're going to derive is ready to be derived. You see, in this one, you have a square root. Now, the square root is not necessarily a problem. If you just had square root of 4, it's not a problem. The problem is the fact that x is in the third. X should not be in the third, and it also shouldn't be on the denominator. Okay, so we're going to have to fix that first. So we just have y is equal to 2x plus the 1 over the square root of 4x. Okay, so the square root of 4 can be square rooted. So we can simplify that. So this is very different from something like this. If you had 4 plus x, you can't square root this because you cannot square root across terms like that. But this 4 and the x are being multiplied, so we can. So we can have y is equal to 2x, then plus 1 over, the square root of 4 is 2. But the square root of x is still the square root of x. So this is what we're going to have, 2 square root x. And then now the new problem is the fact that this is still on the denominator and it's also a third. So let's first change it to not be a third anymore. So we will just say y is equal to 2x plus 1 over, then we have the 2. Now the x, this is what's actually going on here. It's a square root. So here, the exponent that we have here, it's actually a square, just like when you have cube root. Okay, it's a 3 there. So there's an invisible 2 here. And in front of every number and variable, there's a natural exponent of 1. So we can actually rewrite this like this. We can say x, and then we're going to raise it to the power of, you always say the inside exponent over the outside exponent. So that is 1 over the 2. So that's how we can rewrite that. And then now the new problem is that the x is still on the denominator. We need to take it to the numerator. But when you take it to the numerator, it's going to cause its exponent to become negative. Okay, so we have y is equal to 2x plus, and so now I'm moving this x to the numerator. 1 is kind of like standing as a placeholder here. Because there's already going to be an x on the top, I don't have to rewrite the 1. That's like saying 1x. There's no need to say that. So we have x to the power of, that half now becomes negative a half, and we have over 2. Okay, now in this case, I'm actually going to leave this 1 here. The reason why is because we need to have a number here. So that 1 in front of the x, I'm actually going to leave it here. So we have a 1 in front of the x, and this is the reason why. So I'm going to say y is equal to, we have 2x, then plus, and I will rewrite this like this. We say 1 over 2, and then we have x to the power of negative a half. See it like this. The 1 and the x to the power of negative a half are being multiplied. You could move this away and let the 1 carry the denominator of 2. Because this is just a separated form of this. We could have just said, if we said x to the power of negative a half and we put this over 1, you see the fact that these two are next to each other, they're actually being multiplied. So if you wanted to get it back to this point, you multiply the numerator and the numerator, which would give you that, and then the denominator and the denominator, which would give you the 2. Okay, so we can actually just write it like this. And now this is ready to be derived. So we'll say dy over dx is equal to, and so let's derive this. It's the coefficient times the exponent. There is a natural exponent of 1 on top of the x. So it's going to multiply by that. And so you have 2 times 1, which is 2. Then we have x to the power of this 1 already that is already there. But then you have to subtract 1 from the exponent. So minus 1, which would give you a 0. And anything, so it's x to the power of 0. Anything to the power of 0 gives you 1. And 2 multiplied by 1 just gives you the 2. So that just stays 2. Then we come to this part. It's the positive half as the coefficient multiplied by a negative a half. And that will give you negative 1 over 4. Okay, you can be using the calculator for this. Then we have x to the power of, we still have our exponent, and we're going to subtract 1 from it. So 1 can look like, you can also just calculate that on the calculator. So 1 can be written as 2 over 2. I'm just writing it in a way that the denominators are the same. So dy over dx is equal to 2 minus 1 over 4 x to the power of, so I'm saying negative 1 minus 2, which is negative 3, over, and then the denominators stay the same because we are subtracting. When you're adding or subtracting, your denominators must stay the same. So over 2. Then lastly, you can just write this in a way that the exponent is positive. So this is just dy over dx is equal to 2, then minus. Remember that this x is actually on top. It's on the numerator. So we need to take it to the denominator so that its exponent will be positive. So we have 1 over, the 1 is still there, 4, and then the x comes here now. And then the exponent is now positive 3 over 2. So this is the derived form of that function that we had. Okay, so that is 7.2.2. Then 7.3 says the graph y is equal to f prime of x. Okay, so this is already a derived graph. Has a minimum turning point at 1 and negative 3. Determine the values of x for which f is concave down. Okay, so the fact that they're saying y is equal to f prime of x, that derived graph already, has a minimum turning point. When you're thinking about something that has a minimum turning point, we can imagine a parabola that is concave up. This will have a minimum turning point. So if this is the equation of y, okay, because this is the y is equal to f prime of x, this is the graph that has been derived already. So if this is the derived form of this graph, okay, this is f prime of x, then the original graph must have been a cubic function with the a value being greater than 0. Okay, so you have to think about it like this. The cubic function, the equation of it looks like this. Ax cubed plus bx squared plus cx plus d. If you derive this, okay, so y prime, if you derive this, you're going to get this a, because if a is greater than 0, it's going to look like an n, okay, a capital letter N, looking like this, okay, but just more curved. So that's how it looks. And so if you derive this, you're going to get a parabola. So you have to think about it like this. This 3 is already positive, and you have to multiply it by the coefficient of x. If this is positive and you're multiplying it by a positive, then this 3a, this value, is a positive number. So you have now x squared. Then, of course, the b times the 2 will give you plus 2bx and 2bx. And then you have 2 minus 1, which is, of course, 1. Then you would have plus c, and the d would fall away because it's a constant. It doesn't have x in it. So you see, this would be the equation of a parabola. And you can see that the coefficient of x squared is positive. 3a is positive because a was positive and 3 was a positive number, and they multiplied. So it will create a concave up parabola. So that's what I'm saying. The only way we can have this kind of graph, if this is f prime of x, it must mean that the original graph is a cubic function that has the a value being greater than 0, meaning it looks like this. Okay, just also remember, if a value is less than 0 in a cubic function, the graph will just be like a backwards n, okay, but more curved. Okay. Now, I don't really need this part. I was just trying to explain that and where that comes from. So they're saying if we have this graph, that f prime of x, that y is equal to that, it has a minimum turning point at 1 and negative 3. So 1 and negative 3 is the minimum turning point. This is f prime of x's minimum turning point. Okay, then the question is you need to determine the values of x for which f is concave up. The blue one would be a graph of f. That's the original one. That's the derived one. So where is it concave up? For you to find out how it's concave, you need to know what the point of inflection is. Okay, just also remember when we're looking for concave down, so here, this part would be concave down, that is curved downwards. And then this part would be concave up. Okay, it's like a parabola, like we have a concave down parabola and a concave up one. So we're also looking at that here. But we need the point of inflection to be able to find out for which x value this thing would be concave down, because we need to take this blue part. This is concave down. So with this, you have to remember that if we have a cubic function and we derive that cubic function and it gives us the parabola, this turning point, the x value of the turning point, is also going to be the x value of your point of inflection. Okay, so the point of inflection's x value is also 1. So we just have to find out where is it concave down. So the highlighted part in blue, that's where it's concave down. Okay, starting from whatever x value this is, and we know now it's 1. So imagine you had a y-axis. Okay, and for the sake of this, I'm just going to get rid of that. I don't really need that part. So we want to find out where's the concave down. So it's concave down all through here. If this x value, the point of inflection's x value, is 1. And then these are all the places that it's concave down after 1. So here, moving to the left, you see, look at all the points for which this graph is concave down. All of these points are concave down, and look at the x values. They are values that are what than 1. These are values that are less than 1. That would be the value of x for which it's concave down. So you can conclude and say that x needs to be less than 1. Okay, so that is 7.3, and that's the last question in question 7. Okay, so we're on question 8, and question 8 says, given f of x is equal to x cubed plus 4x squared minus 7x minus 10, we have to write down the y-intercept of f. Okay, so when we have to find the y-intercept, just remember that you only have to just make x equal to 0. But there's an easy way to see the y-intercept. So remember that this cubic function is in standard form. And so the y-intercept will be the last number without a variable in it. So that would be d. That is your y-intercept in the cubic function. So the y-intercept is where y is equal to negative 10. As a coordinate, the x value is 0 and the y value is negative 10. So you can also go ahead and make x equal to 0 and substitute in place of x 0. You will get negative 10. Okay, moving on to the next question. They want you to show that 2 is a root of the equation f of x is equal to 0. Okay, so for 2 to be a root, meaning it is an x-intercept, it really just means that if you take this, you have to take 2 as an x value. And if you substitute it into the equation of f, it should give you 0 as your y value. So that will prove that it is a root. So I'm going to take the function of f of x and I'm going to substitute in place of x. I'm going to substitute 2. And it's equal to 2 all cubed plus 4 multiplied by 2 all squared minus 7 multiplied by 2 minus 10. Okay, and you can go ahead and put that into the calculator and see what you get. And when we put that into the calculator, you see you get 0. So I guess here you're just getting a mark for substitution and for your answer. Okay, then moving on to the next question. 8.3 says, hence factorize f of x completely. Okay, so since we know that 2 is a root, we have to factorize f completely. So the fact that they told us that 2 is a root, it helps us to factorize. Okay, so this is the equation of f of x. So the method we're going to use to factorize this is synthetic division. Now, when using synthetic division to factorize, first you're going to focus on the constant in this function. So we have negative 10 as the constant, being the only number without a variable. So we look at that constant and we take factors of that constant. So the factors of negative 10 would be things like negative 1 and 1, negative 2 and 2, 5 and negative 5 as well, right? But we don't have to do this anymore because the whole point of doing this is so that you can take these numbers, these factors of negative 10, and substitute it into the equation, okay, into the function, and the one that gives you 0 is your root, and we use that number in our synthetic division. But we don't have to do all of that because we already know they told us that 2 was a root. So we already know which number here will work. It's 2 that's going to work as one of the factors of negative 10. These aren't all the factors of negative 10, by the way. So since we already know that, it means we can skip that step. We know that 2 is a root. Okay, so this is how we're going to use it. We're going to put 2 on the right hand side, and then we're going to draw a capital letter L, but we're going to draw it backwards. So a backwards L, which would look like that. Okay, and then after we have drawn that, now you're going to look at all the coefficients in f of x, all the coefficients of everything here. So the coefficient of x cubed is a 1. So we're going to put 1 here. Then the coefficient of 4x squared is that positive 4. So we'll put a positive 4 here. And then, of course, the coefficient of x is negative 7. So we have minus 7. And lastly, we have the negative 10. Okay, then the first thing you do is, you see this 1, you drag down the 1. Then we're going to say 1 multiplied by 2, which gives you 2. And we put that answer on top of here. Then 2 plus the 4. Okay, we take whatever sign is here. That is 6. Then again, 6 multiplied by 2, which is 12. Then 12 minus 7, that gives you 5. Then 5 again multiplied by 2 gives you 10. And lastly, 10 minus 10 is 0. And this is one thing, you should always end with 0. If you didn't end with 0, it means you must have miscalculated somewhere. So just always make sure you end with 0. Okay, so this is how it's factorized. Remember that 2 was already a root. So if we're factorizing f of x as it is, if 2 is a root, so it just means that when you were simplifying, when you said f of x is equal to 0, 2 was one of your solutions, meaning x was equal to 2. But now we need to see what the factor was. So to find the factor, it's like taking the 2 over the equal to sign. And so the factor is actually x minus 2. So x minus 2 is a factor, but x is equal to 2 is one of your roots. So we're going to put, this is the first factor we have, x minus 2. And then to find the other factors, we are going to use the coefficients of these numbers that we found here. And how we use them is like this. 1 is the coefficient of x squared. 6 will be the coefficient of x. And 5 will be your constant, the number without a variable in it. So when we write down these factors, it's really 1x squared, but we don't have to write the 1. It's just the x squared. And then we have a 6x, so it's positive. So it's a positive 6x and then a positive 5, so plus 5. And that is our second factors. Okay, so we still have to factorize this part further. So that would be f of x is equal to, then we have x minus 2. And then we factorize this. So open up 2 brackets and we're going to have x multiplied by x is what gives you x squared. Then we have to ask ourselves, what multiplied by what will give us a positive 5, but that can help to give us a positive 6 in the middle. Also notice everything is positive. So factors of 5 would be positive 1 times positive 5. That would give you the positive 5. And of course, if you see you have positive 1 plus 5, it would give you the 6 in the middle. Okay, so these are our factors and now it is factorized fully. Okay, so that is for 3 marks. That's what you get for 3 marks. Then moving on to the next question, 8.4. If it is further given that the coordinates of the turning points are approximately at 0.7 and negative 12.6, and then this as well, negative 3.4 and 20.8, draw a sketch of the graph of f and label all intercepts and turning points. Okay, so they gave us turning points. They gave us the stationary points or our turning points. So we know what those are. Now we can just go ahead and put down our intercepts. Okay, so we have that f of x being factorized, but we just have to find the x-intercepts of this. So to find the x-intercepts, you're going to make y equal to 0. So make that equal to 0. So really what you have is 0 is equal to, and then you have x minus 2, bracket x plus 1, bracket x plus 5. And it works with the same logic as quadratic equations. You're saying something times something times something gives you 0. So we're going to say either this first bracket is equal to 0. Therefore, we're saying that either x is equal to 2 or x is equal to negative 1 or x is equal to, take the 5 over, negative 5. So those would be our x-intercepts. Okay, Then also to find the y-intercept. So you can put it as coordinates as well, just to remind yourself. That's 2 and 0. This one will be -1 and 0. This one is -5 and 0. Okay, the y-intercept, we already have that. So the y-intercept is this over here, 0 and -10. So we can also just put that down. Our y-intercept is 0 and -10. And then, of course, they give us the stationary points. Okay, so one thing about this graph is, apart from the stationary points and all the intercepts, you have to know the shape of the graph. So the shape of this graph, since the equation of it is x cubed plus, and then this keeps going on. But remember, we have x cubed, meaning the coefficient of x cubed is 1. It's a positive one. So it means that a is greater than 0. And when a is greater than 0, your graph is going to form a capital letter N, but it's just going to be a more curved one. Okay, so to draw this graph, we already know the shape of the graph. So what I'm going to do is I'll just put, I don't know where the x and the y axis is yet. What I would actually do is draw the graph. I know what it looks like. It looks like this. So that's what I'll do first. And then now we can start figuring out where the other things are. Draw the graph first, then you can draw the x-axis. Okay, now that the x-axis is there, let me just make this line straighter. So there's the x-axis. Now we can just put down the x-intercepts, because that will help us to just know where exactly the y-axis should go based on these numbers here. So the x-intercepts we have is, the smallest one first is -5, then -1, and then 2. Okay, so I'm putting it down like this. I have -5 over here, then I have -1 over here, and then the 2. So from this, you'll be able to see where the y-axis is going to be. Since this is -5, -1, then you know after -1, you should have 0. And when you have 0, that's where your y-axis is going to be. Then, of course, you have the 2. So that's what I'm going to do. I'm going to draw the y-axis just after that -1. So the y-axis can be here. Remember, they don't really care too much about you writing numbers. They just want to see the shape of the graph is right, your intercepts, even the y-intercept as well, and the turning points. Okay, so here's the y-axis, and now I'm going to just go ahead and put down that y-intercept. So the y-intercept was 0 and -10. So 0 and -10. All I have to do is say that it's intersecting here at 0 and -10, or you could even write the -10. You can write it as coordinates, it's fine. So -5 and 0, and we have -1 and 0, we have 2 and 0. Over here we have the 0 and -10. And then, of course, we're going to have the turning points. So the turning points are just going to be the one here and the one there. Also, just look at where the numbers are going to be. You see this one, the x value should be smaller than the x value you're going to have for this one, because this one is more further to the right. So let's see which one has a smaller x value. So we have the 0.7 and the -3.4. So this one definitely is the one that we have here. Okay, so this one's is going to be -3.4 and the 20.8. Okay, so 20.8. 20.8. That's that turning point. And then this one over here is going to be this 0.7 and -12.6. So 0.7 and -12.6. There we go. Okay, so not really perfect, but it's a quicker way to draw the graph, because they really just want to see the shape is right and you have all your intercepts and your turning points. Plus, in the memo, that's usually how it looks. They don't really have numbers in the memo. And of course, because the name of the graph was, the name of the equation of the graph was f of x, we can go ahead and name this graph f. Okay, so that is a method you can use to draw your graph. First, start off with the shape of the graph. Actually draw the graph. So the shape of the graph, whether it looks like that or like that. You can even use this trick for the parabola as well. Works well with the parabola. Secondly, you put down your x-intercepts. Then you're able to find your y-axis based on that. Okay, so y-axis. Then you put down your y-intercept. And lastly, you're able to find your turning points. Okay, so those 4 steps would really help you with sketching the graphs. Okay, next question. So the next question is 8.5. Use your graph to determine the values of x for which f prime of x is less than 0. So when they say an f prime of x, what do they mean? So f prime of x, when you derive a function, what you're finding in that function is the gradient of the function at any point. So when you say f prime of x, it's really speaking about gradient. So this question is really saying, where is the gradient less than 0? Okay, so let's try and understand what positive and negative gradients mean. When you have a line that is doing this, okay, you read functions from the left-hand side all the way to the right-hand side. What is this line doing, moving from the left to the right? You see that this line is increasing. And so when a line is increasing, it means its gradient is positive. Okay, that's what increasing functions do. They increase moving from left to right. And so it means that if you have a line that looks like this, and you again read it from left to right, it means that this line is decreasing. So we're reading it from left to right and you see it's moving down. So the gradient of this graph is negative. That means it is decreasing. Now we do the same thing with curves as well. So we're only just looking for where is the curve, where is the gradient of the curve negative? In other words, where is the curve decreasing? So if we look at this graph, where is it decreasing? So let's just go ahead and check what it is doing throughout. We're going to start from the left-hand side, moving to the right. Over here, reading it from left to right, look at what this part of the graph is doing. It is increasing. Then it reaches the turning point. Now at the turning point, it neither increases nor decreases. And that's why at this point it is stationary. This is a stationary point. And then after the turning point, look at what it starts to do. It starts to decrease. Then it reaches another turning point and it stays stationary, and then it starts to increase. Remember, we're looking for where f prime of x is less than 0. In other words, where is the gradient smaller than 0? Where is it decreasing? And this graph is decreasing here. So all the way through here. And it is decreasing. Okay, so let's find out which x values exactly belong to that part of the graph, because we always have to answer them in terms of x. Okay, so the x value that belongs directly to this point is negative 3.4. Okay, so that's the negative 3.4. And also let's just mark the x value that belongs to this endpoint as well, since it only decreases from here to here. So that is the 0.7. So notice what it's doing. If we line these parts of the highlighted graph to the x-axis, you see that these points are points that are what than negative 3.4. They are points that are greater than negative 3.4. You see, because they are on this side, on the right-hand side of negative 3.4. But what than 0.7? You see that these points, look at where they are. They are on the left-hand side of 0.7, so they are less than 0.7. So this is really how we can write this. We can write this as a single inequality. We're saying that x needs to be greater than negative 3.4. So it needs to be greater than negative 3.4, but less than 0.7, but less than 0.7. And that would be the values of x for which this graph has a negative gradient, or where f prime of x is less than 0. Okay, so that is where x is greater than negative 3.4, but less than 0.7. Okay, moving on to the next question. Then the next question, 8.5.2 says, the gradient of a tangent to f will be a minimum. So we have to determine the values of x for which the gradient, okay, of a tangent to f will be a minimum. Okay, so let's break this down. The gradient of a tangent. Let's just understand what that means. They're really just adding too much words. I feel like this word tangent is unnecessary in this. But just think about it like this. The gradient, okay, of a tangent. When you have a curve and you have a tangent to that curve, so no matter what the curve is, whether it's a parabola or a cubic function, let's say you have a tangent drawn to a curve at a specific point, because tangents only ever touch a curve once. So understand that when they're saying the gradient of a tangent to f, this is what they're saying. The gradient of this line to this graph, okay? The gradient of the tangent to f and the gradient of f at this specific point, they're exactly the same. Okay, they're equal at this point. So if the gradient of a tangent, of this tangent, let's say it's 2, then it means that the gradient of the graph at this point is also 2. So let's just establish that when they're speaking about the gradient of a tangent to f, let's just understand that part as the gradient of a point on f. So since the gradient of the tangent to f is exactly the same thing as saying the gradient at this specific point on f. If it's exactly the same, let's just skip this word tangent and let's actually speak about the gradient of f at a specific point. So if we rewrite this question, this is really what it's saying. So the question is really just, where will the gradient of f at a point be a minimum? And now we can think about what the gradient of f is actually speaking about. Remember that f is a cubic function, right? If we're trying to find the gradient of f, it means you need to derive the graph of f. And if you derive the graph of f, it's going to form a parabola. If this one is positive, if this one, its a value is positive, when you derive this, it's going to form a concave up parabola. Okay, so this would be the derivative of f. In other words, this function represents the gradient of f. So this is what they're actually speaking about. The gradient of f refers to this parabola. The question is, where will this parabola be at a minimum? Or where will this parabola have a minimum value? So you see now, since it's a concave up parabola, it will definitely have a minimum value and not a maximum value. See this, it comes from infinity going down, and then at this point it turns and starts to increase. This would be the lowest point on this parabola. That is the minimum. So the question is, where will this graph be at a minimum? They want you to answer them in terms of x. You just need to find the x value belonging to this minimum point on this parabola. Okay, because the parabola stands for the gradient of f. That's really what it is. So let's find that minimum value. Okay, let's find the x value belonging to that minimum value. We can first of all start by drawing this derivative of f, that parabola. We can draw that graph. So that graph is going to look like this. So when we're drawing this parabola, the thing about this parabola is that we actually know the x-intercepts of it. You see the x value of your turning point, that negative 3.4, is going to be the same x value of your x-intercept of your parabola. And then the other turning point as well, the 0.7, that is also going to be the x value of your x-intercept of your parabola. And remember, your parabola will be concave up because this one, the a value is also positive. So our graph is basically going to look something like this. The parabola is going to go like that and like that. So something like that. Not really a perfect one, but okay, let me try again. So like this, and then moving up like that. Okay, that looks better. So that will be f prime of x. Okay, this is the derivative of that function, that cubic function. And we just have to find its turning point, but not really the full turning point, just the x value of the turning point, because that will tell us where this graph will be at a minimum. Okay, so to find the x value belonging to that turning point, all you have to do is, you see, this is your x-intercept and this is another x-intercept of this graph. That point that we're looking for is going to be exactly in between, halfway in between these 2 points. So we're really going to find the midpoint of these 2 points. And how we can find that is, first of all, it's already on the x-axis. So we already know that it's going to also be on the x-axis. We just need to find its x value. And you can find its x value by using this part of the midpoint formula. We're just going to say x1 plus x2 and divided by 2. So we're taking x1 of this parabola's x-intercept, okay, because it's halfway between these two x-intercepts of the parabola. So we're taking the negative 3.4 and adding it to the 0.7, and then you're going to divide that by 2. That will be the calculation. And so if we do that, let's see what we get. So if we do that, we get negative 1.3. So that is the amount we get negative 1.35. Okay, so that point where x is equal to negative 1.35, that will be where this graph will be at a minimum. And therefore, that is where the gradient of a tangent to this graph will be a minimum. That will be your answer. Okay, so we need all these calculations there. Okay, and that's how we find the answer. Okay, so that's a way to really just understand what was actually going on there. Okay, so moving on to the next question, this is what we have. We have f prime of x being multiplied by f double prime of x. Where is it going to be less than or equal to 0? Okay, let's talk about this graph, f double prime of x. Since f prime of x, we already found that it's a parabola. So remember, this is how it works. The cubic function, that was f. If you derive this positive cubic function, it will give you a concave up parabola. Okay, also just remember, if your cubic function, if a was less than 0, it would not look like this. It would be like an n, a capital letter N, written backwards, like that. And if you derive that kind of graph, you would have a concave down parabola. Okay, so in this one, we have a concave up parabola for f prime of x. So f double prime of x will be a straight line, but an increasing straight line. So that is a straight line with a positive gradient. So I'm just showing you what f double prime of x is going to look like. We're going to have to draw this in order to be able to find out what x is going to be for this. Okay, so let's start off with drawing it. Remember, it is an increasing graph like that, but there's also something else we know about it. This graph, so we have the parabola, right? And we know what the x value belonging to the turning point of the parabola is. So the thing about that f double prime of x, this graph, you see its x-intercept. It's going to have the same x value as the x value of your parabola in the f prime of x. Okay, so these are just stuff that would be in textbooks that you have to study first to remember. So we can go ahead and draw this straight line graph. So that graph, the f double prime of x, is going to be a straight line, and its x-intercept is going to be that negative 1.35 that we found. So I'm actually going to put that point down so that we don't forget. That's that negative 1.35. Then the x-intercept is going to just be a line that will pass that point on the x-axis. Okay, so this is what this graph is going to look like. F double prime of x is going to be a straight line that is increasing because the parabola is concave up, and its x-intercept is going to be that negative 1.35, which is also the x value of your parabola's turning point. Okay, so the question there, so now that we have that graph drawn down, let's figure out what they want. They want where f prime of x multiplied by f double prime of x gives us something less than or equal to 0. Okay, so if I'm going to actually put them in their colors, remember that this graph was pink and that one was blue. Okay, so to find this, really what we're looking for is this. So we're saying when we multiply, and just remember when we're saying f prime of x, it refers to the y values of this graph and the y values of this graph. So this is the parabola and this is the straight line. Where do you take the y values of this and you multiply to the y values of that, and it gives you something less than or equal to 0? This is only possible if the y values of this graph is positive, and we multiply it by the y values of this graph, which would be negative. Then you would get something that is less than 0. Okay, so I'm speaking about the less than 0 first. We will also look at the equal to 0. Now, another way this could have happened is if the y values of this graph was negative, and we multiplied it by the y values of this graph, which was positive, then we will also get something that will be less than 0 or negative. That's what less than 0 would refer to. But we also have to watch out for where we will multiply these values and they would give us 0. Okay, this will only be possible if, for example, the y values of that was 0, multiplied by the y values of this one, and let's say that was either positive or negative. It doesn't matter, because if you multiply 0 by either a positive or negative number, you're still going to end up with 0. Okay, so that would be the equal to 0 part. We could also have a situation where this graph could either have positive or negative values and multiply by this graph, which has a value of 0, a y value of 0, then we would also get 0. So this is really what we are looking for on the graph, and you'll see how we're going to try and find it. Okay, so here's the graph. I've decided to put the requirements here on this side. So we are going to concentrate on f prime of x and f double prime of x. So just the pink and the blue graph. And since this is the last graph, I know that you're supposed to still, of course, have that cubic function, but just to avoid any confusions, I'm going to erase the cubic function. And let's just work with it like this, because this will just make more sense. Now we can just focus only on these ones. Okay, so this is what this graph looks like now. So I'm erasing everything about the cubic function because I don't really see a need of leaving this here since that is the last question. Okay, so that is the last question for this section. Okay, so this is what we can do here. So first we're looking for where are the y values of the pink graph going to be positive. The y values are positive here. So remember, this is the y-axis. This is the positive part of the y-axis. That's the negative part. So notice the negative part is below the x-axis. The positive part is above the x-axis. So you're only going to look for parts of the pink graph that lies above the x-axis since we're looking for where that is positive. And the parts of the pink graph that lie above the x-axis would be here. So here, that is above the x-axis. But we need to find at the same time, okay, for the same x values, the blue graph needs to also be negative, okay? So it needs to be for the same x values. So I notice that it starts becoming positive here after this point. So when we go like to the left of this point, you see that these have positive y values. Okay, the pink graph has positive y values. If I look at that, the blue graph for this same x values, I will also have to I will look at it in a vertical line like that, because this point on the blue graph, the x value is exactly here. It's also negative 3.4. So if these are the points that belong to the highlighted part of the graph, so these x values, let's also see where they belong to on this blue graph. These same x values, if you extend this down, look at where it is. You see this blue graph has a negative y value. And for the same x value, the pink graph has a positive y value. And that's what we want. And that's what we want. We want where the pink graphs have positive y values, and at the same time, or for the same x values, the blue graphs have negative y values. And this is happening over here. So you see here, same x value at this point over here, it has a positive y value. And if you look at it for the same x values for the blue graph, it has a negative y value. That's what we're looking for. So you see it happens all the way here. So let's mark this point. Now, the reason I cannot take beyond this is because of this. If you go beyond this, you see the blue graph? Yeah, it's sure it has negative y values. But the pink graph at those specific points, at that same x value, you see it doesn't have a positive y value. The pink graph has a negative y value here. And for the same x value, the blue graph has a negative. That's not what we're looking for. We're not looking for where the pink is negative and the blue is negative. The pink graph needs to have positive y values. So we cannot take anything that goes past this line here. Meaning these x values are only values that are less than negative 3.4, because you see they are moving to the left of negative 3.4. There's nothing on the right. It's not working on the right here. Okay, so that's the first solution we have. We can go ahead and say this one, that part worked where x was less than negative 3.4. Okay, now we cannot just assume that this is the only place that it happened. We also have to check through the rest of the graph. So if we look on this part of the graph, and the reason I'm choosing this wing is because I want where the pink graph has positive y values, meaning it needs to be above the x-axis. Here it has positive y values. Here it does not have positive y values. That is below the x-axis. So I'm taking only this part of this graph. Let me see. Does the blue graph for the same x values also have negative y values? So if you look at that, you see this part of the graph. I'm trying to see, okay, let me line this up vertically to the blue graph as well. If we start moving towards this side where this graph is positive, where it has positive y values, move in the same direction for the blue graph, you see that this blue graph has positive y values as well. So that's not going to work. We cannot have where the pink graph has positive y values and the blue graph has positive, because that's not the requirement. The blue needs to have negative. So it's not working anywhere else here. Okay, so it just means that this first requirement has been met where this is positive and this is negative. That works out. Okay, and it only works here for now. Now, let's also consider the zeros because that's also important. Remember, we are also looking for places where if you take the y value of this one and you multiply to that, it gives you 0. Meaning this graph, if its y value is 0, which is here at the x-axis, okay, at this x-intercept, this pink graph has a y value of 0. If you multiply it to the y value at the same x value, okay, of the blue graph, it should give you a 0 because 0 multiplied by this y value, which is negative, will give you 0. So it means that in this case, negative 3.4 is also an included point. So I can't just say x is just smaller than negative 3.4. It's smaller or equal to negative 3.4. Because of that, equal to 0 as well. Okay, so it's really just multiplying the y values of the graph. The pink graph's y value is 0. If you multiply it by the blue graph's y value at that same x value, the blue graph's y value is negative. So 0 multiplied by whatever negative number that is will give you 0. So that's why I have to say this here. Okay, so that means all through I didn't really find any other place that it worked. Okay, so long we are done with that first requirement. Now let's look for where the y values of this pink graph is going to be negative and the y values of the straight line graph will be positive. Okay, so where are the y values of the pink graph negative? That happens below the x-axis. Now the thing is, at the same time, the y values of the straight line graph must be positive. So I'm only going to look for those places. So over here, this part, the reason I will not take this is because, yes, this part may have y values that are negative. But you also have to look at the y values of this straight line. So you see over here, like just a point over here, it has a negative y value on the pink graph. But on the blue graph, that same point for the same x value, it has a negative. So I cannot take that, okay, because that's negative and negative. I need to look for negative and positive. So if I keep going on this graph, you see that as you keep going like downwards, moving from left to right, it's still negative all through here. But this graph as well is also still having negative y values. So I keep moving down, I even get to here, and I see I still have a negative y value here, but for the same x value, this graph also needs to be positive, okay, but it's negative, so it's not working until we get here to this point. You see, at this point, this y value of this graph is 0. So the y value of the blue graph is 0. And if you multiply it by the y value of this graph, okay, the pink graph, it's a negative number. And if you multiply those y values, they give you 0. So since this is one of the requirements, I have to take this. So I have to take this point where x is equal to negative 3.5. But before taking it, let me just check if we also meet one of these requirements, this one, the negative and the positive. So over here, you see that this graph has negative y values, negative, negative, and all of that. But for the same x values, this graph needs to have positive y values, which you can see is working here. A negative y value for the pink graph. And if you line it up to the x-axis and past that, you see that this graph has a positive y value. So it starts to happen from this point, negative 3.5, moving towards the right. It keeps working, okay, until this point here. Because now, here we still have the pink graph having a negative y value and the blue graph having a positive y value, which is what we're looking for, until you get to this point over here. So when we reach this point, you see that the pink graph's y value is 0 because this is an x-intercept. And the blue graph's y value is going to be positive. So if you take that 0 multiplied by whatever positive number that is, that will be 0, which is one of the requirements. When we multiply the y values, we should also get 0. So it means that it's working everywhere in between here. So it means that x is either greater than, so it's moving towards this side, or equal to negative 1.35, but less than or equal to, I also have to say equal to 0.7. Okay, so that is what we have there. These would be our two solutions. Okay, so we're saying it's either that x is less than or equal to the negative 3.4 or x is greater than or equal to negative 1.35 but less than or equal to 0.7. Okay, so this is our answer for this. So that is it for question 8, and then we move on to question 9. Okay, question 9. So question 9 says a wire 12 meters long is cut in two pieces. One part is bent to form an equilateral triangle and the other a square. Okay, so an equilateral triangle, all the sides are equal. A side of the triangle has a length of 2x meters. And 9.1, they want you to write down the length of a side of the square in terms of x. Okay, so since they say a wire which is 12 meters long, okay, so 12 meters long, we have this wire. And the full length of it is 12 meters. But then they say it's cut into two pieces, so not half, just two pieces. And one part is bent to form an equilateral triangle. Okay, so since this line is being cut into two parts, I'm going to just call it like it's being cut into two parts. I'll call this part A and I'll call this part B. So, okay, it's cut into two parts and then one part of it is bent to form an equilateral triangle. So let's say that was the part A that was bent to form an equilateral triangle. So out of that, we form an equilateral triangle, just knowing that all the sides in this triangle are equal. And then they say, and the other a square. So the other part is bent to form a square. So that would be the length of B. Okay, so I'm going to go ahead and draw a square, and that is B. And in a square, all the sides are equal. Okay, then they say that a side of the triangle has a length of 2x meters. So one of the sides has 2x meters. So it means everything else is also 2x meters because all the sides of a triangle are equal. So the whole point of this is to write down a side of the square in terms of x. So we need to find one of these sides, but it needs to be in terms of x. Okay, since it needs to be in terms of x and the only thing that has x in it is the triangle, we start from here. So since this entire wire, everything here, right, is made up of this one part, which I've called A. It's made up of that one part. So let's find the formula for A. So we can say that A, the value of A, that length of that wire, can be the entire 12 meters minus the length of B. So that is 12 minus the B. Okay, so that's what A is. So since A is the entire wire, let's put it in terms of x. Since all of these lines are equal, these sides are equal, it means this is 2x and this is also 2x. So if we're calculating the length of the entire wire in terms of x of this triangle, it's going to be the 2x plus the 2x plus the 2x, which will give you a 6x. So that's the length of A. That is that piece of wire, that's A. So I can say that 6x is equal to 12 minus B. So because I want to name this one in terms of x, it would not make sense to try and make x the subject here. Rather, I'm going to make B the subject, and then I'll be able to name that in terms of x, since the entire length of this part is B, and that's what is used to make this square. So we can take B over to the left-hand side and it becomes positive. It's equal to, and we still have the 12 here, and we're taking the 6x over, so minus the 6x. Okay, so B is equal to 12 minus 6x. But B happens to be the entire length of this square. Okay, so I'm saying that B is the entire length of this square. So that is that 12 minus 6x. Okay, that is everything here. And since each side, all the sides in the square are equal, to just find one of the sides, if this is the entire length of it, I just have to divide this entire length by 4, and it will give me the length of one of the sides of this square. In a way, we can look at it like this. Since B is the entire length of this wire and it's the entire length of this square, that's like looking at the perimeter of the square. And the formula for perimeter of a square would be 4 multiplied by s. Because whatever the side is, you just multiply that by 4 and that will give you the entire perimeter, since all the sides are equal and there are 4 sides. So if 4s is equal to 12 minus 6x. Remember, we just want to find the length of a side. We just want to find s, one of the sides of the square. So we can divide both sides of the equation by 4 to find s. And so one of the sides of this square would be this. So I'll just divide. 12 divided by 4 is 3. Negative 6 divided by 4, so if you say negative 6 over 4, it simplifies to, I'll leave it as a fraction, minus 3 over 2, and we have x as well. Okay, so that is one of the sides of this square in terms of x. So it means that one of the side is equal to 3 minus 3 over 2x. Okay, so that's the first question. Moving on to the next question. Then question 9.2 says, if the square is now used as the base of a rectangular prism with a height of 4x meters, determine the maximum volume of the rectangular prism. Okay, so we have to find the maximum volume. Okay, so if this square is going to be used as the base of a rectangular prism. Remember, a rectangular prism kind of looks something like this. Okay, so it can be something like this, a rectangular prism. And so they're saying that the square is now being used as the base of the rectangular prism. So the square that we had, one of the sides of it, so each side is equal to 3 minus 3 over 2x. So it means that this as well would also be like that. We have all the sides being equal because the base is a square, and one of the sides is just 3 minus 3 over 2x. Then they also tell us about the height. Okay, they tell us that the height of this rectangular prism is 4x meters. So you can kind of imagine it as if it's standing up. This part over here would be the height of it. That's how high it is. So that is 4x meters. Okay, so we have to determine the maximum volume of the rectangular prism. To find the volume of it, the formula for volume is equal to, of a prism, would be the area of the base multiplied by the height. That's how you'll be able to find out how much space is filled up in this entire object. So the area of the base, remember the base is a square. To find the area of a square, you just say the side multiplied by the side, which is really just side squared. And then we have to say that's the area of the base parts, then multiply by the height. We know that one side is equal to 3 minus 3 over 2x. So we have that 3 minus 3 over 2x, and that side needs to be squared, so all squared. And then we'll multiply that by the height, which is 4x. So multiply by 4x. Okay, so this would be the volume. Then we still have to find the maximum volume after that. So let's go ahead and find just the equation of the volume of this. So to simplify this, remember this is a binomial being squared. Just square the first term. That's going to give you 9. Then you multiply the first term by the second term. So that is 3 multiplied by negative 3 over 2. So negative 3 over 2. Then you see that answer that you get, you're going to take that and multiply it by 2. Okay, you could do it the usual way of creating two brackets and foiling out, but that takes long. So then that will give you a negative 9x. Okay, because when we multiply this times this, that becomes that negative 3 over 2x. Then when you multiply by 2, it becomes a negative 9x. Then lastly, you square the last term. So if you take this and you square it, first of all, it's going to become positive. Then the 3 is going to be squared and give you 9 over the 2 being squared gives you 4. And the x being squared gives you x squared. And all of this is being multiplied. Okay, so multiplied by 4x. We multiply by 4x. Okay, so I'm just going to rewrite it like this instead. So I'm writing the 4x in front because since it's only one term and it's being multiplied by all of this by, let me put it in the order of its exponents. Since this has x squared, I'm going to write it first. So I'm going to say it's a positive 9 over 4x squared. And then we have the negative 9x. And then we have the plus 9. Okay, so this is going to multiply in. So we're multiplying these in. And what we're going to get is, you can use the calculator here just to be careful. So 4 multiplied by the 9 over 4. So 9 over 4x squared, it gives us a 9. So we have 9. And this x times the x gives you x cubed. Then it's the 4x multiplied by the negative 9x. So what is 4x multiplied by negative 9? Okay, negative 36. And so x times x will give you x squared. Then we have, again, a 4x multiplied by a positive 9. That will be positive 36x. Okay, so this is the formula for the volume of this shape. But now we just have to find out, they ask for the maximum volume itself. So they're not just asking for you to determine the value of x for which is going to be a maximum. They want the maximum volume. So first we're going to find out at which x value will this have a maximum, okay, volume. So let's go ahead and do that. And the way we'll do that is just remember that looking at the way this formula looks, it has 9x cubed. This is going to be a cubic function. And the coefficient of x cubed is 9. So that is a positive number, meaning your graph is going to look like that. Something like that. Okay. And so we can go ahead and find what we're trying to find is the maximum volume itself. So it has a local maximum and a local minimum. We're looking for this one, the local maximum, and specifically its y value. So let's find its x value first. So since this is the formula of it, to find that y maximum, that maximum value, since it's a turning point, we're going to derive this so that we're really finding the gradient, okay? So the gradient of this graph, but specifically where the gradient is equal to 0, because the gradient is always equal to 0 at the turning point. So let's derive this. 9 times 3, so 9 multiplied by 3, that gives you 27. So 27x, and then take out a 1 from the 3 squared. Then negative 36 times 2, that is negative 72x. And so take out a 1 from that, it gives you 1, but we don't have to write that. Then plus 36, and that x falls away because it becomes a 1. So this is the gradient of this function that we had, the volume of that. Now we just have to make that gradient equal to 0 because that will help us to find the turning points. Only at the turning points are the gradients equal to 0. So we have 27x squared minus 72x plus 36. Then, if we look at all these numbers, we have to factorize this. All of these numbers, let's just see what can go into everything here. So 27 divided by 3, okay, is 9. 72 divided by 3 is 24. 9 and 24 already have something in common. They have 3 in common, so it means there's a bigger factor we can divide by. Let's try 27 divided by 9. Okay, it's 3. 72 divided by 9. It's 8. Okay, so I know 3 and 8 have nothing in common. So, okay, so that means we can divide both sides by 9. 9 can definitely go into all these numbers. So if we have 0 is equal to 27x squared divided by 9, that is 3x squared. 72 divided by 9, that's minus 8x. And then 36 divided by 9, I think that's 4. 36 divided by 9, yeah, okay. So positive 4. Okay, so that's what we have. Okay, then you have to factorize this. So I'm going to use the factorizing method. You can use the quadratic formula if you want to. So we're going to open up 2 brackets, and because there's a coefficient here, you cannot factorize it normally. I'm going to use the cross method. So I'm saying 3x and x, and then I need, so that's the factors of 3x squared. Then I need factors of 4, but once that will help me get an 8 in the middle. The fact that the middle is the only negative one, you should know already that both terms will be negative. Okay, so I have a negative and a negative. I would have tried 4 and 1, but this doesn't seem to help to give an 8 in the middle, because that will give you negative 3, and that's negative 4, and that's negative 7. That doesn't give you negative 8. So I'm going to try 2 and 2. Okay, so 3x multiplied by negative 2, that's negative 6x. And then x multiplied by negative 2, that is negative 2x. Okay, so that gives you negative 6x minus 2x, negative 8x. And that is the middle term. So these are our factors. It's 3x minus 2 and x minus 2. Okay, so that's what we have. So solving for x, we're saying 3x minus 2 is equal to 0. Or we have x minus 2 being equal to 0. 3x is equal to, take the negative 2 over, divide both sides by 3, and x is equal to 2 over 3. Or it is where x is equal to taking that over 2. Okay, so we have 2 solutions here, and we have to now decide which one is going to be the one that belongs to the maximum turning point. The way you can decide that is knowing the shape of your graph. Okay, the shape of our graph looks like this because it's a cubic function and a is positive. So since it looks like this, then it means that this here is your maximum. And if you're looking at this on a Cartesian plane, then it would mean that the x value belonging to the maximum is the smaller x value. So we have to take this one, this 2/3. That would be the maximum. And then the bigger x value is 2. That would be the minimum, the local minimum. Okay, so we know it's this one. So since x is equal to 2/3, to find the actual maximum, okay, that maximum volume, you're going to take this x value belonging to that maximum y value and substitute it into the original equation of this cubic function so that you can find out what that y value is. So the original equation is this volume right here. So we're taking the original equation and we're going to substitute 2/3 because it's the x value that belongs to that maximum y value. So v, and we're subbing 2/3 in there, is equal to 9 bracket 2/3 all cubed minus 36 open bracket 2/3 all squared plus 36 open bracket 2/3. And you can go ahead and put this onto the calculator and let's see what we get. And the answer we get is that 32/3. But because it's volume, I'm not going to really call it just 32/3. I'll put it in decimal form and round off to 2 decimals. So it is this 10.66. So we can just round off to 2 decimals. That volume of that is going to be 10.67, and because it's in volume, okay, it's going to be meters cubed. Remember, these dimensions were in meters, so that is 10.67 meters cubed. That is the maximum. So you can conclude and say the maximum volume is that answer, okay, of the rectangular prism. So the maximum volume of the rectangular prism is 10.67 meters cubed. And that is our final answer in question 10. So we're on question 8, and 8.1 says, determine f prime of x from first principles if f of x is equal to 3x squared minus 6. Okay, guys, this is 4 marks, so this is really a place that you can score marks. So we're going to go ahead and find the derivative of this function, or the gradient really. Okay, so what we can go ahead and do first is, because we know that the formula we're going to use is f prime of x is equal to the limit as h approaches 0. And then our formula is f of x plus h minus f of x all over h. Remember that this is in your formula sheet. So because we're using this formula and we already have f of x, okay, we need to find the f of x plus h. So that's what we're going to go ahead and do first. So we're going to keep this aside and go ahead and find the f of x plus h. So when you look at that formula, that f of x plus h, you see that all they did was add an h to wherever they see x. And that's what we're going to do here. So f of x plus h is actually equal to, and we have 3, see x squared over there. We're going to add an h to it. So it now becomes x plus h all squared, and then minus 6. So we just have to simplify this equation or expression really. So this is equal to, we still have our 3, and let's distribute. So you can do the whole thing with 2 brackets, but that takes quite long. So what you can instead do is just square the first term, which gives you x squared, square the last term, which gives you positive h squared, then multiply the first and second term, which will give you xh, and then multiply them by 2. So that gives you positive 2 xh. So I need some space here, okay, and then we still have our h squared, then minus 6, and now we can go ahead and distribute the 3 into the bracket. So we're going to have 3x squared plus 6xh plus 3h squared, and then minus 6. Okay, so now that we have our f of x plus h, we can go ahead and substitute it into our formula. So this is our formula, and we're going to go ahead and say this is equal to the limit as h approaches 0 and substitute our value. Okay, so we're just taking this whole thing that we have here and substituting it in place here. So just be careful with this part because you can make little mistakes. And now we are subtracting it by f of x. Now f of x, as you can see, has two terms. Because you have two terms, you need to protect this with brackets. So it's going to distribute in. So we're subtracting by 3x squared minus 6. Okay, and all of this goes over h. Then we're going to go ahead and distribute. So you can distribute from here. You can also distribute from here. It's still fine. So this is equal to the limit as h approaches 0 of the same function that we have. Then we're going to distribute. So that becomes a negative 3x squared. And that would become a positive 6. And then it goes all over h. Now, the thing about this part is, you know that whatever you were subtracting by, that is the only thing that's going to cancel throughout here. So I'm looking for something that has a 3x squared. There we go. We have a 3x squared. That cancels with that. And then with 6. So the negative 6 will cancel with the positive 6. Okay, so all we're left with right now is we still have the limit as h approaches 0. We have 6x h and then plus 3h squared and then nothing else all over h. Okay, so now we are getting to the final point, and the whole point of us doing all of this is really so that we can get this function or this expression to a point where h is not the denominator, because you see that we are approaching 0. So we need to substitute in place of h, 0. We don't want that to become undefined. So what we can do there is take out a common factor of h. So take h out as a common factor and we're left with 6x, and then what are we left with here? So you just say that divided by that, and you get positive 3h all over h. And so your h's cancel. Now, even if you didn't add this step and you just went ahead and divided, it's still fine because there is some sort of factorization that we can see that was implied. Okay, there was some sort of implied factorization. So we have that is equal to, so at this point, you can rewrite this again, but then you have to rewrite that lim of h approaching 0. I'm just going to go ahead and substitute. So now I don't need to actually write that it's approaching 0 because I'm substituting 0. So that is 6x plus 3, and then in place of h, we put 0. And so you know that 3 times 0 is 0. So our answer is really just 6x. So when we derive that, f prime of x gives us 6x. And just to check and make sure that you are actually correct, what you can do is go to your original function, and using the rules of derivative, you can derive that. You see, if you said the coefficient times the exponent, you get 6, and then you have x, and then you take the exponent minus 1, which is 1, and you don't have to rewrite that. And then you have negative 6, which is a constant. If you derive a constant, it becomes 0. So we know that that really is our answer. So you can do that, grade 12s, just to make sure that it is correct. Okay, I also wanted to add, if you guys are enjoying these videos, please make sure to give it a like and share. And you can also subscribe to see more content like this. It really helps with the growth of the channel. Okay, so that is the first question in question 8, and we move on to the next question. We are on 8.2, and 8.2 says, determine the derivative of f of x is equal to this. And this is for 5 marks. It is not using first principles, okay? They just want you to determine the derivative. They never mention first principles. So our function looks really weird, but there is a squared, and we have to actually simplify that. So you have to get your function to a point where it is simplified before you can actually derive it. It's kind of like preparing it to be derived. So we're going to go ahead and apply that squared. When something is squared, it really just means the same thing is being multiplied by itself twice, like that. Okay, so we can go ahead and just use that short method of distributing a binomial, or rather a squared binomial. So we have this, and what we can do is we take the first term and we're going to square the first term. So if you square this, the 2 squared becomes 4, and the root x squared, you see, that's going to cancel out your root there. So you're just left with an x. So that part is done. And then we're going to square the second term, which is the negative 1 over x. When something that is negative gets squared, it becomes positive. And then 1 squared is 1, and x squared is x squared. And then you're going to multiply the first term and the second term by each other. So here's what happens. We have 2 root x being multiplied by negative 1 over x. So they become negative. And then you see that diagonally nothing really cancels because this is a root x and that is an x. It's not really the same thing. So what we can do is just multiply numerator with numerator. So 2 root x times negative 1 is just negative 2 root x. And then this has a denominator of 1 that we cannot see. So 1 times that just stays x. Okay, now we can actually simplify it further. So what we can do, well, just to show them that we did square it, we can just rewrite it here first. So we just have there, we have a minus 2 root x over x. And let me also just write this like that, 1 over x squared. Okay, so at this point, are we ready to actually derive this expression? No, okay, we're not ready to derive it. And the reason why is because you see that you still have x's on your denominator. They shouldn't be there. They should be on the numerator. So what we're going to do is go ahead and simplify these. So for this one, what we can do here is we're going to say f of x is equal to, and we have 4x. And instead of like just putting it to the top, what you can do is divide. This is still an x. We can just rationalize the exponent by rewriting that square root of x like this. So we have minus 2, and we're going to leave the base. Now, you see this minus and then this square root of x specifically, right? It has an inside exponent and an outside exponent. The exponent on x is 1, and the exponent on the outside that we cannot see is actually an invisible 2 because this is the square root, like you have a cube root as well. There's a 3 here. Okay, so we can just go ahead and say inside exponent over outside exponent, and that's how to actually simplify a surd so that its exponent is a rational number. Okay, so at this point we still have that, and we have over x. And what I'm really doing here now is I'm going to divide. Because I have an x on the numerator and an x on the denominator, I'm dividing. But when you're dividing things with the same basis, you're going to subtract the exponents. So the exponent here is an invisible 1. So we're really just saying a half minus 1, which gives you negative a half. So all of that really just becomes x to the power of negative a half. Okay, so that's what we have. And that's what happens when we simplify that. And then over here, we just have a plus, and that should not be on the denominator. What we can do here, because we don't have an x on top, we can actually move the x squared to the numerator. And when you do that, what happens is that the exponent becomes negative. Okay, so that is what our expression ends up looking like. And now we're ready to derive. So we can go f prime of x is equal to, and we're saying the coefficient times exponent, which is 4, and you have x, and you take the exponent, which is a 1, minus 1, which becomes a 0, but x to the power of 0 would be 1, and 4 times 1 stays 4. Then here, coefficient times exponent, you have a negative 2 times negative a half. Okay, so the negative and negative would cancel. But you see diagonally, the 2 and the 2 would also cancel. So there you're left with a positive x. And then in the exponent, you have 1 over 2, and you have to subtract by 1. So exponent minus 1, which is going to give you, you can use your calculator, negative 3 over 2. And then here we have, okay, we're going to take the coefficient, which is an invisible 1, times negative 2, which gives you negative 2. Then you have x to the power of negative 2 minus 1, which gives you negative 3. And there we go. So there it is finally derived. If you like, you can rewrite the exponents being positive, or you can leave it like that. So if you wanted to rewrite the exponents being positive, you could rewrite it like this. F of x is equal to, and you have 4 plus, now you see the thing about this is your base is x. That's the thing with the negative exponent. To make sure the exponent is positive, you're going to have to take this base and move it. Currently, it's on the numerator because it's normal, its denominator is 1, the natural denominator of 1. So you're going to have to move it to the denominator so that the exponent can become positive. So that's going to be, you see, now the one that is here is not this one. It's just a placeholder of 1, the one that was actually in front of the x. So you have x to the power of positive 3 over 2. That can still go further. And then we have here, what is carrying the negative exponent? It's the x, not the negative 2. So nothing's wrong with the negative 2. Leave it there in the numerator and bring that to the denominator. Okay, now if you want to finally write it in surd form, this can go back into surd form like this. So f prime of x is equal to 4 plus, and you have 1 over. Now you see this, remember how I said inside exponent over outside exponent? Well, that's how you can actually rewrite that. So we're going to put it as a surd. We're going to put the x and put our surd, and the inside exponent is a 3 and the outside exponent is a 2, which we don't have to write because it's a square root. And then you have the minus 2 over x to the power of 3. So there we go. And that would be written in surd form with positive exponents, but you can also leave it like that. You will not get penalized for this. Okay, finally moving on to the next question. 8.3 says, given f of x is equal to 3x cubed minus, and we have all of that. The question is, determine the interval for which f is concave up. Okay, so I'm going to quickly speak about concavity and how that really looks. Remember, I just really try my best to put a little bit of some learning in the past exam papers. Okay. So with concavity, what we can actually first of all think about is the way this function looks. So it is a cubic function, first of all. And do you notice that the value of a, because you know that the cubic function is ax cubed plus bx squared plus cx and then plus d, which is your y-intercept. So if a is positive, right, you have a cubic function that looks like an n. I have explained this before in my past exam paper videos. So that is a if a is greater than 0. And if a is less than 0, you have a cubic function that looks like that. So it looks like a backwards n, really. Okay, so it looks like a capital letter n. And then this one looks like a backwards capital letter n. Now, the thing about concavity, I know that we don't need a graph to solve this, but I just want you to understand what it means. When something is concave up, the same way we think about a smiley face parabola, this is a concave up parabola, okay, because it is curved upwards. So when you are looking for the part of your cubic function that is curved upwards, where you're going to find this, as you can see, we can clearly see it here. It's over here. This is the part that is curved upwards. This is the part that looks like a smiley face parabola. But how you find out where exactly it is, you're going to have to find out where it starts. Okay, where does the concavity change? That is where the point of inflection is. Okay, so you're going to have to find the x value of the point of inflection, and if you find that point, you know that your graph will be concave up for every other x value that is greater than this point. That is, of course, for a graph that has an a value greater than 0. And then if your graph has an a value less than 0, is the other way around. You see that way it's curved upwards, it's here. Okay, so I'm only doing that just so that if they give you a physical graph, you'll be able to actually find that. But with this, we don't actually need all of this. We don't need the graph at all. What we can actually do here is this. If they ask you for which values of x is your graph concave up, all you need to do is find the second derivative of your function and find out where it is greater than 0. So just solve for this inequality, really. That's all we have to do here. And then when it's concave down, it's the other way around. It's when it's less than 0. Okay, so we're solving for this. So let's go ahead and find the second derivative as that. Well, we're going to go ahead and find the first derivative, which we already had. No, we didn't. Okay, we didn't have that of this graph. So it's equal to, you're going to say coefficient times exponent, which gives you 9, and you have x minus 1, which is 2. Coefficient times exponent, negative 6x minus 1. You don't have to write that one. And then plus 6, and you know the x falls away because of the exponent of 0. A constant, if you derive, always becomes 0. So this is our first derivative. Then find the second derivative. So f double prime of x. And I guess we can already just tell them is greater than 0 and then just derive that. So that's 9 times 2, which is 18. And you have x. 2 minus 1 is 1. You don't have to write that. And then minus 6, and the x falls away. So this is greater than 0. Okay, so now that we have this, we can go ahead and solve for this inequality. Please note, this is a linear inequality. It's not a quadratic inequality. So there is no confusion with this. You solve for this just like you would with an equation. So we're going to take our negative 6 over, and we have 18x is greater than positive 6. And then to solve for x, we divide both sides by 18. And that therefore means that x is greater than, what is 6 over 18? Okay, they both have a common factor of 6. 6 divided by 6 is 1. 18 divided by 6 is 3. And that is our answer, okay? X is just greater than 3. So that is, I think this is set builder notation. The other notation, no, this is actually interval notation. So if you wanted to write it in set builder notation, the one with like brackets and stuff like that, that one looks like this. So you could have written it like this. You see, you're really just saying that x is going to be greater, right, than 1 over 3. So if you have 1 over 3 here, you're saying that all my x values lie here, values that are greater than 1 over 3. So you could have written that like this. X is an element of. Now with set builder notation, you're always thinking about what is the smaller number and what is the bigger number. See, the answers are here. It's numbers that are bigger than 1 over 3. So the smallest number we're comparing it to would be the 1 over 3, and the biggest number would be positive infinity because it's heading towards positive infinity. So you're going to say that x is an element of 1 over 3, right, all the way to positive infinity. And then with the brackets, you see, if they didn't say x is greater than or equal to, you're going to put a round bracket, because the actual number of 1 over 3 is not included in this answer. But if it was, you would put a square bracket, okay? Now for infinity, infinity always has a round bracket because infinity is not an actual specific number. It's more of a concept, okay? So this is what we have. That's how you could have written it as well. Okay, moving on to question 9. Okay, so question 9 says, 9.1, sketch below is the graph of f prime. Okay, so this has already been derived. And so it's the derivative of, and they give you the full equation of the original function. And tell her that points A, B, and C are the intercepts of f prime. Okay, so A, B, and C are intercepts, x-intercepts and the y-intercept, okay, with the axes. The first question is to write down the coordinates of A, which I feel like we can fill in here, but it's fine. Okay, the coordinates of A, we're going to go ahead and find that. Remember that A is a point on the derivative of this graph. So if they gave you the original function, all you have to do is derive this function and you'd find out exactly what A is. A is intersecting the y-axis, so it is your y-intercept. Okay, so we're going to derive that function, see exactly what it gives us, and then find the y-intercept from that. So this is our function. Let's go ahead and derive. So f prime of x is equal to, that's going to give us negative 6x squared, and again, negative 6x, and then positive 12. So if this is our function, if this is our parabola, this parabola, what exactly is the y-intercept? The y-intercept is this number over here, because that's your c value. Okay, ax squared plus bx plus c. C is your y-intercept. So if that is our y-intercept, the coordinates of A would be the x value, okay, of the y-intercept is always 0, and then the y value is 12. So that is A. Okay, moving on to the next question. So the next question says, determine the coordinates of B and C. As you can see, B and C, I need to write that down. That is 12, just in case we need it. So 12. B and C, as you can see, are your x-intercepts. So we have to find the x-intercepts. Well, we can go ahead and find them by taking, you can't take the original because the original is the cubic function. The parabola is the derived. So we can take this formula, okay, our parabola, and go ahead and find the x-intercepts. So to find the x-intercepts, you have to make y equal to 0. So since this is our parabola, this is our y value, f prime of x there. So we're going to go ahead and say f prime of x is equal to 0. And we can substitute there. So we're saying negative 6x squared, and then we still have the minus 6 plus 12 minus 6x plus 12 is equal to 0. And we just have to solve for this. So do you see that they all have a common factor of -6? So you can divide both hand sides by -6, and then you're going to get, so that is going to give you x squared, and then this will give you positive x, and that's going to give you a -2 is equal to 0. And now we have to factorize. So x times x gives us x squared. Now we need factors of -2 that can give us +1. So factors of 2 really just 2 and 1. Because that is negative, 1 has to be negative, and they need to, when added, give us +1. So you can make the 2 positive and the 1 negative, because 2 minus 1 is +1. That's what gives us the positive coefficient of 1. So that's +2 and -1. And then solve for x. X is either equal to -2 or x is equal to +1. And now we can just decide which one is B and which one is C. So -2 and +1. As you can see, B is more on the left. Again, it's a negative value. So -2, and then C is +1. So as coordinates, you can go ahead and write it like this. B is -2 and 0 because it's a x-intercept. And C is 1 and 0. And there we go. Okay, moving on to the next question. The next question is just a question, really. They say, which point on the graph of f will have exactly the same x values as B and C? So which point on the original function is going to have the exact same x values as B and C? So you see, with a cubic function, this is the derivative of that cubic function. The points that would have this exact same values, because this is concave down, it means your cubic function's a value was negative already from the beginning. That's why, as you can see, it is negative. So it's going to form an upside down n, or backwards n, really. Okay, so it forms a backwards n like that. And so the points that would have the exact same x values as B and C, okay, as your x-intercepts of the parabola, okay, the derivative of your cubic function, that would be your turning points or your stationary points. That's what that is, okay? So it's going to be your turning points. I'm sure if you say stationary points, it'll still be fine, okay? So we can just go ahead and tell them these are the turning points. Okay, and that's for 1 mark. Moving on to the next question. Then the next question, 9.1.4, says, for which values of x will f be increasing? So not concave up or anything like that, but increasing, okay? So this actually has to do with the gradient and really what the function is doing. So if you have a line that's doing this, you read graphs from the left-hand side to the right-hand side. Would you say this line is moving up or down? It's moving down. If you read it from the left to right, you see it's moving down. And so this would be decreasing, okay? So if you want to see a function that's increasing, it needs to be moving up. So that's what we're really going to be looking for in our original function. So we kind of have a rough sketch of what it looks like, something like that. It could look a little different. So we have this, and let's look for the places that this graph is increasing. If we start over here, look at what the graph is doing. Remember, you move from left to right. So if we're moving like this, you see that we're moving down. Okay, so it's decreasing there. And then over here, what is it doing? It is increasing. And it stops increasing there. Okay, at the stationary point, it actually stands still. It's stationary. It stays still here. Then it starts to decrease again. So we can see it's all of this part of the graph here. And how we can actually answer them is using the stationary points, because at the stationary points, the graph is neither increasing nor decreasing. So at this point, we can say that this is where x is greater than -2, but less than 1, because you see it's increasing from -2 all the way to 1 as x values, of course. Okay, so that is our answer there. We'll tell them that it's increasing for x values that are greater than -2, but less than 1. Okay, moving on to the next question. 9.1.5 says, determine the y coordinate of the point of inflection of f. So the point of inflection, you simply find that by making the second derivative of your function equal to 0, because the point of inflection is just that point that the graph changes concavity. So it's concave up here. Then you reach a point of inflection and the concavity changes to concave down. Okay, so that is what they want us to find. They want us to find the y value. So to find the y value, you first have to find the x value. Then when you find the x value, you take that x value and substitute it into the original function. And that will help you to find the y coordinate belonging to that x value. Okay, so let's go ahead and do that. So we have already derived this function. I might as well just say f double prime of x is equal to 0 because I already have the derivative of this. The derivative of this is this function. Okay, let me just start by saying f prime of x, first of all, is equal to, and we have this. So that is negative 6x squared minus 6x plus 12, right? That's what we have there. Okay, so now that we have this, we can go ahead and derive it again. And I'll just say make it equal to 0. So I'm just going to put the derivative of it on this side. So when we derive, that's negative 6 times 2, which gives you negative 12x. And then 2 minus 1, which is 1. You don't have to rewrite that. And that is minus 6. Okay, and the x falls away, and so does the 12. It's equal to 0. Then we can go ahead, and I should have just left it like this, but it doesn't matter, it's fine. So now that we have this, I can just go ahead and say, well, take the 12 over. So we have negative 6 is equal to positive 12x. Divide both sides by the 12 to leave x on its own. And x will therefore be equal to, what is negative 6 over 12? That gives you negative a half. Okay, so now that we have negative a half, that is the x value of the point of inflection. We have to find the y value, the y coordinate. So to do that, we're going to have to substitute this into the original function. Okay, so we're going to go ahead and say f of, and we'll say negative 1 over 2 is equal to. And this is our function, and we're just substituting. So negative 2, and then in place of x, you're going to say negative 1 over 2 cubed minus 3, and then negative 1 over 2 squared, plus 12, and then negative 1 over 2, and then plus 20. And then you can just use a calculator to find exactly what the y value is. And that's really all we're doing here. And the answer we get is 13.5, which you can also leave as a fraction. It's fine. As a decimal is also okay. So there we go. That is our answer for that question. And we move on to the next question. Okay, so 9.2 says, the tangent P, which is 3 and negative 10 to a curve. Okay, I like to draw these things down as they say, just so that we know exactly what it looks like. So there's a tangent, right, at P, this point P. So let's go ahead and plot that down. It's 3 and negative 10. So 3 to the right and 10 units down. So maybe let's just say, for argument's sake, it's somewhere here, right? And that is P. So that's 3 and negative 10. So to the curve is given by y equals negative x squared minus 1. Wait. The tangent at P. That doesn't make sense because the tangent, if it's a tangent, it's a straight line. So the tangent to the curve is given by this. Okay. That is supposed to be a straight line equation, but it is a parabola's equation. So it's kind of like, maybe the parabola is this. Not sure. Okay, so let me just go ahead and look at this question quickly. Okay, so if you check the marking guidelines of this, they actually do set 9.2. Do not mark this question. This question has been removed from the examination paper. So there was probably a confusion with that question. So that doesn't have to be done. And I wanted to do this and just maybe give an equation to this, because I thought maybe they actually meant y equals negative x minus 1. But the thing is, they don't really tell us too much about that curve, really. So I don't think it's good to actually do that. We can actually just let it go. It's fine. Okay, so I will skip this question and we can move on to question 10. Okay, question 10 says, the profit, which is W of X, earned by a company to manufacture X bicycles per week is given by this equation. So the thing about this is it's given by this formula, but this is the profit that they're going to earn to manufacture a specific amount of bicycles. So depending on the amount of bicycles they make, they will make a specific amount of profit. That's really what's going on here. So X is the amount of bicycles, and then W of X is the profit. So the question is, what should the weekly bicycle production be to maximize profit? So what should be the weekly bicycle production? How many bicycles should be produced so that they can maximize profits? So the final answer, they're really just asking you for the value of X, because X tells you how many bicycles was manufactured. So how many bicycles must be created so that the profits can be at a maximum? So this is a calculus question, of course, and we're going to have to derive here. So we're really just finding what exactly is the X value when this is at a maximum. So we can take this that we have, negative X. Okay, it has fractions, so we just have to be careful. So let me actually rewrite this. You see the way this is written? You can actually rewrite this in a way that you can properly derive it. So instead of negative and then X cubed, remember that there is an invisible coefficient of 1 in front of the X cubed. So we can rewrite that as 1 over 150 and then X cubed, then plus 3X squared minus 250X minus 2,700. Okay, so this is what we have. And we can go ahead and simplify here. So the first thing we can do is we're going to derive. Okay, remember the idea behind it is you're trying to find the maximum, not necessarily the maximum profit, but the amount of bicycles that must be produced for them to have a maximum profit. So in other words, as a graph, what you're trying to find is you're looking at this. This is a cubic function, and it's a cubic function with its a value being negative. So it's going to be those cubic functions that look like an upside down n. It may not look exactly like that, of course, but just something like that. And what you're trying to find is where it's going to be at a maximum. So you have a local minimum. Okay, that's the lowest part, the lower part, and a local maximum. So these are the points we're looking at, and we're trying to find out where, okay, or which X value, at which X value is it going to be at a maximum. That's really what we're trying to find out. What exactly is the X value for the local maximum of your cubic function? Okay, so we can go ahead and derive to find the gradients. Okay, that's what the derivative gives you. So W prime of X is equal to, and we're saying negative 150 times 3. So 3 and 150 have something in common. They have 3 in common. So 150 divided by 3 is 50. 3 divided by 3 is 1. So that is negative 1 over 50. Then we still have our X, and we take the 3 minus 1, which is 2. Then it's positive 3 times 2, which is positive 6. And we have X. 2 minus 1 is 1. I don't have to rewrite that. And then we have minus 250, and we have X to the power of 1 minus 1, and that gives you 0, which of course becomes 1. And so negative 250 times 1 stays negative 250. Okay, so now that we have this, what we can do at this point is we found the gradient, right? Now you need to specifically find the turning points. To find the turning points, you're going to make your gradient equal to 0. Remember, the idea behind this is at the turning points, the gradient is stationary. It doesn't move. It's neither increasing nor decreasing, so it's standing still. That's why we make the gradient equal to 0. And we have 1 over 50x squared and the rest of everything that we have here. So plus 6x. That is a 6, right? Yeah, it is 6x, and then minus, why am I saying 2? Yeah, it is 250. I keep getting confused by this. 250. Okay, so this is what we have, and we can, sorry for that. What we can do is now simplify this. Okay, we're going to have to factorize. It doesn't look nice to factorize right now. So what I can actually look at is the fact that we have a denominator of 50. We can call that negative 50 and get rid of that by multiplying both hand sides of this by negative 50 so that that can come out of the way. So negative 50 also on this side. Okay, so we're just multiplying here. That gives you 0 still. Negative 50 times 0 is still 0. Then when we're multiplying here, negative 50 times negative 1 over 50. Now I'm going to give the the negative to the denominator, because look at what happens. You see, this is on the numerator. You can cancel diagonally, so they cancel out and you're just left with 1. So really you're left with x squared. And then we have 6x multiplied by negative 50. So it's going to become negative first of all. And 6 times 50, 6 times 5 is 30. And then you just put your 0 there. So that is negative 300x. Okay. Then lastly, the negative 50 times 250, negative 250, that becomes positive. What's 250 times 50? Well, we can say 25 times 5 gives you 125, and then just put your 0 and your other 0. So that's 12,500. Okay, so this is what we have. Then we have to factorize this. But this looks long to factorize, so I'm going to use the quick method. So with the quick method, you don't show them that you use the quadratic formula, but you still use it. So this is how we're going to do this. We have 0 is equal to, and we're multiplying, right, these two brackets. What times what gives you x squared? That's x times x. So now we just have to find the numbers, okay? So the numbers that would give us this, but when added, give us this. So we can say negative b, but our b is 300, so negative 300, so minus b, then plus minus, which we just say plus, square root of, and we'll say negative b all squared, so negative 300 squared minus 4 times a, which is 1, times c, which is 12,500, all over 2a, which is just 1. Okay, so you see the first answer you get is 250. That is your solution. It's saying x is equal to 250. So what must the factor be for you to have gotten 250? It should be negative 250. So if you say x minus 250 and you take that over, then you get x equals 250. Or, and then change the sign, and that just gives you just put a minus and you get 50. So x is equal to 50. And then what should the factor have been? Should have been minus 50. So there we go. We have our two values. And I'm glad I drew this graph. Now we can actually see which one is going to be our maximum. Okay, because the question is, we need to find out the amount of bicycles they need to produce for the profit to be at a maximum. So which one belongs to the maximum, the local maximum? Is it the 250 or the 50? It would be the 250. So x is equal to 250 because this one is more on the right. It's bigger than this one. This is the smaller one. That's why that's 50. Okay, so we're not taking that. We're taking this. So let's answer them according to how they asked the question. The question is, what should the weekly production be to maximize the profit? They need to produce 250 bicycles weekly. Okay, so now we're on question 7, and question 7.1 says, determine f prime of x from first principles if we have f of x being equal to negative 4x squared. Okay, so this is a place that you can really score marks. You just have to make sure that you're very careful. So we need to determine f prime of x. First, find f of x plus h so that you have that out. Let me also just rewrite f of x so that I don't get confused. So f of x is equal to negative 4x squared. And so f of x plus h would just be negative 4. And wherever you see x, replace it with x plus h. So x plus h all squared. Okay, then we're just going to simplify this. So the negative 4 stays. We need to FOIL this out. Again, you can open up two brackets and write x plus h and x plus h. Or you could deal with this the quick way. So I square the first term, x squared. Then I multiply the first and the second term, which is xh, and then I multiply that by 2, which is positive 2xh. And then lastly, we say h all squared, which gives you positive h squared. Okay, so that's what we have. Then that is going to be, we're going to distribute this. So when it multiplies in negative 4x squared, negative 8xh, and negative 4h squared. Okay, so now we have f of x plus h. And now we can go ahead and derive from first principles. So we're saying that f prime of x is equal to the limit as h tends towards 0. And then you're going to say the formula is f of x plus h minus f of x all over h. let's go ahead and substitute. So lim as h approaches 0, then we have f of x plus h, which is negative 4x squared minus 8xh minus 4h squared. Then we're saying minus. Now, okay, I will still just include this part, but you will just notice that whatever f of x is, the signs that you have there will just change. But it's okay, I'll just work it out just in case there's a mark allocation for actually substituting like that. So minus, but you see that what we are minusing by has one term but a negative in front of it, so you need to put brackets still. So negative 4x squared all over, and then we'll put in that all over h, and this is equal to the limit as h tends towards 0, and we have negative 4x squared minus 8xh minus 4h squared. Then we're going to FOIL that in, so or distribute it. That is positive 4x squared. Okay, and this is going to go all over h. Now, you will notice that, you see whatever you subtracted by, that's what's going to cancel here. So you're just going to have to look for what looks like this, the 4x squared, right? And you can see there we have that. This is negative 4x squared, and it's going to cancel, of course, with that positive 4x squared. So those two cancel. And then let's just rewrite what we have. So I'm writing this, I'm really just looking at this based on, you know, the past papers and we have all seen. They usually had some steps that you should not skip where you are getting marks for. One of the steps was this part. I always used to just ignore that and take out the common factor already. Okay, so I still have to write lim as h approaches 0. Then you see that we want this to come out of that denominator so it's not undefined. So we're going to take out a common factor of h. So h comes out and we have negative 8x and minus 4h. That's what's going to be left on top. And we're dividing by h. Then these two cancel. So I'm just going to rewrite it. So I'll still write the lim. Okay. And then we have negative x. 8x minus 4h. Now we can go ahead and substitute. So now we're substituting. We don't have to write the limit as h approaches 0. So negative 8x minus 4, open bracket, and in place of h we'll put in 0 because it's approaching 0. Okay, so the gradient is going to be negative 8x, and that is the gradient of that function that we had originally. Okay. Just to make sure that you are correct, you can go ahead and derive this using the power rule so that you see that you have actually derived that properly. Okay, so power rule, negative 4 times 2, negative 8. And as you can see, that is exactly what we have here. Okay, so you can just make sure you do that. The next question we have is 7.2. So 7.2, this is what we have. In 7.2, we have 7.2.1, you have to determine f prime of x if f of x is equal to 2x cubed minus 3x. So this is just from the rule, and this is a simple one, you know, no complicated things. We're just going to derive that. So let me just go ahead and say f prime of x is equal to, so I'm going to say the 2 times the 3, which is 6, and we have x. Then you're going to take the 3 and subtract a 1 from it, which is 2. Then we have a coefficient of negative 3 multiplied by the exponent of an invisible 1, okay, which gives you still negative 3. Then you have x. Now you're going to take that exponent that you had there, which was 1, and you need to subtract a 1 from that. If you subtract a 1, you're going to get 0. But then anything to the power of 0 is equal to 1. And if you have negative 3 times 1, it just stays negative 3. Okay, so this is f prime of x. Okay, moving on to the next one. In the next one, this is what we have. We have dx, and I'm just going to rewrite this one. We have 7, the cube root of x squared, plus 2x raised to the power of negative 5. So it's nice that they already put that in a form that you don't have to move it yourself, because normally it should have been on the denominator. Then you would have to actually push it up to the numerator, but they've already done that for you. So it's only the surd that we need to look at. Okay, so with the surd, how to simplify a surd, or really how to write a surd with a rational exponent, is like this. We're still going to write dx because we have not derived yet. Okay, and I'm not really supposed to write equal to because you only write equal to when you are deriving. Right now I'm not deriving, I'm just trying to put it in a form that will help me to be able to derive this. Okay, so we just still have dx, and then this is what we're going to do here. You see this 3, right? That belongs to your x, that whole surd. If you want to write a surd in its standard form, but let's just put down the 7 first. So we still have the 7. Now we need to write this in a way that its exponent is rational, not really a standard form. So this is what we're going to say. We'll leave the x, and then you're going to say the inside exponent divided by the outside exponent. Okay, it's just in over out. Okay, then moving on, we have plus 2x raised to the power of -5. And now everything is perfect and ready to be derived. Now we can just say is equal to. And so you're saying coefficient times exponent. So what is 7 multiplied by 2/3? You can use a calculator if you want to. 7 times 2 is 14, so 14/3. 14/3, and we have x. And then you're going to take from this exponent and you subtract 1 from it. So what's 2/3 minus 1? Well, it's like saying minus 3/3, but you can use a calculator. 2 minus 3 is -1/3. Okay, denominator stays the same because we're subtracting. Then we have positive 2 multiplied by -5, which is -10x. Then your exponent is -5. You're going to subtract a 1 from it, -1, which gives you -6. Okay, and that is our answer. So this is for 3 marks. So there is no really a requirement for you to, write the things that are negative, okay, as a positive exponent. You don't really have to write those as a positive exponent. At this point, it's okay. Okay, and because it's 3 marks, you're getting a mark for writing it in the format that it's supposed to be so that you can derive. You're getting a mark for that. You get a mark for each term, really. But this one, you didn't have to write it in that format. It already came in that format. And then you get a mark for deriving each of the terms. So you derive that and derive that. So that's 3 marks. Okay, moving on to the next question. Okay, so the next question, 7.3, says, for which values of x will the tangent to f of x is equal to this, okay, have a positive gradient? Okay, so first of all, let's look at the type of graph that we have. We have f of x is equal to -2x cubed plus 8x. So first of all, we can already see that this is a cubic function. And do you see that the a value, okay, that coefficient of x cubed, that a value is negative. When your a value is negative in a cubic function, your graph is going to look like this. It's really an n, like a capital letter N, but backwards. When it's positive, it's going to look like this. I also explained these in the other videos as well. So that is one thing that we need to think about. So it looks like this. And now what they're asking us is, we need to tell them the values of x for which a tangent, right? So if you had a tangent drawn to this graph, right, that cubic function, we need to find out the values of x for which that tangent's gradient is going to be positive. So let's break that down. Let's break down that question. They're saying the values of x for which the tangent to that will have a positive gradient. Okay, if there was a tangent drawn to this curve, right, you need to know something about tangents and curves. When you have a tangent drawn to a curve, all this means is that, you see at this point of contact with the tangent and the curve, the gradient of the tangent and the gradient of the curve are exactly the same. So think about it. If the gradient of the tangent and the gradient of the curve are exactly the same, what they're really asking you is, you need to determine the values of x for which this curve will have a positive gradient. Because if the gradient of the tangent is positive, then the gradient of the curve at that point is also positive. That's what they're asking you. So you need to determine the values of x for which this curve will have a positive gradient. Okay, so let's think about positive gradients. So when a gradient is positive, let's actually explain that with a line. I'm trying not to take too much time in explanations. So when we're thinking about a line that has a positive gradient, that line is going to be an increasing function, meaning it's going to be moving up like that. So when you see a graph, okay, or curve, any type of function, and it is increasing, it means that its gradient is positive. So the cubic function has places where it increases and places where it decreases. Just remember that you need to read the increasing and decreasing from the left to the right. This is moving upwards, so it's increasing. So let's look at that with this graph. Which places do we find that the graph is increasing? Okay, so if we read it from the left, like just from here, right? Look at what the graph is doing. You always move from left to right. The graph is doing what? Decreasing. Then it does something. Here at the turning point, it stops decreasing. Okay, it's neither increasing nor decreasing. Its gradient is standing still. It's stationary. That's why it's called a stationary point. So the gradient is equal to 0 at the turning point. Then what happens at this point over here? Let me highlight that in purple. What happens here? The graph starts to increase. So what does that tell you about the gradient? The gradient at this point is positive. Okay, so, and then of course at the next turning point again, the gradient stands still, is stationary, and then of course there it decreases. So this is the place that we're looking for. We're trying to find out for which values of x, okay, this graph has a positive gradient. We know that it has a positive gradient all through here. Now, do you see an important point that you need to find in this f of x? It is the turning points. Because if you find the turning points, you will know that in between the turning points, whatever this number is, this graph is going to be increasing for values that are greater than whatever that first turning point x value is, but less than whatever that second turning point's values are. It's in between these two numbers. So that's the next thing we need to do. We need to actually find the turning points of this curve. So since we need to find the turning points, our equation, first of all, is f of x is equal to 2x cubed plus 8x. And how do we find the turning points? Okay, remember what happens at the turning points. The gradient is equal to 0 because it's stationary. Since the gradient is equal to 0, we're going to take this curve and find the gradient by deriving it. When you derive the function, you're finding its gradient. Okay, so negative 2 times 3, that gives you negative 6x. 3 minus 1 is 2, and then we have positive 8, and then of course you know it has an exponent of 1. You subtract 1 from it, becomes 0. Anything to the power of 0 is 1, and so 1 multiplies by 8 and just stays 8. Okay, great. We found the gradient of this curve. We want to find the turning point. The turning point, okay, has a gradient of 0. Hence, we are going to make the gradient equal to 0. So we're saying 0 is equal to negative 6x squared plus 8. Okay, then I'm going to go ahead and take this over so that it can become positive. You see, we're going to solve for x here. The x values are going to tell you the x values of your turning point. So that is 6x squared is equal to 8. And I can get rid of the 6. Divide both sides by 6. We have x squared is equal to 8 over 6. You see that 8 and 6 have a highest common factor of 2. So 8 divided by 2 is 4. And then 6 divided by 2 is 3. So this is what we have. So do you see that this is an equation? So we can get rid of this squared by square rooting. But when you square root, you need to remember that this is an equation. So you have two solutions. That exponent 2 has two possible solutions. Okay, so we're going to say plus and minus. And so x is either equal to positive. And you see, when something is square rooted, the fraction, as a fraction, if something is square rooted, you really square root in the numerator and the denominator. So it's like square root of 4 over square root of 3. Okay, square root of 4 is 2, so that's 2 over square root of 3 because that's an irrational number. I cannot really square root that number. Okay, so that is positive 2 over square root 3, or x is equal to negative 2 over square root 3. Okay, so there we have our two x values of our turning points. Remember, all we need to do is tell them that. So we're going to have to put one here and one here. So since this one is on the left, it's the smaller one. That's what's going to go there. Let me just bring that graph down. Okay, so this is the values that we have. The one that will go here would be the negative one because it's more on the left. So that's negative 2 over square root 3. It's the smaller one. And this one is positive 2 over square root 3. Okay, now that we have that, we know that the values of x for which this graph will have a positive gradient would be this. This is how I'm going to conclude this. I'm saying therefore it's where x is bigger than negative 2 over square root 3, because you see it's all of these values in between these two numbers, bigger than negative 2 over square root 3 but smaller than 2 over square root 3. So I'm saying x is greater than negative 2 over the root 3 but less than positive 2 over root 3. And that is our answer. Okay, moving on to question 8. So we're done with that one. Okay, so moving on to question 8, more calculus. So question 8 says, given f of x is equal to negative x cubed plus 6x squared minus 9x plus 4. And they have also said it's equal to this, which is lovely because they've already factorized it for us. So we don't have to factorize it when maybe finding x-intercepts. Okay, so 8.1 wants us to determine the coordinates of the turning points of f. Okay, we just determined the turning points, or rather the x values, in question 7. So we now know how to do that here. Okay, so 8.1, to determine the turning point, you derive the function first. So that is negative 1 times 3, which is negative 3x. Then subtract a 1 from that 3, which is 2. Okay, and then we have positive 6 times 2, which is positive 12x. Subtract a 1 from that 2, which is 1. I don't have to write that. Then negative 9. And of course, the x falls away because it gets raised to the power of 0, which becomes 1, which multiplies to the negative 9. So now that we've derived it, we will set that equal to 0 to find the turning point. And then we have negative 3x squared plus 12x minus 9. Okay, so you can go ahead and factorize this. I'm noticing a common factor of negative 3 all through this. So I'm going to go ahead and just divide both sides by negative 3. And I'm going to have 0 is equal to positive x squared. And then positive divided by negative is a negative. So 12 divided by 3 is 4x. And then that gives us positive 3. Okay, so factorize. 0 is equal to, open up 2 brackets, x times x. Let's think about factors of 3 that can give us 4. Well, that can be 3 and 1. But you see that only the middle is negative, right? Because this is positive, the only way you could have gotten this is by saying negative 3 multiplied by negative 1. And that's how negative 3 minus 1 also gives you negative 4. So we have minus 3 minus 1. Okay, so this means that x is equal to positive 3, or x is equal to positive 1. So now that we have our x values, we can go ahead and find our y values because we need to find the coordinates of the turning points. So we're going to say f of 3. Now you don't have to go ahead and substitute the whole thing. You can just say f of 3, substitute, and find out those values. So I'm just going to do that. Okay, so what we get is 4. Okay, for substituting, we get that. And so the second one, we have to substitute the x value of 1. So again, f of 1, and now just go ahead and substitute. And then we get 0. So as you can see, that is an x-intercept. Now that's okay, it's still a turning point as well. So it's one of those situations where the graph is sitting on the x-axis, maybe something like that, like on the x-axis. Okay, so our turning points are finally, the first turning point is we have 3 and 4, so 3 and 4. And the second turning point is 1 and 0, which is of course also an x-intercept. So that is 8.1 done. Moving on to the next question. The next question says, draw a sketch of the graph of f, clearly label all intercepts with the axes and any turning points. Okay, so we just have to draw the graph. Let's think about all the things that we need when we need to draw a graph. You have your turning points. You also need your x-intercepts. So we can go ahead and solve that problem now. Let's find the x-intercepts. Let's talk about the y-intercept. This one is actually simple to solve in this case. So do you see that the function is in standard form? And they also factorized it for you. In standard form, you see the last variable without any letter. Okay, the last number is 4. That is going to be your y-intercept. Okay, so it's that d at the end plus d. It's your y-intercept. Remember, the y-intercept always has an x value of 0. So your y-intercept as a coordinate is 0 and positive 4. So we got that sorted out. Now we just have to clear up the x-intercepts. The x-intercepts, they've already factorized this for you. So I'm just going to go ahead and say f of x is equal to, and I have x minus 1 all squared times negative x plus 4. And I'm just going to go ahead and simplify this. So as you can see, this format is the type where you have an x-intercept that is also a turning point. Just take note of that. So to find the x-intercept, we're just going to set these brackets equal to 0. So I'm really just saying that x minus 1 all squared is equal to 0, or negative x plus 4 is equal to 0. So in this, let's go ahead and just The 0, if you like, you can square root both sides. You don't even need to say positive or negative because 0 is neither positive nor negative. So we have x minus 1 is equal to 0. Then we're taking negative 1 over, and so x is equal to positive 1. That's our first intercept. We already knew that one. And then this one, I will just take x over because it's negative. So 4 is equal to x. So we have 4 and 0. Okay. So these are our turning points, 4 and 0, and of course 1 and 0, but we already had that one. So we have everything now we need. We have our turning points, we have our y-intercept, and we have our x-intercept. Okay, so I'm just highlighting that because we already have that there. So just go ahead and draw your graph. Okay, so to draw the graph, let me just go ahead and draw a set of axes. So a y-axis and an x-axis. So here's our y-axis, and that's our x-axis. And I'm not even going to draw numbers on it because it's really not necessary. You don't really need the numbers. So now the next thing I'm going to do is just put down some points that we have. First point I can go ahead and put down are the turning points because it really helps to see the shape of the graph. So the turning points, let me start with the smaller one, 1 and 0. That is an x-intercept. So I'll say 1 is somewhere here. So I'm just going to put that 1. Okay, and then the next turning point is 3 and 4. So that is more on the right. 3, okay, and then 4 up. So I can even just use these lines. 1, 2, 3, 4. Okay, 4 up. So that is a point that we have. 3 and 4. This one is 1 and 0. Let me actually highlight the points in red. So 1 and 0. So those 2 points are there. Then the next thing that we have is the y-intercept, which is 0 and 4. So remember, it is on the y-axis. Let me actually just label the axes. So it's on the y-axis and it's a 4. Interestingly, this has a y value of 4. So it's in line with this one. Here's your 4. Okay, so it's here, that point. Then the next point that we have is just 4 and 0. That's an x-intercept. 4 and 0, since this is 3 over here, 4 and 0 will just be more further to the right. So that's 4. So that is 4 and 0 as our x-intercept. Okay, so everything just looks very scattered right now, but we're just going to tie it all up together. You can easily see the way the graph looks because first of all, you have f of x is equal to negative x cubed. When the coefficient of a is negative, then your graph is going to look like a backwards N. So we already know that. Now you need to remember where your turning points are. Your turning points is this and this. So since those are our turning points, all we're just going to do is we know that this is where it's going to curve. Since it looks like that, it's going to curve like that. Okay, so our graph is just going to look like this. It's really just going to go like that, down and curve. Then it's going to go up and then reach there and curve, and then go down, of course, touching the x-intercept. Let me just get that right. Okay, so there we go. That's what it's just going to look like, something like that. And you're really just getting marks for those important points. You see, it's only 4 marks. You're getting marks for labeling those points, or really they just want to see the shape of it and the points that you have. Okay, so that is question 8.2. And we're done with that. Moving on to the next question. Okay, next question. Question 8.3 says this. So it says you have to use the graphs, right? Use the graphs to determine the values of k, value or values of k, for which this, it's still the same function, but they're making it equal to k, will have 3 real and unequal roots. So they have to be real and unequal. Okay. Let's start off by looking at what we have here, right? They said negative x cubed plus 6x squared minus 9x plus 4 is equal to k. This is the equation that they gave us, right? They're making this equal to k. We need to find out the values of k for which it's going to have 3 real and unequal roots. So first of all, take k over. So we have negative x cubed plus 6x squared minus 9x plus 4 minus k is equal to 0 because there's nothing here now. So that's the roots, right? Where this is to find the roots. So we need to find out the values of k for which that graph is going to have 3 real and unequal roots. Okay, let's look at the way this graph looks right now. This graph currently has how many roots? It has 2 roots, okay? those are x-intercepts. It has 2 x-intercepts. We needed to have 3, and they need to be real. Another thing that we should also take note of is the fact that this k is negative, but we'll get to that. Let's just look at this quickly. Okay, so how should we move this? Well, if you look at k is saying negative k. So it's already indicating that we're going to have to move down. Okay, it's already minusing. Well, it's not indicating it for you. It could have also been positive. Then you would have had to just sort that out yourself. But it's negative, and right now it's really in our favor. So it's negative, but let's look at this graph. How can we move this graph in a way that it's going to have 3 roots? Well, it has 2 roots right now. If you think about it, if you move the graph up, right? Like if the graph looked like this, it will only have 1 root. And we don't want that. We want it to have 3 roots. Okay, what if you decided to move the graph down? Like from where it was, we move it down. Look at what happens when you move it down. Do you see that you have a root here, here, and here? 3 roots. That's what you want. If you keep moving it down, it keeps having 3 roots. 1, 2, 3. Until you move it to this point. Then it has 1, 2 roots. So you see that if you move it anywhere within this region, you're always going to have 3 roots. And that's what we want. So how did we move the graph? We moved it down. So we know that we need to move this graph down. That's great. But how far down should we move it? Well, let's measure how far down. It was here at first, right? So we can focus on this, 3 and 4. You see that y value is 4, right? When we moved it down to this point, what is the y value now? The y value is 0. Okay, so you moved it down by how many units? By 4 units. So this is how we can think about it. Because this already says minus k, it's really in our favor. It's already telling us, okay, we're moving down because it's a minus, and that's great. So we just need to tell them by how many units we need to move. Okay, we don't have to manipulate that number, think about whether it's going to be positive or negative. It's already minus, telling us we're moving down. So how far? Well, first of all, if you move it anything more than 0 units, because moving down already, right? If I move 1 unit down, I have 1, 2, 3 roots. 2 units down, 1, 2, 3 roots. So if I move it anything more than 0 units, it's going to have 3 roots. But I shouldn't move beyond what number? I shouldn't move beyond 4 units. Because when I reach 4 units, then you see that this now has 1, 2 roots, 2 x-intercepts. Okay, so that's what I can say here. I can say that the value of k just needs to be, it can be anything more than 0. It can be greater than 0, right? It can move anything more than 0. It can move 1 unit, 2 units, but it must not move beyond 4. So it must be greater than 0, but less than 4. And they made it really simple by putting a positive k there. So we didn't have to overthink the whole thing. Okay, so that is the answer for that question. Moving on to the next question, we have 8.4. Okay, so 8.4 says this. It says, the line g of x is equal to ax plus b is a tangent, okay, to f at the point of inflection of f. Determine the equation of g. Okay, this is not a bad one. It's actually quite a simple one. They're telling us that, you see this graph that we have, remember it looked like that? There is this graph g of x, and g of x is a tangent, so it's a straight line. So we have this tangent to this graph, but it's a tangent at the point of inflection. Well, the point of inflection is really just the point where this graph changes from concave up to concave down. That's all. So it's a tangent at the point of inflection. So it's kind of like, let me just try and get that right. Something like that, right? It's at the point of inflection. It's touching there. So how do we find this equation of g of x? Well, we have the equation of f, which is great. And they told us that this is a tangent to this at the point of inflection. This tangent is a straight line. In order to find the equation of a straight line, you just need the gradient of the straight line, right? And you just need at least 1 point so that you can go ahead and use that to find c, or the y-intercept, okay, in y is equal to mx plus c. So how would we find the gradient of this straight line? Well, unfortunately, you don't have 2 points that you can use to find the gradient. So we're not going to find the gradient using the traditional method, but we do have the equation of f. We have f of x. Since we know f of x, we can derive it to find the gradient. And we're going to derive it to find specifically the gradient at the point of inflection. That's what we're going to do to find that gradient. Okay. But you see now, in order to do that, you actually need the point of inflection. So you need the x and the y value. Well, just the x value for the gradient, but you need a point. So first things first, we need to find that point of inflection. Let's go ahead and find that. Since we know that the equation of this graph or function is f of x is equal to negative x cubed plus 6x squared minus 9x plus 4, to find the point of inflection, remember, you get the second derivative and set it equal to 0. So let's first of all derive, which we already have, but I'll just derive quickly. So that's negative 3x squared plus 12x minus 9. Then derive it again. And so this is going to be negative 6x. When you subtract 1 from there, that becomes a 1. You don't have to write that. Then plus 12. The x falls away, remember, because x to the power of 0 is 1. Then you're going to make the second derivative equal to 0. So we have negative 6x plus 12. Then we're going to take this negative 6 over because it's negative. So positive 6x is equal to 12. Divide both sides by 6. And so x is equal to 2. Here's our point of inflection, the x value of our point of inflection. And that's great. We can just go ahead and just find the y value of the point of inflection while we're at it. So the y value of the point of inflection, how do you find the y value? It's a point, okay? So it's on the graph. So to find its y value, take the x value and substitute it into the original function so you can get its corresponding y value. So that's going to be f of 2 is equal to, and I'm just going to substitute. So f of 2 is equal to 2. That's what we get. So that is 2. The y value of the point of inflection is 2. And now lastly, what do we have to find? We have the whole point, right? The point of inflection, the point on the straight line is 2 and 2. Okay, so now that we have the point of inflection, what else do we need? Remember, we needed a point and the gradient of this line. Okay, to find the gradient of the line, we're going to take the derivative, we're going to derive it, and then find out exactly what the gradient at this particular point is. That will be the gradient of this tangent. So the gradient at where the x value is equal to what? We found the x value of that point of inflection. We'll find the gradient where the x value is equal to 2. So I'm saying f prime of 2 is equal to, and I already have the gradient of that. So f prime is equal to negative 3 times 2 all squared plus 12 times 2 minus 9. And just substitute that, and this will give you the gradient where the x value is equal to 2 of this function. Okay, and we can see that that gradient is equal to 3. So we have the gradient of that tangent. It's equal to 3. Okay, and now almost everything is done. So remember that g of x is equal to ax squared plus b. That is just a straight line. You can go ahead and find the equation of a straight line. So we're saying y is equal to mx plus c, and we know that our gradient is 3. So we're saying y is equal to 3x plus c. And now in order to find c, you need to substitute a point on that straight line, which is the point of inflection 2 and 2 that is on the straight line. So we're going to just say 2 is equal to 3 times 2 plus c. And so 3 times 2 is 6. So we're saying 2, and then positive 6 is coming over, minus 6 is equal to c. So c is equal to what's 2 minus 6? Negative 4. So it finally means that y is equal to 3x minus 4, and that is the equation of g of x. Since they didn't say write it as y, I would just write that as g of x. I'll say g of x is equal to that, and that is our equation. Okay, so that is 8.4. That is a question that can come up in different ways, really. Moving on to the next question, 8.5. Okay, so the last question says calculate the value of theta, the acute angle formed between G and the x-axis, sorry, in the first quadrant. Okay, so it's the angle formed between G and the x-axis in the first quadrant. So just look at what G looked like, right? G of x was this straight line. So if I just erase this, really what they're just saying is, okay, this straight line of G, right? You have your x-axis, you need to find the angle of the acute angle, okay, formed by the x-axis and that straight line. That is the angle of inclination of this G. Okay, so that is the theta they're talking about. So if you have to find the angle of inclination of a line, you know that this is G, of course. So the angle of inclination, theta, you find that by just saying tan of theta is equal to the gradient. What is the gradient of G? Well, we found that. We know the gradient of G is 3. So tan of theta is equal to 3. And then I'm just going to find theta. So I'll say theta is equal to, we are going to take tan over, or in other words, you're just going to find the inverse of tan. So the second function of tan and then of 3. So you can just do that on your calculator. So we're saying shift tan of 3. Okay, so did they say anything about rounding off? No, nothing like that. Okay, so theta is finally just equal to, we'll round off to 2 decimals, 71.57 degrees. Okay, so that is that. It seems like a question they just decided to throw in that would really just help. It's 2 marks. It's a good question to at least just throw in to help to increase the mark. Okay, so we're done with question 8, and now we finally move on to question 9. Okay, so for question 9, I just decided to increase this because I really couldn't see what's going on. Okay, so they say the diagram below represents a printed poster. So this is a printed poster, okay? Then they say rectangle ABCD is the part on which the text is printed, okay? This shaded area, ABCD, is 432 centimeters squared, and AD is equal to X. So they're telling us a lot. They told us the area of that shaded part, and they told us that AD is X. Okay. Then ABCD is 4 centimeters from the left, okay, left and right edges of the page, and 3 centimeters from the top and bottom of the page. So 4 centimeters and 3 centimeters like that, okay. The first question is for us to show that the total area of the page is given by this equation. Okay, so you see the whole goal is find the area of that entire page. That's what we need to do. Okay, 9.1. How do we find the area? Well, you know that the area of this shape, a rectangle, is always going to be length multiplied by breadth. That's all, right? So let's see if we can find each of them, the length and the breadth. If we can find expressions for them, of course. It's not going to be a simple number because this is in terms of x. So an expression for the length, first of all. How do we find the length of this? Well, do you see that they told us that AD is x? And we know that this, right, from the left and the right, they're both 4 centimeters. So if you add them all together, that's 4 centimeters plus x plus 4 centimeters. So the length of this page, we can just call that, since it's 4 plus x, we can just call that x plus 8. I'll just call it x plus 8. It just looks better as the x that's in first. So that sorts out the issue with the length, right? It's in terms of x, and this is in terms of x as well. So now we have to find out exactly what the breadth of this page is going to be. Okay, so to find the breadth of the page. So the breadth of this page, this entire thing, we also know that this is 3 centimeters. So if you count, it's like 3 centimeters, also 3 centimeters, 3 centimeters. But what's AB? How do we find AB? Well, that's probably where this comes into play. So they said that ABCD, the area of it is this. So how about we find an expression for the breadth using this information? They told us that AD was x centimeters, right? So to find the area of the page, that's the area of, not really page, sorry, the shaded part, first of all, we can use that to find an expression for AB, because that's what we need. We need an expression for AB, okay? So the area of, I'll say shaded, right? That's what we're looking for. Okay, so that would be, of course, the AB multiplied by the AD, which would give you that area, which they told us is 432 centimeters. But remember, we have AD already. So I can just say that we already have that as X. Okay, so since we already have AD as X, to find AB, we can just go ahead and make this the subject. How do we make AB the subject? Well, X is being multiplied to AB. So to get rid of the X, we're going to have to divide both sides by X. And of course, X is not equal to 0 because it's a length. Length cannot be 0 because this is a physical page we can see. Okay, so AB is equal to, that just is 432 over X. That is the expression for AB. So this now makes finding the breadth of this page easier. So to find the breadth of this page, we're just going to say it is that AB, right? That piece, which is this 432 over X, plus that 3 centimeters, because that's what fills up, that's what makes up the entire breadth. The 3 centimeters plus the 3 centimeters, which is 6 centimeters really. So this is an expression for the breadth of this entire page. Okay, great. We have the length and the breadth of the page. How do you find the area now of the page? So area of page. Area of page is always going to be length times breadth. So the length that we have is X plus 8. That's X plus 8. The breadth that we have is this. It's also 2 terms, so I'll put a bracket. So 432 over X plus 6. And now we just have to simplify. Okay, since they said A of X, I'm also just going to say A of X is equal to that. Just simplify by foiling out. Okay, so we're saying is equal to, and we're going to distribute this out. Let me just push this up a little bit. So if we distribute it, you're saying the X multiplied by this. You see, if X multiplies by 432 over X, the X and X are going to cancel diagonally. That's gone. So you only have 432 left there. Then the X multiplies by the positive 6, which gives you positive 6X. Then the 8 is going to multiply to this. Okay, and as you can see, 8 times this as a fraction, 8 times 432 over X. The 8 and the 432 are just going to multiply. So let's just find out what exactly that's going to be. 8 multiplied by 432, that gives you 3,000. So this is going to be positive 3,456. And then over X. The X is not cancelling here because there's no X here to cancel. Okay, that's what we get there. And then 8 multiplied by 6, that is going to be plus 48 that we get. Okay, so this is what we have. Just make sure that all your like terms are together. So it means that A of X is finally equal to, and we're saying, since they put that first, I'll also just put it first. So 3, 4, 5, 6 over X, then plus 6X that we have. And then of course the 432 plus 48. So that's going to be positive. Well, 32 plus 8 is going to be 40. So 40 plus 40 is 80. So that's positive 480. And it's exactly what they have there. So there, that is our final answer. So we got that. Okay, next question, 9.2. 9.2 says, determine the value of X such that the total area of the page is a minimum. Okay, so they're not asking for the area that will be a minimum. They're just asking for the value of X. That's all. So how do you find the value of X for which this is going to be a minimum? You're going to have to use calculus. So this is a question that probably grade 11s will not be able to solve. The reason why is because, as you can see, this is not even a parabola. Okay, grade 11s can solve the ones that have parabolas because you can just use turning points equation. But since this is calculus that we're just going to have to use to find for which values of X something will be a minimum or maximum, you first derive that, okay, and you set it equal to 0. And the idea is that at the minimum or maximum value, okay, of a curve, that's usually the turning point. The turning point is a place where the gradient is standing still, so the gradient is equal to 0. That's why we derive and make it equal to 0. Okay, so now that we have this, we're just going to have to derive that. But I can see it's not ready to be derived, so let me just rewrite it. You see that x needs to come to the numerator. So we have 3, 4, 5, 6. X raised to the power of negative 1. That's what happens when it comes to the numerator. Its positive 1 exponent becomes negative. Then everything else is fine. So 6x plus 480. Okay, now we can go ahead and derive. So we're going to say a prime of x is equal to this multiplied by negative 1 is just negative 3, 4, 5, 6. X raised to the power of negative 1 minus 1 is negative 2. Then we have positive 6. Positive 6, and of course the x 1 minus 1 is 0. Anything to raise to the power of 0 is 1, and so it multiplies to the 6 and stays 6. So this is what we have. It's the gradient of this function. We're going to set the gradient equal to 0. And so it's negative 3, 4, 5, 6, x raised to the power of negative 2 plus 6. Okay, I'm going to take this over since it has a negative value, right? It's negative. So positive 3, 4, 5, 6, and x, I can bring that to the denominator so that x exponent, the exponent on x can become positive 2, is equal to 6. Okay, then in order to solve for x, we can go ahead and just cross multiply. Or we can also just look at it as, oh, I'm going to move this over there and move that over there. But let me just cross multiply so that it doesn't, look confusing. So cross multiplying, that's going to be this multiplied by that is 6x squared. Then this multiplies by this denominator, which is actually a 1. Okay, and that is 3, 4, 5, 6. Then we can divide both sides by 6. Hopefully that number divides by 6, but it doesn't matter. Divide by 6. Okay, it does. So x squared is equal to 576. Then this is saying x squared. So you need to find the square root of both sides. So square root both sides, but it's an equation. When you square root both sides, this is going to be positive or negative. So either x is equal to, what is the square root of this number? So I'm just going to say square root of 576, and that is 24. Either x is equal to positive 24 or x is equal to negative 24. Okay, let's think about that carefully. Remember what x is, right? X is a length. It's a distance. Can we ever have a negative distance? No. Even if you walk backwards, it's not going to be negative, okay? Because you're still covering a space, so it's positive. So we cannot even take this one. Therefore, it means that x is actually equal to positive 24 centimeters, and that would be our minimum value. Question 8, 8.1 says we have to determine f prime of x from first principles if f of x is equal to 1 over x. Okay, so something you can actually do first before deriving it is you can use the actual rule of derivative to derive this function first, and just to make sure that you have the right answer, so that when you derive using first principles, when you get your answer, you can compare it to that. So we have f of x is equal to 1 over x. Okay, what we can do is prepare this to be derived. So f of x is equal to, the problem now is x is on the denominator. It shouldn't be on the denominator, it should be on the numerator so that you can properly derive it. So when you move it to the numerator, there's a consequence for this. It means that your exponent, which originally was 1, right, it's going to become negative. So it's now negative 1. And then now it's ready to be derived. So you can say f prime of x is equal to 1 times negative 1 is negative 1. And then x to the power of negative 1, subtract 1 from that. So you have x to the power of negative 2. Then if you put this in a way that its exponent is positive, this is just going to be negative 1. Since this is on the numerator and the exponent is negative, you bring it to the denominator, which makes the exponent positive. So we already know what the answer is now. And let's just go ahead and derive this using first principles, okay? From first principles to see whether we're actually going to get to that answer. So let's go ahead. When you are deriving from first principles, you're going to use this formula. So this is really the formula for the gradient of a function. We have f of x and we have f of x plus h. So we have to first find f of x plus h. So I'm going to go ahead and find that and say f of x plus h is equal to, meaning wherever I see x in my function of f of x, I'm just going to replace it with x plus h. So I have 1 over I see x. I'm just going to say plus h. Okay, so really just add in an h to the x. So now we know what that is, and we can go ahead and use our formula. So we're going to go ahead and say that this is equal to, and we're saying the limit as h approaches 0. You'll keep saying this until you get to the substitution. So this is f of x plus h, so we put 1 over x plus h. And then minus f of x, right, which is 1 over x that we have there. And all of this is being divided by h. Now, this looks quite complicated, and you don't have to write it like that. What you can do is, the numerator, write that as one term, right? So I'm going to leave that as 1 over x plus h minus 1 over x. And then I'm dividing by h, so divided by h. Since these are fractions and this is not a fraction, we can make it a fraction by putting it over 1. Okay, so that's what we have. And then this is equal to, we're still going to have the limit as h approaches 0. And now we have to work on this fraction. So do you see that you're subtracting in a fraction? When adding or subtracting in fractions, you need to make sure that the denominators are the same. So how would we make the denominators the same? If you look at these fractions separately, the only way to make the denominators the same is to really multiply them by each other's denominator. So this one you'd multiply by x, and so what you do on the bottom, you must do on the top. This one, you would multiply by that x plus h. So times x plus h and times x plus h, right? But of course, as like that. So that's actually what's going on there, because you can't multiply this one by h. It's not going to work. If you multiply it by h, and I've seen students say multiply it by h because they see a plus h here. The thing is that's going to become an xh. So that's not the same thing as x plus h. So that's what we do there. And so our common denominator is going to be, as you can see, since this is two terms being multiplied by one term, you have to write it as x times x plus h. That's your common denominator. And the numerator that we will have, let's just be very careful here. 1 times x is just x. That's fine. But please note that we have a minus here. So if we have a minus first, and then we have this, you see, it's the 1 times the x plus h. Since we are multiplying by something that has two terms, we still have, if you look at it as if the 1 is still there, it's really like 1 times x plus h. You see that now that negative is going to affect what you have in your brackets. Okay, so that's kind of what's going on there. Then we have divided by, and we have, instead of making this division, we can use, since we are dividing by a fraction, we can use the rule called tip and times, meaning you tip the fraction, you swap the numerator and denominator, and you change the division sign to a multiplication. So this is what we have, and then we can say is equal to the limit as h tends towards 0, and we can simplify that. That is going to be x. When you distribute, you get negative x and negative h over, we still have here x times x plus h, and then this is being multiplied by 1 over h. Okay, so now that we have this, you can see that the x and the x would simplify to 0. So there on the numerator, I still write this because I've not substituted yet. So negative h over, and you have x times x plus h multiplied by 1 over h. So when multiplying fractions, you can cancel common factors if they are in a top-down position. So like there's a common factor on top and the bottom. But you can also cancel common factors diagonally. So do you see there's an h there and an h there? So that cancels. It's like h divided by h is 1. So there's a placeholder of 1. And h divided by h there, still have our placeholder. So this is equal to the limit as h tends towards 0. And we're going to say negative 1 times that 1 that is still there, which is negative 1, over, and here it is this times the placeholder of 1 remaining, which stays the same. Okay, then we are now ready to substitute. We've gotten the function to a point where if you substitute h, it's not going to make it undefined. You see, if you had substituted h here, your denominator would have been 0, and so this would be undefined. So that's the whole purpose of simplifying. Okay, so now we can finally substitute. So we're just saying that f prime of x is finally equal to, say, negative 1 over, in place of h, you're going to put 0. So x times x plus 0. And f prime of x is equal to, we have negative 1 over, now you see x plus 0 is equal to x. So x times x is x squared. And you see we get the answer that we got when we use the rule. So use the rule just to check and make sure that your answer is correct. Okay, so that is 8.1 and we move on to 8.2. Okay, so we're finally on 8.2 and 8.2 says we have to determine the derivative of this function. So d over dx. So with this, I'll just say, just pay careful attention to notation. You will notice that these ones that have this, some sort of derivative instruction, and then you have your brackets. The thing about them is you first have to prepare your function to be derived, or your expression to be derived. After preparing it, then you go ahead and derive it. So just take note of how we're going to write this. An alternative to writing it this way, you could have also written it like, they could have also written it like that, and then, put the function in. So you would do the same thing that we're going to do here in this situation. Okay, so what we do here is we're going to go ahead and say, because we're not deriving yet, we'll keep writing d over dx. And then let's go ahead and simplify what we have here. So the ground rules are, where you have an x, it should not be a surd. Okay, anything that is a surd and an x, you need to kind of change it. But if you have a number that is a surd, it's fine, because that number is just a number. Okay, so you don't have to change numbers that are surds, but you have to change variables that are surds. So let's go ahead. We see here, this has to be changed. Since it's being square rooted, we can square root it. The square root of 4 is 2. And the square root of x to the power of 6 is x to the power of 3. Because what's actually happening is you have the square root of x to the power of 6. This root has an invisible 2 here. You keep the base the same and you say the inside exponent divided by the outside exponent. And that's how we get that. So that's what we have there. And this is now fine. See, we have x to the power of 3. That is perfect and ready to be derived. Then here, is there anything that you need to change there? No, there's nothing you need to change there because your square root is on its own. The x is not under the radical, so you can leave it like that. It's just plus the square root of 2, and we have x to the power of 2. Okay, so that's what we have there. Now we are ready to derive, and because we are deriving, I say is equal to, and I go ahead and start deriving. So coefficient times exponent, that gives you 6, and we have x to the power of, subtract the 1 from the exponent, gives you 2. Then here, coefficient, the square root of 2 times exponent, gives you positive 2 square root 2. Then x squared minus 1 gives you 1, which we don't have to write, and that is our answer. Okay, so that is our answer there. Moving on to the next question. The next one is another derivative question. We have 8.2.2. We need to determine g prime of x if g of x is equal to this. So let's look at this. Do you see that there is a denominator of x squared? We shouldn't have that. Now, I know normally you would think, okay, maybe we need to move this to the top. That wouldn't work in this case, because I want you to see what's actually going on here. Do you see that you have 3 separate terms and all of them are being divided by x squared? We can actually expand that. So how they came about to be like this is because they were probably written like this before. So it was g of x is equal to 3x to the power of 4 over x squared. Okay, so each of them would have had this common denominator of x squared. That's why when you added them together, they looked like that. And then you'd have had minus 4x squared over x squared, and then plus 6 over x squared. That's why when they added them together and subtracted, of course, when you did that, it became that. And now you can simplify them individually. So we have g of x is equal to, if you divide this by that, you get 3x to the power of 2, and then still have minus there, divide that, you get 4, and then x squared will cancel. And then here, you just have plus 6 and then x squared. But what we can do to get this to be derived is your x should not be on the denominator. So let's move it to the numerator. And so that makes the exponent negative. Now we can derive. We can say g prime of x. So we have 3 times 2, which is 6. And then we have x. And then we subtract 1 from that is 1. You don't have to write that. Then you have minus 4, of course. So when you are deriving a constant, it becomes 0. Okay, the gradient of every constant, like if you have y is equal to negative 4, it's a straight line. If you derive this function, it gives you 0, because every straight line or vertical flat line has a gradient of 0. That's the reason why. Okay, so we have that, and then this, when you derive, it's going to be this positive 6 times the negative 2, which is negative 12. We have x to the power of negative 2 minus 1, which is negative 3. Okay, so I'll just check. It's only 3 marks. So they would have given you a mark for separating, but not really expanding it. They don't give you a mark for doing this. It's the actual act of separating. So a mark for separating, probably a mark for putting that in its correct order, that, and then deriving. So it's 3 marks. You don't necessarily have to put this or write this as a positive exponent. You can if you want to, but at this point it's fine. Okay, so that is that. Moving on to the next question. Then we have the last question of question 8, and it says the equation of the tangent to f of x is equal to 3x squared plus bx plus c at x is equal to 1 is given by y is equal to that. So the equation of a tangent to this parabola, okay, at x is equal to 1 is given by this equation. You have to determine the values of b and c. Okay, let's go ahead and visualize what's going on. So they say the equation of a tangent to f of x, which we can see is a parabola that is concave up because the a value is greater than 0. So we have a concave up parabola, and we have a tangent to this parabola at x is equal to 1, right? And this is the equation of the tangent. I want you to also notice that the equation of this tangent, do you see that your gradient is greater than 0? So it is an increasing function. So it's going to look something like, I have the tangent there. I'll just pull that closer, of course. So you have that, and then it's touching the graph once, and we know it's touching the graph. So we know the equation of this tangent. It's y is equal to 9x minus 9. We also know where it touches the parabola. It touches the parabola at the point where x is equal to 1. So as you can see, because it's on this line, we can even find the y value. And then they also told us the equation of the parabola. Okay, so we have the a value at least. So they want us to find b and c. Okay, you see, this has to do with equations and simultaneous equations, really. If you have to find 2 variables, you will need 2 equations. So we're going to have to see how we can form these 2 equations. So since this is the equation of this function, in order to form this, I can see a way of, first of all, it would be helpful to find the y value of this. Okay, I can see a way that we can use the information that we have been given twice to form 2 separate equations. But I'm going to go ahead and find well, it's not really necessary. Let me show you. So you see, the powerful thing they gave you here is telling you that this was a tangent to this parabola. I want you to understand that the parabola, at different points, it has different gradients. So different gradients here, right? But the thing about a tangent is that a tangent is a straight line. And so its gradient is constant, okay? It doesn't change like a parabola. So because its gradient is constant, we already know the gradient of the tangent, it's 9. So because they meet, right, the tangent and the parabola, they meet at the point where x is equal to 1. Let me get rid of this. We don't really need this now. So because they meet at the point where x is equal to 1, we know that at this point, their gradient is exactly the same. So here's the first equation we can form from that. Knowing that their gradients are exactly the same, what I would do is I would attempt to find the gradient of f, because that's what I'm saying. I'm saying the gradient on f and the gradient of the tangent are the same at this point. So find the gradient of f. It's f prime of x is equal to, we say 3 times 2, which gives us 6. We have x, you subtract 1 from your 2, you get a 1, and you don't have to write that. It's invisible. Then you have here plus b. You see there's an exponent of 1 on the x. So you say b times 1, which is going to give you your b plus b. And then when you have your x, you see it has an exponent of 1. When you subtract that 1 from it, it becomes 0. Anything to the power of 0 gives you 1, and the b times 1 will just give you b. So this is what you get when you derive, when you try to find the gradient of the parabola. Now, we're not just looking for any gradient on this parabola. We're looking for a specific gradient. We're looking specifically for the gradient at this point. And we know that the gradient at this point is 9, because that's the gradient of your tangent. The tangent and the parabola have the gradient, the same gradient at that point. So what we're going to do is, before actually substituting the gradient, I'm going to say I'm specifically looking for the gradient of f at a particular point where x is equal to 1. That's what I'm looking for. So I'm going to substitute 1 into that. So substitute 1 plus b, you really just get 6 plus b, right? That's f prime of 1. Now the thing is, we already know what the gradient is at this point. That gradient is 9. So I'm going to substitute it into the gradient. F prime of 1 is speaking about your gradient of f at the point where x is equal to 1. I know that gradient is 9. So I'll rewrite that, and it's equal to 6 plus b. As you can see, we're already going to solve for b. Take 6 over, that gives you 9 minus 6, gives you b. And so you know that b is equal to 3. There we found our first expression. So our first equation technically. Now, what can we use to find the second equation? Well, it's quite simple. All you have to do is, why don't you just find the y value of this point? Once you find the y value of this point, substitute the x and y value into your graph of f, since this point lies on the graph of f, and then you'll find c, because you already have b. Okay, so that's the second thing we can do. So let's go ahead and find the y value. We can find the y value because it lies on this graph. So we say y is equal to 9, and then substitute in place of 9, 1, then minus 9. So y is equal to, that's 9 minus 9, which is 0. Okay, so that's the point. The point of contact, okay, with the tangent and that graph is 1 and 0. Now we're going to substitute this into our equation of f. So the y value is 0. I say 0 is equal to, and the x value is 1. So 3 times 1 squared plus, and we know what b is, it's 3. So 3 times 1 plus c. That's what we're looking for. And now we can go ahead and find this. So this is equal to, we have 0 is equal to 3 times 1 squared is just 3 plus 3, which is 6 plus c. Take 6 over, negative 6 is equal to c. So there you have c and you have b, and that's actually what they asked you to find. So that is that question, and that is the end of question 8. And then we move on to question 9. Okay, so now we're on question 9, and question 9 says the graph of f of x is equal to ax cubed plus bx squared plus cx minus 5 is drawn below. And then we have e, which is negative 1 and 0, and g, which is 5 and 0. And these are the x-intercepts of f. The first question is to find the values of a, b, and c. Now, I know many grade 12s actually struggle with when they give these questions, where they want you to find the formula of your cubic function. The thing is, you just have to focus on one thing. Focus on the graph and what they gave you. So you look at the graph, and do you see that the only points that they are specifically giving you are x-intercepts? So it means we're going to use the x-intercept formula. But now you have to use the proper formula. You see, with the x-intercept formula of a cubic function, and remember, because this is a memo, it's also a teaching opportunity, so I will explain in more detail. The thing about it is, let's just briefly explain that. You can have an x-intercept formula where you have 3 roots, like that, right? 3 roots, 3 x-intercepts. So with this type of formula, it's going to just look like this. Y is equal to a times x minus x1, meaning root 1, times x minus root 2, times x minus root 3, because these are 3 separate roots. Then you have an x-intercept formula where your graph somewhat does this. Doesn't always have to look like that. It can also look like this, for example. But ultimately what's actually happening is you have roots, but you have 2 roots instead. And the thing about these 2 roots is that one is a turning point and a root at the same time. So this will be the formula for that. Y is equal to a times x minus x1 times x minus x2 squared. So the one that is squared, you can already guess, would be the one that is a turning point and an x-intercept at the same time. Okay, so they gave us x-intercepts. We're going to use one of the x-intercept formulas. And of course, we're going to use this formula. Okay, so let's just establish what is our x1 and x2. Our x2 must be the one that is a turning point and an x-intercept. So x1 and x2. Our x1 would be this one because it's just an x-intercept. That's all, 5. And our x2 is the one that is a turning point and an x-intercept. So let's go ahead and substitute this. So we're going to say y is equal to, we have a times x minus our x1 is the 5. And then times x minus our x2 is the -1, which is really minus -1, which just becomes a +1. You just say +1 all squared. And now you see that the only thing missing in your formula is just your a. So to find a, if you could fill in numbers for x and y, because that's also x, then you would have a. So it means that you need a point, because a point is the only thing that will have x and y like that. So let's look and see, did they give us a point? Well, the graph looks empty, but if you look at the formula they gave you, do you see that they gave you a y-intercept? The only thing without x, your constant, is your y-intercept, and that's -5. So that's a point. So it means on your y-axis, this graph intersects the y-axis at -5. So the coordinates of that would be 0 as your x value and -5 as your y value. That's what we're going to substitute into this equation. So we're going to go ahead and substitute 0 and -5 in place of x and y. So that makes that -5 is equal to a times, and in place of x, 0 minus 5, and then 0 plus 1, all squared. Let's simplify. We have -5 is equal to, we have a. Let me actually just simplify on screen. 0 minus 5 is -5. 0 plus 1 is 1. 1 squared is 1. So you have -5 times 1, which is -5. And so to solve for a, you would divide both sides by that -5, and you see that a is finally equal to 1. Now that you have a, you can take a and substitute it into the part of the equation that was almost complete. So we're going to substitute it there. So that is, but I'm going to call this f of x because it is f of x. F of x is equal to, in place of a, we say 1 times x minus 5 times x plus 1 squared. Now, 1 times anything stays the same. So I can actually just pretend that 1 is not there. It multiplied. So f of x is equal to, we're going to leave this x minus 5 and then distribute that. Remember, that can be expressed as x plus 1 times x plus 1. That's what that squared is. So you could distribute the traditional way, or you could just do this. You look at the first term, you square that. That's x squared. Then you say first term times second term gives us x, and you multiply that by 2. So you get positive 2x. Then lastly, take the last term and square it, which will give you positive 1. And now we can distribute. So f of x is equal to, you say x times x squared, which gives you x cubed, x multiplied by 2x, which gives you positive 2x squared, x multiplied by positive 1 gives you positive x. -5 times x squared is -5x squared. -5 times positive 2x is -10x. And then -5 times positive 1 is -5. You see, end up with the same constant. So we have f of x is equal to, x cubed is the only thing with the cube. Then we have positive 2x squared minus 5x squared, which gives you -3x squared. And then positive x minus 10x gives you -9x. And we have -5. So because they told us that f of x was equal to the ax cubed plus bx squared plus cx minus 5, it therefore means that a is 1. As you can see, the coefficient is 1. We already found a. B is -3. And c is -9, just as they have said it is. Okay, so the key thing here, I know many students struggle with this. The key thing is, look at your graph, look at what they gave you. Based on that, you're going to use a particular formula. So that's 9.1. and we finally move on to the next question. The next question 9.2 says, calculate the value of x for which f has a local minimum value. Okay, so you have to think about the way f looks. F is that kind of graph. It's a cubic function with a positive a value. So that's what we have there. The local minimum, okay, would just be the lowest turning point. So that's your local minimum. So you see what they're actually asking you for. Calculate the value of x for which f has a local minimum. You just have to find the x value of your local minimum, okay, of that turning point. So let's go ahead and do that. We're going to have to try to find the turning point first. That's what we're going to do. So take the function of f, which we now know, just rewrite it. And now that we have our function of x, we're going to find the turning point since we're looking for the local minimum. So we're going to derive this function, f prime of x is equal to, and so that's going to give you 3x squared and minus 6x and minus 9. And now that you have that, to find the local minimum, you're going to make the gradient equal to 0, because the logic behind that is that when you have turning points, you see, it's all about gradients. We're looking at that. Here, the gradient is positive because this part of the graph is increasing. Then the gradient stands still. The gradient is 0 at this point. It's stationary. That's why these are stationary points. Then the gradient starts to get lower. It starts becoming negative, right? So these gradients are negative because this part of the graphs, they're really just decreasing. Then it reaches a point where it stands still and then goes up, okay? So at the stationary point, your gradient is stationary, it's 0. So we're going to say 0 is equal to 3x squared minus 6x minus 9. Okay, so just a bit of algebra here. Just going to go ahead and divide both sides by 3 since it's common all through. So we have 0 is equal to x squared minus 2x minus 3. Okay, so let's go ahead and factorize that. 0 is equal to, open up two brackets, we have x times x. And then factors of negative 3, they can give you 2. Why don't you just try negative 3 plus 1? That gives you negative 2. And if you multiply, it gives you negative 3. So x is therefore equal to 3, or x is equal to negative 1. So how do we know which one is our local minimum? Well, we know our graph looks like this. So the minimum is this one. As you can see, this would be an x value that is bigger than, let's just call that b. It's going to be an x value that is bigger than the x value here. So you know that you're supposed to take the bigger one. So just take, you know that it's going to be 3. So I'll cancel the negative one. Just in this scenario, I'm canceling it. And I'm saying that the x value for where we have a local minimum is where x is equal to 3. And that is our answer. Moving on to the next question. Question 9.3 says, use the graph to determine the values of x for which f double prime of x multiplied by f of x is greater than 0. So let's go ahead and get the graphs first. So if this is our graph, and they're specifically speaking about f of x, which is the one we have, and f double prime of x, let us just go ahead and find out what this one is going to look like. So in order to get to that, this is what happens. When you have your cubic function and you derive your cubic function, you end up with a parabola. Because this cubic function's a value was 1, meaning it's a value greater than 0, you have a cubic function that kind of looks like a capital letter N, okay? It's just more curved. If it's negative, it will look like a backwards N, okay? Just more curved. So because we have that, and because a was positive here, when you derive it and get a parabola, your parabola will also be concave up. But I want you to see how the parabola would look. It looks like that. But what actually happens is you see, I didn't draw it so well. Let me actually just try to put it right, like here, right? What happens is the x-intercept of these parabola would have the same x value as the turning point of your cubic function. So that turning point here, it would be the same x-intercept. That's why I said I didn't draw this so well. So I think it should be fine like that. So that same one should be that. But please notice that this parabola is when you derive f. So this is f prime. So what does f double prime look like? If you derive a parabola, you get a straight line. Because your parabola was concave up, your straight line is going to be an increasing function, but we need to at least know where it's going to be. So the thing about this parabola is the turning point of your parabola, the x value of that turning point, is going to be the same x value as your point of inflection of your cubic function. Okay, that point of inflection. Now here's the thing about the point of inflection, that x value of the point of inflection, so they're just speaking about the x values, is going to be the x value of your x-intercept of your straight line. This is f double prime of x. Okay, that's what it looks like, and that's how you know what it looks like. So you can kind of already look at the function and start drawing it in your head, and you can kind of see what it looks like. But of course, they expect you to, sketch it with a pencil so that you can find out what to do. So I only did that so that you know where this comes from. Okay, that we know how to get that now. That's the x value of the point of inflection of your cubic function. So I'm going to erase the parabola one because we don't really need that. Okay, I think this part is necessary. And now we can think about what we need to do. So because they say f double prime of x multiplied by f of x must be greater than 0. So the straight line times the cubic must be greater than 0. On your graph, the only way you can find this is, please note that when they say f double prime of x, they're referring to the y values of that graph and the y values of this graph. When you multiply them, they must give you something positive. The only way that's possible, okay, if you multiply two things and get a positive number, is if the two things are both positive or they're both negative. That's the only way that that's possible. So in other words, what you're looking for in these graphs is you're looking for places where the graph has negative values, both negative values or both positive values. And we can go ahead and search. Remember, you can use your trusty vertical line. Okay, hold on to your vertical line and let's look. So when we start off here, we know that of course this graph continues going down like that. And so it has a negative value, right? And at the same time, the cubic function as well. Let me actually just start from here. So it has a negative value. The cubic function also has a negative value. They're both negative here. That's one of the scenarios. Let's see. They keep being both negative. See that point? If that's a coordinate, that has a negative y value. This one also a negative y value. Okay, keep going. They both still have negative. And then here, something changes here. The reason I say something changes here is because think about the cubic function. What is the y value this cubic function has here? It's 0. Okay, so not negative, 0. And here, this one has a negative. So we'll keep that in mind. So it does not happen where x is equal to negative 1. We keep going. See that point over there has a negative y value. The y value of the straight line, negative y value. Keeps happening, keeps going, still negative, both negative. And then you get to here. At this point, the straight line has a y value of 0, right? And this has a negative y value. And now after that, look what happens. The straight line has a positive y value and the cubic function has a negative. We don't want that. We want them to both be both negative or both positive. So let's pause and actually just take the ones that we just found so long. So long, we found that we have both negative y values here. So here on that graph, and for this same x value, it's going to be for this part. But you need to remember not to include negative 1, because at negative 1, that y value is 0. If you take a y value of 0 and multiply it by the y value of negative whatever that is, you get 0 and not a positive number. Okay, that's not what they asked for. So we can see that it's working all the way here. So what are the x values for which it's working for? All these values, all of their x values are values that lie here. These are values that are less than negative 1. So I'm going to say that. I'm going to tell them that x is, well, I'm going to need to change that a little bit. The reason why I'm saying so is because you see that if we keep going, it also worked here. It stopped working like here, right? It also worked here because they both have negative y values here. See? For here and here, they both have negative y values. So I'm going to find a way to sum this up. What we can actually say is we need to find that x value first because we don't know what that is. We can see that it's working for values that are less than this, but of course not equal to -1. So let's go ahead and find that point of inflection, the x value. We only have to find the x value. So why don't we just use the derived function that we already have and then derive that further. Then we will find the point of inflection, the x value of the point of inflection of our cubic function. So when we derive this, we get f double prime of x is equal to, that gives you 6x minus 6. Then make that equal to 0 to find the point of inflection. You have 6x minus 6. Just take your negative 6 over, equal to 6x, divide both sides by 6, and therefore x is equal to 1. So we know our point of inflection now. And so now that we know that, we can answer them. See the highlighted parts, that's all the places that it's working. We're going to say that x is less than 1, but x is not equal to -1 because at -1, that doesn't work out, okay? That has a y value of 0, that has a negative y value. When you multiply them, they don't give you something positive, they give you 0. So there we say x is less than 1, but x is not equal to -1. We got that part. Let's keep seeing places that it's also going to work. So let's take our vertical line, and so you would use a ruler, of course. Take our vertical line and keep looking. So here we saw it didn't work because that has a y value of 0, that has a negative y value. Keep moving. This has a positive y value, that has a negative y value. That's not going to work. Positive times negative is negative, not positive. We're looking for where it's going to be positive. Keep going. So positive and negative, and it keeps doing that until you get to 5. At 5, the cubic function has a y value of 0. And at 5, the straight line has a positive y value because it keeps shooting up, right? And so after 5, do you see that the cubic function has a positive y value? And at the same time, for the same x value, this straight line will also have a positive y value. So positive times positive is a positive number. That's actually working out. So we can see that it starts to work from here onwards as well. Here. And of course, if that graph continued going, like after 5, it shoots up. So it works there where x is what than 5? X is greater than 5. Okay, so we're going to say that, or really how I can just put it is, instead of saying, oh, x is greater than 5, it looks weird like that. What you can just say is x is less than 1 or x is greater than 5, then tell them, but x must not be equal to -1. And that would be your answer for that question. So with graph interpretation, you just have to be very careful to make sure you are looking at the graph and looking at it thoroughly to make sure that you did get everything that it's working for and everything that it's not working for. Okay, so that is 9.3. We finally move on to the next question. Okay, 9.4 says, for which values of t will the graph of p of x is equal to f of x plus t have 2 distinct positive roots and 1 negative root? So this one, it's still graph interpretation, but it's more like graph manipulation, okay? Because you're going to have to manipulate this graph, move it with drawings and stuff to see how you can achieve these roots they're asking for. Please note that they said, for which values of t, okay, so solving for t this time, will the graph of p of x is equal to f of x plus t. So this is a new graph when we're adding t, have 2 distinct positive roots and 1 negative root. So you know you can't use delta here because we're working with the cubic function 1. And secondly, they're asking for very specific roots. When they start asking for things like positive and negative roots, you can't really use delta for that. Delta doesn't manipulate roots to that extent. So we need our graph. Let me go ahead and get our graph. And when we have our graph, they asked for, and I'm glad, not that it wouldn't have worked if it was negative, but I'm glad it is positive because it's just simpler when it's positive, okay? So I'm glad that t is positive. So f of x plus t will have 2 distinct positive roots and 1 negative root. Let's look at the roots that it has right now. Right now, it has only 2 roots, right? One is negative and one is positive. We needed to have 3 roots, but specifically 3 roots where 2 are positive, 1 is negative. So I'm going to draw an outline of this graph so I can properly move it up or down just so that we can see what is happening in this graph. Okay, so this is the outline that I drew, and we are going to go ahead and move this. So because we have plus t can just be anything. We're just going to think about what it should be. Are we moving it up? Are we moving it down? Let's go ahead and try moving it down. If you took this graph, you moved it down, look at what happens. See the issue here? No roots here, and you only have 1 root. So clearly moving it down is not an option. We need to move it up. So moving it back to its original position, if you move it up, what happens? Okay, so let's just move it up just by a little bit. So if it went just beyond it being at the x-axis, do you see now that what you would have is you have 1 root there, another, and another. 3 roots. But the thing is, we want 2 positive roots, 1 negative. Now you have 2 negative roots, 2 negative x-intercepts, and 1 positive. That's not what we want. So you would have to keep moving it up to see how that works. If you keep moving it up, let's say we move it to here. And this is a very important point because you see that after moving it from this point, right, where it is touching the x and the y-axis at the same time, if you move it beyond this, that's when you actually see 1 negative root and there's a positive and a positive root. So this is a very important key point here. What happened here? So you see that if we move it till here, right, if you just move it a little beyond this, that's when you start getting the roots you're looking for. So how must we move it for it to look like that? Think about this. We moved it to a point where the y and the x-intercept are both at 0. Before, the y-intercept was at what? We already knew that number. It was at -5, and you moved it to the point where the y-intercept was at 0. So how far up did you move it? How many units up did you move it? If this is -5, you must have moved it 5 units up so that it can land here. Okay, so that's a key point we're going to put there. Then I'm just going to copy this graph and actually put the proper one that we're supposed to have. Let's just change the color of it. We can change it to blue. Okay, so this is still our graph, still moving it. So now when you move it up, yes, now we finally have 1 negative root and 2 positive roots. So now we know that if you move it anything more than 5 units, you're going to have your negative root and your 2 positive roots. That's great. But must we just move it more than 5 units and just let it continue moving up more than 5? You can just continue shooting up more than 5 units. No, we can't do that, because at some point if you do that, it's only going to have, because that's going to extend down, it's only going to have 1 root and then nothing there. So it means that now you need to tell it where to stop. That's what we're really doing with this graph. So we know we need to move it up more than 5 units, but how far up? Okay, and let's just see. Let's move the graph and see what happens there. Okay, so for this, I created a green graph. So if I just kept moving it up and up and up and up, what happens? Still has the roots I'm looking for, negative and positive and positive, negative and positive and positive, until I get here. What happens when I get here is that I don't have 3 roots anymore. I have 2 roots. Do you see the key things we need to look at? We should not move it past this point. But how do we know how high that is? Because I know I must move it more than 5 units, but how much should I not move it past? Well, you can find out that by looking at what the y value was here, right? And when you moved it up to that green point, what is that y value now? That y value will be 0. So you just have to find out what exactly this y value is, and you tell them that you should not move it anything more than that amount of units. Because if it, for example, was like -9, right? Then it means that if you move it 9 units up, then your graph is going to sit like the green graph, and you shouldn't move it anything more than that. So another thing is we need to find that. So this was the local minimum. Let's find the y value of the local minimum. So now it makes sense that they asked us for the x value of that local minimum. We have the x value, we'll find the y value. So let's substitute 3 into that equation. So I'll put that calculation down. We'll say f of 3 is equal to 3 to the power of 3 minus 3 times 3 all squared minus 9 times 3 minus 5. And let's find that answer. And that number is much further than I thought it would be. It's f of 3 is actually equal to negative 32. So now we know that number. Okay, so that calculation, I'll leave it down there because it's going to be very helpful. So now I know that number there is a negative 32. So we should move it more than 5 units. Anything more than 5 units would give you a negative root and 2 positive roots, but nothing more than 32 units, because when you move it more than 32 units, when you move it 32 units exactly, you're going to only have 2 intercepts. And if you move it anything further than that, you only have 1 x-intercept. So how we would write the values of t is like this. T should be bigger than 5. It should be more than 5, but it must be less than 32. Move it anything more than 5 units, but nothing more than 32 units, and that's your answer. Okay, so that is the last question for question 9. Then we finally move on to question 10, which is our last question for calculus. And now we're on question 10. Question 10 says, EHGF is a rectangle. Now we have HE, okay, produced x squared centimeters to n. Okay, so HE is produced x squared centimeters to n. Okay, so that is being produced to n. Then they tell us that EH is produced x squared centimeters to p. So EH is produced x squared centimeters to p. Then they tell us that NF produce intersects PG at M. Okay, so those two get produced and they intersect at M. Then to form an isosceles triangle, MNP. So this is an isosceles triangle. So they're already telling us that this and this, those are equal. Okay. With, of course, they say it's NM being equal to PM or MP. D right there lies on NP, where MD is perpendicular to NP. So we have perpendicular. And then they tell us that NP, that is 4 units. And MD is 3 centimeters. Okay, they're all in centimeters. So MD is 3 centimeters. Okay. 10.1, you need to show that the area of EFGH is given by A of x is equal to 6x squared minus 3x cubed. Okay, so let's work with that. Let's see what we're going to get there. Okay, so let's just establish a few things. First of all, they made it very clear this is a rectangle. They said the rectangle. So we can consider all the properties of a rectangle on this. Okay. Regardless, they told us that these two lines, that and that, are equal. So that line and that line. So we have an isosceles triangle. And that's x squared, that's x squared. This is a rectangle. And we can see this is perpendicular. So this is 4 units. So already you can see that these two triangles are literally the exact same triangles. This one is just flipped around. So they're basically, those two triangles are congruent. Okay, so those are congruent triangles, and we can actually see them because you see you have a side being equal, we have a common side and an equal angle. They're both 90 degrees, so they're congruent. But this is not Euclid, so we don't have to give them reasons. We just have to conclude certain things. Okay, let's actually focus on, because I don't like to find things. I know I'm just analyzing a lot too much here. It's just because the shape looks intimidating. That's really all. But let's actually focus on what we would do to find what they told us to find. They said find the area of that rectangle. Naturally, to find the area of a rectangle, you just take the length and you multiply by the breadth. So if we're looking at that, they already call that B. So we need to take the length, which is EH, and we need to multiply it by the breadth, which is EF. And now I don't have to go searching for random things. I just have to focus on what I need to find. I need to find EH and EF. So we'll look at that. How do we find EH? Okay, that one seems quite simple to find. They told you this entire thing is 4 units. From here to here is x squared. From here to here is x squared. You see the remaining part is EH. So to find EH, you would just take the entire 4 units, and you minus it by this little part, the x squared, and you minus it by that other part, the x squared, and you'll be left with your EH. So EH in terms of x is 4 minus, see, negative x squared minus x squared is negative 2x squared. Okay, so we have EH, check. Now we just need to find EF. Let's look at this. How can we find EF? Okay, since this is part of a rectangle, a rectangle has certain properties. So let's actually consider the properties of that rectangle. First of all, a rectangle has 2 pairs of opposite sides being parallel. So that's parallel to that. And this is parallel to this. Sorry, I should give that a different type of marking for parallel. Okay, how does that actually help us? The goal is to find EF. So everything I should use should be to find EF. Let me look at this for a while. Okay, so when I looked at this for a while, at first, I was trying to consider, using like Pythagoras or something like that. But that's not really possible because unfortunately, like if I try to use Pythagoras on this, I need to have NF. Then I went on a whole spree of looking for NF and I did not find NF. So that's clearly not working. So what I'm going to go towards, because we have parallel lines, is I'm going to try and see, because I also noticed, remember that they told us that MD, right, is 3 units. Let's keep that in mind. They gave us that for a reason. There's no way they just put it there so that we can't use it. So because of that, I thought maybe we can use the proportionality theorem. If you tilt your head this way, right, you see this is a big triangle that you have. Because that's a triangle that you have, you can use the proportionality theorem. Now here's the thing about this line MD. It is a vertical line. We know it's a vertical line because it is perpendicular to our base, right? And our base is part of a line with a rectangle. A rectangle is made up of a vertical and a horizontal line. So this is a horizontal line, so this is vertical. Because it's vertical and these ones are vertical, they're all parallel. So if you tilt your head, let me just actually put that in black. So parallel, parallel, right? If you tilt your head and you look at the triangle NMD, do you see that you can use the proportionality? Well, it's not proportionality theorem I'm seeing here, because if it was proportionality, I would have to kind of like use this, maybe NF and NM, right? And then NE and ND. And that's not really possible because, yeah, sure, I can find NM because of Pythagoras, but I can't really find NF. That was the first headache in the first place. So it's not proportionality. Instead, you can try and use similarity. Look at these 2 triangles. Look at NEF and look at NDM. Those 2 triangles will be similar. You would know this from the similarity proof. I also have a video on that. Okay, so I'm not going to have to prove anything. This is not Euclid. So what I'm going to say is, and I'm just going to write this down for the sake of it helping me find my proportions. I'm going to tell them that triangle NEF is similar to triangle NDM. Okay, and here's just a brief explanation for why they're similar. You have parallel lines. That's corresponding angles. Those 2 angles are equal. You have a common angle being equal. And by default, the third angle in the triangles would be equal. So they're similar. And then we have, what we're going to do is we're going to use these proportions. Now, I don't know how it's going to work. I just know I need FE. And so I'm just going to try my best to work through that and hopefully it can help me find FE. So when you have similarity, when you have 2 triangles being similar, the sides are going to be in proportion in this way. So you see the side NE over ND. So you see NE over ND would be equal to the proportion will be equal to EF over DM. And that would be equal to NF over NM. Okay. And M. So I'm just going to fill in what we have and hopefully we'll be able to find one for FE. We will definitely will be because it's structured like that. So NE is x squared. So we're going to fill in. That's x squared. And D, what is ND? ND. Okay, so you see with ND, because this is a congruent, you see I showed you that these two triangles are congruent. You have an equal side, common side, and an equal angle, right? It would mean that this little part ND is 2 units, and that one is also 2 units, cut in half since it's a total of 4 units. So we have that. We have ND, it's 2 units, 2. Don't need reasons, it's not Euclid. EF. Now, where's EF? EF is this. What is what we're looking for? It's fine if it's empty. No problem, because we're looking for that. Over DM. DM is 3. Yay. So this is actually looking very good. I would have gone ahead and go and find these, but I see I don't even need them anymore. I just need these two. I'm going to work with that. Okay. So I'm just going to erase that. Don't really need that. This is, of course, because of similar triangles. Okay, the reason I say I don't need that, because you see that here, the only thing missing, the only side missing is EF. Everything has a value. This is x squared, but it's still in terms of x. So to find EF, we're dividing by 3. So to get rid of this 3 so that EF is alone, you'd multiply both sides by 3. And then it would mean that you're left with EF because the 3's would cancel. And here you'll be left with, you have 3 and x squared over 2. You can write that as 3 over 2 x squared. That's EF. Finally, we found EF. So there we have our 2 sides that we needed, and we can go ahead and use this now. So again, we're saying that the area is equal to EH, which we know is that, times EF, which we know is that. Okay, because this is one term, I'll write it first. That's x squared being multiplied by something that has 2 terms. So you need to use brackets so that it can multiply into both terms. So that's 4 minus 2x squared. Okay. Then we have A is equal to, we're going to multiply. So if you distribute in 3 over 2, maybe I should show you what this is going to do, times 4. What actually happens is when things are common, they cancel diagonally and also top and bottom like that. So diagonally, do you see that 2 is common? You're saying 2 divided by 2 is 1. 4 divided by 2 is 2. So all that's left is 3 times 2, which gives you 6, right? So in the numbers, that all that's left is 6. Then you still have x squared. Then if you multiply that as well, let's see what happens. So 3 over 2, I'm working on the numbers first, times negative 2. You see that diagonally 2 would cancel. 2 divided by 2 is 1. 2 divided by 2 is 1. So this is a negative 1. 3 times negative 1 is negative 3. And then of course there are x's. So x squared times x to the power of 2 as well is x to the power of 4. And there we go. That's a of x. I've been calling it a of x. And we finally found the value of a of x. Okay, so that's that, 4 marks. Moving on to the last question of question 10. Okay, and then the last question is calculate the maximum area of rectangle EFGH. Okay, so this is the area of it. To find the maximum area, you first have to find the value of x for which this area will be a maximum, okay? Okay, so we're going to take our function, and to find out its maximum x value, you're going to derive the function, basically finding the gradient, and then you're finding where the gradient is equal to 0, because at stationary points, this is where this graph is, you know, neither increasing nor decreasing. That's just those are the points that are sitting still on the curve. So on most curves that you see, these would be really key points to find whether this is the maximum or the minimum. Okay, so we're going to find the value of x for which this is going to be a maximum. To do that, you're finding the gradient of the function, and you're specifically finding where the gradient is equal to 0. So we're going to say a prime of x is equal to, that will give you, so multiply, we get 12x. Then negative 3 times 4 is negative 12. And we have x to the power of 4 minus 1, which is 3. Okay, so this is our function derived. Then you're going to set it equal to 0 so that you can find that maximum or minimum point. Okay, those turning points, the stationary points, is equal to, we have 12x minus 12x cubed. I can take that over. No, not really. Since they both have 12 and x, just take out 12x as a common factor. Then you're left with here, if you divide that by that, you get 1. If you divide this by that, you get negative x squared. Okay, so this is what we have. So we can say this can be factorized further. You can use difference of two squares if you want. It's not necessary. So I'll just say 0 is equal to 12x, or 1 minus x squared is equal to 0, right? Because they're being multiplied. If you have something times something and they give you 0, it's either that this one is equal to 0 or that one is equal to 0. So divide both sides by 12, and then you see that here 12 cancels. 0 divided by 12 is 0, so it means x is equal to 0. That's one solution for x. And here I'm just going to do this simple way, not the difference of two squares. So take negative x over, it becomes x squared. Square root both sides, but because this is an equation, you must say plus minus. So x is either equal to positive 1 or x is equal to negative 1. Okay, how do we know which one is our maximum? Well, this is not, a normal function that we're used to seeing. It's not a parabola or cubic function. So all you can do is really just substitute. We're going to substitute and see which one works. And I try a of 0 into our function of a of x. What do we get? I get 0. So that's just 0. If you try a of 1, a of 1 and a of negative 1, they're going to be the same thing. See, this is the reason why. Because here the x gets squared. So even if it was negative, it will become positive. And here the x gets raised to the power of 4. So even if it was also negative, it would be positive. So these ones will give you the same answer. So it doesn't matter actually. You can take either one. So let's try a of 1. If you substitute 1 into that, let's see what we get. We get 3. Okay, 3 centimeters squared, of course, because it's area. If you change it to, this is what I was saying, if you substitute negative 1, you're going to get the same thing. You see that a of negative 1 is also 3 because of that squared and that 4. So as you can see, the maximum out of that, the highest area that we can get from that shape would be the 3. So we can tell them that the maximum area, okay, is 3 centimeters squared, since they told us all of that was in centimeters. Okay, we're on question 8, and question 8.1 says we need to determine the derivative of this function. Okay, so we're deriving these functions. Always make sure that the function is actually ready to be derived. And as you can see, this one is good to go because you don't have any surds and no x on the denominators. So we can go ahead and derive that. And so to derive this, we're just going to say is equal to, and then again, coefficient times exponent, that's 3. We have x, exponent minus 1, that's 0. Anything to the power of 0 is 1. And of course, 1 times anything stays the same. Same thing here. Coefficient times exponents would be negative 10. And we have x, and then exponent minus 1, which is 1. And you don't have to write that. So that one is quite simple. And it's only 2 marks. So that is the answer there. Moving on to the next question. The next question, 8.1.2, says we need to derive this function. So find g prime of x if this is the function. Okay, so remember the whole story with getting your function ready to be derived. This function is not ready to be derived. There's too much things is wrong with it. So first of all, you have a x on the denominator. It needs to come up to the numerator. And you have a surd. So let's go ahead and fix that up first. So we have g of x is equal to, and the 2 is not a problem, so you don't move it. You're going to bring the x to the numerator. But the consequence is that its exponent becomes negative. And then we have minus. Now this is a surd. It shouldn't be a surd. You're just supposed to write that base so that its exponent is just a rational exponent. So we have x to the power of, and you're always going to say the inside exponent over the outside exponent. So that is 7 over 3. Okay, now it's ready to be derived. So we'll say g prime of x is equal to, and coefficient times exponent, negative 4x. Exponent minus 1 would be negative 3. And then here, coefficient times exponent is negative 7 over 3x. Exponent minus 1 would be, you can use a calculator, but this is like saying minus 3 over 3, which is 4 over 3. Okay, so that's what we get there. And then you can just write the exponent as a positive exponent. I mean, this is for 4 marks. So we're going to say g prime of x is equal to, and we have negative 4. Now, to make that exponent positive, it's currently on the numerator, so you need to move it down to the denominator. So over x to the power of 3. And then that's just minus 7 over 3, and then you have that. You can put it back in third form if you want to, but it's also fine as x to the power of 4 over 3. If we were putting it back in third form, it will be 7 over 3, and then you have your x, and you put your root, your radical first, and then you know that the inside exponent is always the top, because it's inside over outside. So the top exponent is the 4, so that's the one that goes inside. The outside exponent is the 3. Okay, so yeah, that's what it would look like if you put that back in third form. Okay, moving on to the next question. The next question, 8.2, says, determine the equation of the tangent to this graph. F of x is equal to that at the point where x is equal to 2. So this is a basic calculus type of questions you will learn in like the beginning stages of when you guys are learning calculus. So we just have a cubic function and it's a positive one, the one with a positive a or coefficient of x cubed. So it looks like an n, okay, just more curved. And then we have a tangent at the point where x is equal to 2. So wherever this is, it just means that because you have a tangent there, this graph just touches, okay, that line just touches the graph at one point. Okay, and we just have to find the equation of that. But we know that this is at x is equal to 2. Remember, because it's a tangent to your cubic function, it means that it's touching the cubic function at some point. So, because they want us to find the equation of the tangent, a tangent is a straight line. So that's that y is equal to mx plus c. So you see that all you need here is a gradient and a y-intercept. And of course, you find the y-intercept by just taking a point and substituting it into the function. So because we need a gradient, we can actually go ahead and find the gradient first. To find out what exactly the gradient of this tangent is, you are going to find out what is the gradient of the cubic function at this point, at x equals 2. So we can do that by actually deriving your cubic function. When you derive, you find in the gradient. So the derivative, we're saying f prime of x is equal to, and let's derive coefficient times exponent. We have 3x, exponent minus 1, 2. And then again, that's negative 8x, and then exponent minus 1 is 1. You don't have to write that. And then plus 2, and the x falls away, of course, because 1 minus 1 is 0. Anything to the power of 0 is 1. So right now what we have is the gradient of this function at any point. But we specifically want the gradient of this function at the point where x is equal to 2. So to find that gradient, we're going to substitute 2 into this gradient formula. So 3 times 2 squared minus 8 times 2 plus 2. And then you can just punch this into the calculator and find out what the gradient is. And we get negative 2. So we know now that the gradient at the point where x is equal to 2 is negative 2. So check, we have the gradient. And now we just need the y-intercept. And remember, to find that y-intercept, you just need a point on your tangent, okay? Now the point on the tangent is this point here. This is the only point that we have at that point of contact. So we have the x value, we just need the y value. So how do we find the y value? Well, this point also lies on the cubic function. So to find its y value, just take the x value and substitute it into the original function. So we're going to do that by saying f of 2 is equal to, and we will just substitute that into that. Okay, and once we do that, you see that the y value when x is 2, the y value is negative 1. Okay, now we have everything we need. We have a full point and we have the gradient. So you can choose to use the y equals mx plus c, or you can use y minus y1 is equal to m times x minus x1, which I prefer to use because after just substituting, you just simplify and you already have your equation. So the y1 and the y2, because right now we found out the point of contact, which is at 2 and negative 1. So this is going to be your x1 and that is your y1. So that is y minus negative 1, which of course becomes the positive 1, is equal to our gradient is negative 2. So that's negative 2 times x and then minus 2. Okay, So now we can just simplify this. So this is equal to, I'll start on this side and let's distribute. So that is going to be negative 2x, and then that is positive 4. Then on this side, we're going to leave the y, but take the positive 1 over and becomes a negative 1. And so you see that y is now finally equal to negative 2x and then plus 3. And that is our equation, negative 2x plus 3. Okay, so that is it for 8.2. And then we move on to the next question. The next question, 8.3, says f of x is equal to negative 6x squared. And we have to determine the derivative from first principles. Okay, 5 marks. This is an easy 5 marks. Just make sure that you work through this carefully so that you can get all your marks. Okay, so first of all, because we know we're using first principles, we already have the f of x. We need to get the f of x plus h first of all. Okay, the first principle formula is in the formula sheet as well. So that is negative 6 times x plus h squared. And this is equal to, we're going to say negative 6, and then we can FOIL out that. So you can choose to write 2 brackets. That takes longer. So I'm just going to first go ahead and square the first term, which is x squared, square the last term, which is h squared. And then first term times second term is xh. And then you multiply that by 2, which is positive 2xh. Okay, so that's what we have there. That was a positive h squared. Then you can just distribute the negative 6 in, which is negative 6x squared minus 12xh and minus 6h squared. Okay, so we have our f of x plus h, and we can go ahead and write our formula. So the derivative of f is equal to the limit as h approaches 0, and we're going to say f of x plus h minus f of x all over h. Again, formula is in the formula sheet. So limit as h approaches 0, and we're substituting f of x plus h, which is this. So negative 6x squared minus 12xh minus 6h squared minus f of x, which is negative 6x squared. So if you say minus negative 6x squared, you know that that's going to become positive at the end of the day. But I'm just going to put that like that first. So you have the exact same thing. Just make sure that you do not make mistakes when writing that. But the only difference is that's going to multiply in. So we're going to have this. I copy that h. We're going to have this again. And then we have, don't forget this part. And what happens here is that becomes a positive because it multiplies. So the only thing that's going to cancel is whatever you were subtracting by. So it's this, and that cancels with that. Those are exactly the same. Okay, now with what we have left, what do you notice about all of them? It's not even what we notice, it's what we're supposed to do. See, the problem right now is that h is not the denominator, and if you substitute 0, this is going to be undefined. So we need to take h out as a common factor so that it can cancel with the denominator of h. So we can take h out of these two terms, and in the first term here, you're left with negative 12x. And in the second term, you're left with negative 6h. Okay, all over h. And there you go. Your h's cancel, and now we are left with this. So you can choose to rewrite this. I'm just going to rewrite it actually. The limit as h approaches 0, we have negative 12x minus 6h. That's what's left. And now we can go ahead and substitute. So the derivative of this graph is negative 12x minus 6. Substitute 0 is equal to negative 12x. Okay, grade 12s, always make sure to double check whether this is actually correct by going to the original function and then using the rules of differentiation to actually derive this. So that is going to be coefficient times exponent, as you can see, is indeed negative 12x. Subtract the exponent by 1, and that's what we get. Okay, so that is correct. Moving on to the next question. The next question, 8.3.2, says, write down how you will restrict the domain of f such that the inverse, okay, is a function. Okay, so restrict the domain so that the inverse is a function, because we were working with a parabola. Remember, one thing you will learn about the parabola when you're working with inverse functions is that regardless of how the parabola looks, our parabola is actually concave down because you saw it was negative 6x squared. Okay, if you find the inverse of this parabola, it is going to just really do the opposite of what it's doing. Whatever it's doing on this side, right? You see that it's facing towards the bottom on the y-axis, towards the y-axis. It's going to do the same on the x-axis. So it's facing towards the negative part of the y-axis here. The inverse is just going to do this. Okay, it's going to face towards the negative part of the x-axis. And as you can see, this is not a function because it won't pass the vertical line test. You see, okay, it touches the vertical line twice, so it doesn't pass that. So it's not a function. So how do you restrict the original so that the inverse is a function? You do this at the turning point, because this is a point where you can actually control this graph. This is the point that actually causes this to not be a function. It should only have one wing, not two, and that's why it's not passing the vertical line test right now. So we're going to restrict it from its turning point. So what is the turning point of this function? Okay, it's already just negative 6x squared. Just like the y equals x squared graph, it lies on the origin. So that's where your turning point is. You can go ahead and find it using the formula x is equal to negative b over 2a, but it's useless at this point because you don't even have a b value. So b is 0. Okay, so you can already see 0 divided by anything is 0. Okay, so we know that the turning point is 0 and 0, but specifically the x value of the turning point is x is equal to 0. So how do you restrict this so that it is a function? Well, we're looking at the original. Let me just highlight that in red. So you're going to have to choose a half. Any half is fine. You can choose the left half or the right half and just restrict it like that. So if I decided to choose the right half, I'm really just saying the x values are, as you can see, if you line that to the x-axis, these are values that are starting at 0 and then moving towards the right. So they are values where x is greater than or equal to 0, and that would be restricting it. So you can either say this, if you like, you can go with x is less than or equal to 0. It will still be correct. So these two answers are correct. Because if we don't have this part of the graph anymore, then the inverse becomes a function because it's not going to have two wings. So what really happens is this part gets erased. Okay, this one is gone, and all you're left with is in the inverse, it will have an effect on it. So that's what you'll be left with, the other half. And now it's a function. It passes the vertical line test. You see, touches the vertical line once. Okay, so that is that. Moving on to the next question. Then 8.3.3 says determine the equation of the inverse, okay, for where the inverse's y values are going to be less than or equal to 0. And you need to write your answer in the form of y is equal to. Okay, so ultimately they're just asking us for the equation of the inverse. But at the last point, we're going to have to see which one we will choose because they specifically want the y values of the inverse to be negative. Okay, so find the equation of the inverse. The original function was that negative 6x squared, right? So we can say y equals negative 6x squared. And then to find the inverse, you know that you just have to swap the x and y value. So that is going to be x is equal to negative 6y squared. And then make y the subject. So to make y the subject, we have y squared right now. And so we need to get rid of the negative 6. So you can divide both sides by negative 6 since it's multiplying by the y squared. And then you're going to have, I'm just going to write this on this side, okay? So the y squared is equal to, and this is just negative x over 6. And here's the thing. Now to solve for y, you need to get rid of the square. The inverse operation of squaring is to square root both sides. But where you have your solution, because it's an equation, the positive and negative solution of this would work. Okay, so we're saying that y is equal to positive or negative square root of negative x over 6. But here's the thing about this. Remember that they said that the y values need to be less than or equal to 0. So you have a positive and negative solution for your y values. You're going to go for the negative solution since the range of the y values need to be negative. So the answer is negative square root negative x over 6. And I know you look at this and like, can we ever get values? Yes, we can. I know it's square root negative or something, but if x is a negative number, then yes, you're going to get solutions. Okay, so that is the equation. You can also write the domain for this. Okay, it's good to write the domain with the equation of your function. So the equation of this part. So since it's the inverse graph, you can actually just look at which one it was here with the little diagram. It's good to draw diagrams to just understand the bigger picture behind it. So it was the one where we had the inverse function, right, having negative y values. So when you look at that, do you see that with the inverse graph, there is this part that has positive y values. Okay, if you map it to the y-axis, these values are positive y values. And then there's the inverse part, the other half of the inverse function, that has negative y values. Okay, so clearly this is the one they're referring to. Do you see that the x values of that part is the part where x is less than or equal to 0? It's really for both of them. The only difference with the other wing is that its range is where the y values are greater than or equal to 0. Okay, so here I'll just say where x is less than or equal to 0. Okay, so there, that is our equation. And then we finally move on to question 9. Okay, question 9. We have a cubic function. They say a, which is 1 and 9, and b, that's 5 over 2 and 8, are turning points of the graph f below. And then we have c, which is a y-intercept over there. And the first question is, for which values of x is f decreasing? Okay, so when you're looking at a function, always make sure to read functions from left to right, like the way we read in general, left to right. So when you're looking at the parts of the graph that are decreasing, let's actually follow what this graph is doing throughout. From here, because we're reading from left to right, so I just follow the trend of it. So do you see that it's moving up like that? So that is increasing. Then something very important happens at this point, since it's a turning point. At this point, or at this stationary point, this graph stands still. So it's no longer increasing nor decreasing. And then at this point, what does it do? It decreases, okay? And then it stands still again, and then increases. So you can see the values of x for which it's decreasing is over here, between 1 and 5 over 2. Okay, so it's all of these values. So this is where our x values are greater than 1, but less than 5 over 2. Okay, so there we go. It is x is greater than 1, but less than 5 over 2. Okay, moving on to the next question. 9.2 says, write down the x-intercept of f prime, the derivative of f. So what are the x-intercepts of the derivative of a cubic function? You know that if you have a cubic function, right, and you derive it, it will become a parabola. In this case, as you can see, this is a cubic function that forms an n, a forward n. Okay, so it means that the a value where you have ax cubed, that is positive. Okay, so with that, when you derive this, it becomes a parabola, but specifically a concave up parabola, because you saw that the a value was greater than 0. So the question is, this is f prime. What are the x-intercepts of that? The x-intercepts of that will happen at the same x values as the turning point. Now, of course, the way I drew it, it doesn't even look right at all. Okay, it should be, let me just try and get a good sketch of it. Okay, something like that. Okay, so you see that the x values of your turning points would also be the x values of your x-intercepts. Okay, it's always important to make sure you study the graphs, your cubic function, and how it relates to the derivatives and what they look like in graphs. Okay, so that's what we know. So the x-intercepts, those x values, is x is equal to 1 and x is equal to 5 over 2. If you want to write them as coordinates, it's 1 and 0 and 5 over 2 and 0. Okay, so those are our answers there. Moving on to the next question. Okay, 9.3 says, for which values of x will f be concave up? Okay, so now we're speaking about concavity. You see, so this part, you just really needed to know how your graph works, how to, when you derive it, what does it form, what kind of parabola does it form, concave up or concave down. And you needed to know the relationship between these points, like the turning points and the x-intercepts of your derivative and so on. So with concavity, you know that the point that the graph changes, okay, its concavity is that point called the point of inflection. And all they really mean by concave up or concave down is just curved up or curved down, okay, like with the parabolas. So do you see that with the cubic function, there are two types of concavity that we have. we have concave down, and we have concave up. So they're asking the values of x for which it's concave up, so the green part. We would need to find the point of inflection. Now, even if you don't have the actual function, the full equation of the function, you can actually find this with only the turning points. You just need those x values. Remember how these, right, these x values are the x-intercepts of your parabola, the derivative of your cubic function. Well, you could decide to derive that again, or you can look at it like this. If you find the middle of your x-intercepts, you're going to get the x value of your parabola's turning point. Now that x value is the x value of your point of inflection. Okay, so with that, how do we actually find that x value of the point of inflection, since we know it is the x value of the turning point? You already have this and you have that. You know that the parabola is symmetrical about its turning point. So this part does the exact same thing as this part. So it means that to find that x value, all you have to do is think about it like this. From this point to here is exactly the same distance as from this point to here. Those are the same distance. So take this x value, add it to that x value, and divide by 2 to find the midpoint. Okay, so that's what we're going to do there. I'll say to find that x value, say x is equal to, I'll just say x1 plus x2 over 2. We don't really need a formula, but okay. And so we're taking our x values of our x-intercepts of the derivative, or really just the x values of the turning point, which is 1 and 5 over 2. So what is 1 plus 5 over 2 divided by 2? Okay, so 5 over 2, that's 2 over 2. You can use a calculator, but that's 7 over 2 divided by 2, which you can tip and times, becomes 1 over 2. And then therefore x is going to be equal to 7 over 4. Okay, so the values for which is concave up would be this part, the green part. Since you already know this is 7 over 4, do you see that it's concave up when we're moving towards the right hand side of 7 over 4? Here's 7 over 4. It's all the values moving towards this side. So the values that are greater than 7 over 4. Okay, so that is our answer there. X is greater than 7 over 4. That would be the values of x for which your cubic function is concave up, okay, curved up. Moving on to the next question. Okay, 9.4 says, determine the value of k for which y is equal to f of x plus k will have 3 positive x-intercepts. 3 positive x-intercepts. Okay, we're going to need the graph for this. So I'm just going to bring this graph down first. Okay, looking at our graph, they want 3 positive x-intercepts. So for it to have 3 positive x-intercepts, how should we move this graph? Well, you can look at the graph and actually try to move it up, but moving it up, you can see that's going to be a terrible idea because this function looks like this. If you pick up this graph and you start moving it up, you see that it's only going to keep having 1 x-intercept, which is going to be negative. So it's going to be here, right? And that's negative. So that's not going to work out. We need to move it down. Okay, so how far down though? Right now it has only 1 x-intercept. We needed to have 3, but specifically 3 positive ones. So you need to move it down until this turning point is first touching the x-axis. Then at this point it has 2 x-intercept, 1 here and 1 here. So 2 x-intercepts. And then if you move it further down, what happens? It has 3 x-intercepts. And you see that there are going to be 3 positive x-intercepts. Okay, now we can't just say, okay, we're just going to keep moving it down. We need to find out how far down we need to move it and how much should we not exceed, okay, to move it by. Okay, I just made that thinner because, yeah, it's easier to see like that. Okay, so let's see how we should move it. Now, you see how I said when we move it down, we need to move it until the turning point is touching the x-axis. You're going to control these by looking at the turning points. They're going to be a very important point here. So if you move this, right, from where it currently is, so that it sits on the x-axis, how far down did we move it? So remember here, the previous turning point, so the turning point here was 5 over 2 and 8. So 8 on the y-axis. And then you moved it down so that the y value, right, of that turning point is now 0. So how many units down did you move it? You moved it 8 units down. So if we can move it anything more than 8 units down, let me copy that. And now we have another version of it. If you move it anything more than 8 units down, then it's going to have 3 x-intercepts. You see, anything more than 8 units, 1, 2, 3 positive x-intercepts. Keeps having 3 positive x-intercepts. Okay, until what point? And here's how we find out that. If you keep moving it down and you move it to the point that it touches, you see the maximum, local maximum, touches the x-axis, then at this point it only has 2 x-intercepts. We need it to have 3. So it means that you shouldn't move it any more than this. So we need to move it more than 8 units down, but no more than what? Okay, again, look at, because we moved it so that this part sits on the x-axis. What was it previously? Its y value was 9. You moved it so that its y value is 0. So you moved it how many units down? That is 9 units down. So you need to move it more than 8 units down, but no more than 9 units down. Okay, so we have the two numbers that we're really looking for, 8 and 9. But now we need to see how we can actually explain that here. Okay. So the question is specifically determine the values of k for which y is equal to this, the graph, right? Plus k will have 3 positive roots. So you already know that you need to move it down. But here's the thing, we have a plus here. So we need to really think about that. Here's a way we can actually think about it. So if you had a minus, it would have been easier because this graph is already moving down. Because it has a plus, you need to just think a bit more here. Okay, so to think about this, you know that the graph needs to move down, right? So if it is moving down and we said anything more than 8 units down, because we needed to move down, you're going to have to make that 8 negative, okay? Because it's like saying f of x minus 8 so that it moves down. So how I would have said this was, I can say that we're really just saying f of x plus, and then whatever k is, k must just be negative. Okay, so looking at it here, we know that our k value, I'm just saying negative k because I needed to move down, right? Here, I knew that I need to move it more than 8 units down, but no more than 9. So I'm saying that my negative k needs to be greater than 8, but no more than 9. But here's the thing, that is negative. It needs to be positive. So you can either divide or multiply by -1, okay, to make the k positive. So now, this now reads as positive k, but your signs are going to change, okay? So they're going to look funny first, but we'll still get to the answer. So that becomes a -8, and that is a -9. Now, you can't leave this inequality like this because right now it's not really in the right order. So you're going to have to just think about what it's saying. We have k, right? And it's actually, you're looking at each number individually. But you know that the smaller number should come here and then the bigger number is here. Between -8 and -9, which one is smaller? It would be -9 because it's more to the left on the number line. Okay, and then you have -8. So we're going to put the -9 here, and then you're going to follow the inequality. The inequality is saying that k needs to be greater than -9. So just draw the inequality facing the k like it is. Okay, it's facing the k. And then here with the -8, do the same thing. Look at the k versus the -8, and you're going to draw the inequality facing the -8 because that's what it's doing here. So the inequality is actually saying that k needs to be greater than -9, but less than -8. And that is true, okay, because you look at the number line, we're saying that k can be any value bigger than -9, but no more than -8. And that's actually true for the graph as well. It can be values greater than -9, but you know that -9, because it's negative, values greater than -9 or stuff like -8.5. That's bigger than -9, okay? So it would still hold the same idea we needed it to hold, where we need it to go more than 8 units down. You see, that is a value greater than -9. Okay, but no more than -9 or no more than 9 units. Okay, so I hope that made sense. That's actually a way that you can actually just find the answer instead of overthinking it. We kind of treat it like we would normally, but because we know it's moving down, and since they use the plus here, we will just say, okay, it's f of x plus, and we make our k negative instead. And then you just sort out your inequality and make sure you write it in the right order. Okay, so that's it for that question. Moving on to question 10. Okay, we are on question 10. And question 10 says, a cyclist rode from town P and stopped at town T. The speed in kilometers per hour at which this cyclist rode is represented in the equation s prime of t is equal to negative 3t squared plus 18t. So you see that in this question, with the speed, it's being represented as a concave down parabola, first of all. And they already say s prime of t, meaning there was an s of t. Okay, so just keep that in mind. And then they tell us that, note, speed is the rate of change in distance with respect to time. Okay, so they're just telling us how to calculate, how speed is calculated. And the first question is, calculate the maximum speed that the cyclist reached on this ride. Okay, that seems fine because you see that the speed is already being given as a concave down parabola, and they just want us to find the maximum speed. So the highest speed, as you can see, would be at the turning point. So if it was on a graph like that, then we would have to find exactly what that highest speed was, which is really the y value of our turning point. Okay, let's go ahead and do that. So to do that, how do you find the y value of a turning point? Or really just the turning point? Well, you can use the x is equal to negative b over 2a. You can use that and then substitute to find your x value. Then when you find the x value, substitute that into this to find the y value. We could also derive as well. So we have s prime of t, but we could also use the derivative to find the turning point. So we have negative 3t squared plus 18t, and we could say s double prime of t is equal to, and let's derive, that's going to be negative 6t, okay, and now we have an exponent of 1, and then plus 18, and of course the t falls away because of the exponent of 0. Okay, and when we derive, we're really just finding the gradient. And once you found the gradient, we're really just trying to find where the gradient is equal to 0. So we'll make our gradient equal to 0. And we have negative 6t plus 18, and we can solve for t now. So we can take that over. So it's positive 6t is equal to 18. To solve for t, divide both hand sides by 6. Therefore, t is equal to 18 over 6, which is 3. Okay, so we know that t is equal to 3. This happens at 3 hours, and then we would substitute 3 into our equation to find exactly what that highest y value is. Okay, so let's just take that equation and substitute. So we have s prime of t, and we're going to say s prime of 3 is equal to negative 3 and substitute. And now we can just punch that into the calculator and see what this gives us. Okay, so s prime of 3 is equal to 27. And remember, this is a speed, so we're going to have to put it in kilometers per hour, as they said. Okay, so kilometers per hour. Okay, so that is what the maximum speed is. We can just also make a conclusion there. Okay, so there we go. Moving on to the next question. The next question, 10.2, says, calculate the distance between town P and town T. Okay, so we need to find the distance. When we're trying to find the distance, I mean, you could use distance formula, but it will have to make sense without diagram. So let's just look at what we have. The only thing they really gave us was the speed. But this is the speed from town P to town T, right? So that is a formula for it at different hours. Since they gave us the speed, and remember this was s prime of t, you know, we could find s of t. That's already what I'm thinking about, but I'm sure there are different ways of doing this. But let's just see. So we can find s of t actually. So you can think about it like this. If this represents the speed, okay, from town P to town T, which is really just in kilometers per hour. So how much distance did this cyclist move at every hour? Then if you get S of T, right, this would be the distance, okay, depending on each hour. So we can actually think about it like that. Okay, but remember that the question wants us to find the distance from town P to town T. For us to be able to use that S of T formula, okay, which is really the distance. This is going to be the distance formula since S prime of T is the speed, okay, it's the rate of the change in distance per hour. Then for us to actually use this, we need to know at what hour does the cyclist stop riding. So because it starts at town P and then it stops at town T, we need to know at what hour does he stop so that we can take that hour and substitute it into our distance formula, and that will give us the full distance that the cyclist traveled. Okay, so how do we find out where the cyclist stopped? Let's think about it. The only thing we have is the speed. What would be a marker for where the cyclist stopped? Well, you have the speed. And you know that the speed changes, or even we can even say the speed increases, first of all, we can see it here, as the cyclist starts to ride. And then it reaches a highest of 27 kilometers per hour, and then it starts to decrease. So one very important point here would be that when the cyclist starts riding, or right before the cyclist starts riding, the speed would be exactly zero because the bicycle's not moving, okay? So there's no speed there. The speed is exactly zero. And we also know that when the cyclist stops riding, the speed will also be exactly zero because you've come to a stop. So we can actually use that to our advantage here to find out where exactly the cyclist actually started and ended. So we can find that using the speed. Remember, this is where the speed is equal to zero. So let's just make the speed equation equal to zero to find those 2 points. Okay, so we're going to say S prime of T and make that equal to 0. S prime of T is equal to 0. And let's go ahead and just substitute. So we're really saying 0 is equal to whatever S prime of T was. And we can just solve for T now. Okay, because these are negative, I'll just take them over. So we have 3T squared minus 18T is equal to 0. Then see that we have a common factor. So we can take 3 out as a common factor, 3t specifically. And then what are we left with? 3t squared divided by 3t is t. Negative 18t divided by 3t is negative 6 is equal to 0. And therefore 3t is equal to 0, or t minus 6 equals 0. Divide both sides by 3 here. T is equal to 0, or t is equal to positive 6. So these are the starting and ending points. That actually makes sense now. That the cyclist starts at t is equal to 0 when the time is 0 hours, which makes sense, and when the time ends at 6 hours. Okay, that actually does make sense since the speed formed a parabola, and I think we should have already seen it from here. I didn't need to do all of that. We could have seen it from here because, so it's really that from this x-intercept, right? If from the first x-intercept to the maximum, there was a distance of 3 units, then from the maximum to the next x-intercept, there would also be a distance of 3 units. So that would make that at 6 units. So that makes sense. Okay, we didn't really need to do all of that, but yeah, we see that now. Okay, now the next thing to do, or the way I'm looking at this, since I'm going through this whole approach, we would have to find S of t. Okay, so how do we find S of t? We're really just going to have to find the antiderivative of this. So it's really just deriving backwards in a way. Okay, doing the reverse of deriving. Okay, so let's take this and then find out what it should have been, what it was before it got to this point. Okay, so if this was what we had, how do we find the original equation, S of t? So when you're deriving, you always take the coefficient and then you multiply it by the exponent, and then you're going to get whatever the coefficient of this is, which is negative 3. So it means we took something and we multiplied it by the exponent. If the exponent here is 2, it means that s of t's exponent must have been 3. So we said x or something multiplied by 3, and it gave us -3. Okay, so what exactly was that number we multiplied? See, this is really just an equation. Since you're multiplying by 3, to find x, you just divide by 3 on both sides. So x is equal to -1. So it means that what this was actually negative, and then you had t, and of course that is to the power of 3 since it's 2 here. Okay, so that's that part. And then to find this is positive 18t. Okay, so again, you must have said something multiplied by the exponent that was here. The exponent here is 1, so it means that the previous exponent for s of t was 2. Okay, so, and that gave us the 18 that we have here. So we're saying something times 2 is equal to 18. That could only be 9. Okay, you could divide both sides by 2, but that's 9. 9 times 2 is 18. So it means that you had positive 9t and then squared. Okay, since this is a 1 here. Okay, and then another thing I notice here is, because you know this always goes in the form of t cubed and t squared and then t. If this had a t, then you would have had a number, for example, like +5. Then I would know that, okay, then this was positive 5t, so that when you derive it, it becomes positive 5. But because we don't have anything here, it means there was no coefficient of t. There was nothing with t. So the only other thing that they could have been is a constant. So, for example, if the constant was 3, we wouldn't know from s prime of t, unfortunately. If the constant was 3, we wouldn't even know, because when you derive a constant, it becomes 0. So that's the only thing missing right now, and we can call that plus c. It's really the y-intercept that is missing. Okay, so this is the distance formula. Great. We know where this ends. We know that the journey ends at 6 hours, but we don't have this. So we can't actually substitute and find the answer now. We need to actually substitute a point that's going to help us to find c. Okay, so which point can that be? So with t is equal to 6, I have no idea what the y value is. What about t is equal to 0? Remember that the derivative, right, is your parabola. That is the rate of change in distance, the speed. This is the distance, and it forms a upside down n, a backwards n, I mean, right? But it's more curved. So we have that function, and c is missing. So we need a point on this graph to actually find this. Now, we do have a little information about this whole thing. We know that the maximum speed is 27 kilometers per hour. And there is a formula to actually find distance if you are given the speed and the time. And that formula is, you can remember that formula like this, dSTV. Okay, so distance, speed, and time. That distance is equal to speed multiplied by time, and then speed is equal to distance over time, and time is equal to distance over speed. Okay, so that is something that you guys learn in grade 9, roundabout. But the thing about this is I would love to use this to find the distance at 3 hours. But when you think about that, that's not really accurate, because the thing about this is you can see that the speed is not constant. It's changing as the cyclist goes on. So if you use 27 kilometers per hour to find a distance, so it's not going to be accurate because the speed is changing. So since the speed is changing, the best way to actually do that, to actually find a distance here, would have been to find the average speed. But then again, it's still an average. So I wouldn't actually, I don't want to go with that, because average speed is still an average. It's not exact. So let's just try to deal with this in a way that we can just get the exact speed. Okay, so what is another point we can use? What is a point that we actually have on this graph? If you think about that, remember that this cyclist starts his or her journey at t is equal to 0, right? 0 hours. So at 0 hours, what happens? The speed is 0, true. But this also means that the distance is 0, because the cyclist has not moved anywhere. You have not traveled any distance. So distance is 0. So there's actually a point we know on this graph, on the distance graph. We know that at t equals 0, the distance will also be 0. So we can use that. So we're really just substituting the points 0 and 0 into this function so that we can find c. Now, I don't actually have to substitute. You can, but if you do that, you'll see that c will be equal to 0. Because if we're saying that there's a point 0 and 0 on this function, we're really just saying that it has an x and a y intercept of 0, meaning c is equal to 0. Okay, so we know c now is equal to 0. So since we know c is equal to 0, then it means our distance formula is really just negative t cubed plus 9t squared, and that is it. So since this is the distance, we know where the cyclist stopped at t equals 6 hours. So let's substitute 6 into this formula so that we can actually find that. So s of 6 is equal to negative times 6 cubed plus 9 times 6, and let's find the answer here. And we get 108 kilometers. Okay, so that would be an exact, the exact answer there. We can also use average speed to actually find this. Okay, so that would be the answer. Okay, let's just see any alternative, way of doing this, because I'm still looking at this note. Speed is the rate of change in distance with respect to time. Well, that actually does seem like they're speaking about s of t. It's the rate of change, okay? Rate of change is gradient. Okay, so I'm going to leave it at that, especially because they gave us the speed as s prime of t, really just indicating that there was an s of t, and they did tell us about the speed being the rate of change in the distance with respect to time. Okay, so that is our answer. The distance from town P to T is 108 kilometers.